One of the most basic constants in physical science is the speed of light. In zero gravity, it reaches a speed of around 299,792 kilometers per second. For the sake of convenience, this speed is often rounded to 300,000 kilometers per s. The speed of light establishes an absolute maximum for the transport of both matter and data. In relativity theory and our knowledge of space and time, it is fundamental. The speed and behavior of light are fundamental to several scientific phenomena. The velocity of light is independent of both the source and the observer in a vacuum, where it stays constant. This consistency is fundamental to relativity, as proposed by Einstein. Light interacting with the medium's atoms causes this speed shift. The basic speed limit, established by light in a vacuum, is unaffected by this slowing down. There is an effect on time itself from the speed of light. Relative to an outside observer, time slows down for things as they approach the speed of light. Time dilation is an essential part of special relativity. Special relativity relies on dilation. In his famous equation, EH_mc², Einstein demonstrated the link between mass, energy, and the speed of light. The mass of an item grows in relation to its energy, which makes it more difficult to accelerate it to the speed of light according to this equation. According to the rules of contemporary physics, an endless amount of energy is required to travel at or above the speed of light. Light speed has both theoretical and practical consequences. Because of their great speeds and the Earth's gravitational field, relativistic effects must be considered by systems like GPS satellites. The precision of GPS would be drastically diminished in the absence of these adjustments. Due to the constant velocity of light, astronomical studies may reveal things' original, prehistoric states. The time it takes for light from faraway galaxies and stars to reach Earth is in the billions. When we gaze at these heavenly bodies, it seems as if we are seeing into the past. The magnitude of the cosmos can be better grasped with knowledge about the speed of light. Light years, the unit of distance that light travels in a year, are often used to measure distances in space. The vastness of cosmic distances may be better understood with the aid of this measurement. Numerous technological advancements rely on the speed of light. This includes the internet, fiber optics, and lasers. Our knowledge of the characteristics and behavior of light is crucial to these technologies. Innovation and connection are being pushed forward by developments in these domains. Light speed complicates our knowledge of transport at speeds greater than light in theoretical physics. Wormholes, warp drives, and quantum tunneling are some of the concepts that investigate potential methods to overcome the speed limit of light. There are exciting possibilities and substantial problems offered by each hypothesis. The boundaries of our knowledge of the speed of light are continuously being tested in experimental physics. Advanced observational methods and high-energy particle accelerators explore the frontiers of quantum physics and general relativity. Both novel phenomena and the validation of current ideas are the goals of these studies. Black holes and neutron stars are cosmic phenomena that show how important the speed of light is. Nearby massive bodies have such strong gravitational fields that they distort and alter the speed of light. By analyzing these impacts, we can learn more about the universe's most extreme environments. Theorizing about the nature and velocity of light, Einstein's ideas revolutionized contemporary physics. All three of space, time, and energy might be more easily understood with their help. Research and discovery are still guided by this paradigm. The influence of light speed changes depending on the circumstance, even if it is constant. We seldom ever become aware of relativistic impacts in our daily lives. On the other hand, these effects become noticeable while traveling at high speeds or in locations with high gravity. In order to progress technologically and discover more about the cosmos, knowing what they are is essential. For space research to continue in the future, faster than light travel is crucial. It stands for the prospect of contacting other galaxies and stars during our lifetimes. Humanity may be able to explore and populate other planets if this opens up new horizons. The immense lengths of space are one of the primary drivers of the search for faster-than-light travel. Proxima Centauri, the closest star, is more than 4 light-years distant. The present speed of spaceships makes the journey there seem like it would take an eternity. With travel at or faster than the speed of light, this trip may take months or even years instead of decades. It is possible that new planets might be found by exploring star systems other than our own. Some of these worlds may contain resources that are hard to come by on Earth, or they may even be inhabited. New avenues for exploration, resource exploitation, and maybe even housing for years to come may open up as a result of this. Traveling at speeds greater than light has the potential to completely change how we see the cosmos. We could see the stars in all their glory right now, thanks to this technology. This has the potential to pave the way for new discoveries in cosmology, astrophysics, and the study of the rules of nature. Another factor that could be critical to humanity's survival is interstellar travel. There are several natural and man-made dangers that Earth must contend with. A possible defense against future world disasters might be to set up colonies on other planets. Significant changes would be necessitated by the technical developments needed to achieve travel at the speed of light. Innovations that help many other disciplines might result from developing the energy sources, materials, and propulsion systems that are essential. In ways we haven't even thought of yet, these innovations have the potential to enhance our everyday lives. International cooperation might be enhanced by such trips. It is probable that international space organizations and countries will have to collaborate in order to accomplish this, potentially leading to more collaboration and peace on a worldwide scale. This might create a feeling of togetherness and one goal. A whole new crop of innovators, thinkers, and adventurers might be sparked by the quest for travel at the speed of light. Achieving such a massive feat might entice talented individuals to pursue careers in science, technology, engineering, and mathematics. Innovation and discovery might be propelled even further by this inflow of talent. The advent of travel at speeds faster than light would also open up new economic possibilities. Potentially lucrative new sectors might emerge in the space travel, mining, and transportation industries. This has the potential to boost economies everywhere and provide new employment opportunities in space as well as on Earth. Our way of life and perspective on the world might be upended by such innovations. Possibility of reaching faraway stars raises questions about our identity and our role in the cosmos. A spirit of exploration and wonder might be encouraged, leading to new heights for humanity. It would be beneficial for scientific research if tests could be conducted in a variety of settings. Conditions for research in physics, biology, and other fields might vary greatly depending on the planet and star system in question. Perhaps this will help us learn more about the cosmos and lead to some exciting new discoveries. Improvements in sustainability might be spurred by the pursuit of faster-than-light travel. Here on Earth, we may benefit from research into more efficient energy sources and space travel propulsion systems. Addressing environmental concerns and promoting sustainable living might be much easier with this. With time, ethical concerns would rise to the forefront. Before setting out on our cosmic adventure, we must think about how our actions could affect other planets and the life they may harbor. Because of this, new ethical frameworks and regulations may emerge. More people would probably start thinking about space and science. Potentially captivating the public's imagination is the notion of traveling to other stars. Scientific research and space exploration programs may get more funding as a result of this heightened interest. The ultimate goal of developing travel faster than light is to reimagine humanity. Our knowledge, bravery, and technological capabilities would be tested to their breaking points. Getting there may bring people together around a shared objective and open our eyes to possibilities beyond Earth. The public has a skewed view of faster-than-light travel. A lot of folks assume it's as easy as exceeding a certain speed limit, but there is a lot more nuance to the truth. Going faster than light is just part of it. A frequent misunderstanding is that being able to travel faster than light would enable one to reach every location in the universe in a moment. Although it has the potential to significantly cut down on travel time, the distances involved are still rather large. It may take years or even decades for a travel to occur, even at superluminal speeds. There are those who think breaking the speed of light would be impossible. But there are a lot of theoretical models that suggest methods to do it that don't violate any of these rules. Instead of going faster than light, these models often have space-time bent or warped. A lot of people think that we will soon be able to travel faster than light. The fact is that our grasp of the fundamental physics is still in its infancy. Practically traveling at the speed of light may be a long way off, if ever achieved. It is often believed that the technology necessary to accomplish travel faster than light currently exists. Science fiction often portrays spacecraft that are technologically sophisticated. Although this is much beyond what our present technology can do, we still need major advances in engineering and physics. Time travel and traveling faster than light are often confused. In theoretical physics, they are similar but distinct ideas. Although traveling faster than light may cause time to dilate, it does not necessarily permit time travel in the other direction. In the minds of many, traveling at the speed of light would be a breeze. Navigating intricate and maybe perilous space-time areas would really be required. There may be obstacles and dangers along the way that we haven't thought of yet. There are those who think that if we could travel faster than light, all of our space exploration issues would be resolved. Although it would be a significant improvement, there are still issues that must be resolved, such as radiation, life support, and human psychology. It's only a beginning. It won't fix everything. Some people think that any culture that could travel faster than light would be unbeatable. Having said that, there would be risks and restrictions associated with such powers. Superior technology cannot guarantee complete safety. The concept of traveling faster than light is typically simplified to just being faster. Actually, it incorporates intricate ideas like energy fields and space-time manipulation. Going fast isn't even close to the complex science that behind it. Many also think that communication would be instantaneous if we could travel faster than light. Having said that, the rules that regulate communication and travel are distinct. Separate from the aforementioned problems is the issue of faster-than-light communication. There are those who think that if we can travel faster than light, everyone will be able to use it. In all likelihood, only the very wealthy and technologically advanced would be able to afford it. Governments and huge companies may continue to control it for very some time. The idea that relativistic effects wouldn't apply to travel at speeds faster than light is a common misunderstanding. Relativity controls how things behave in space-time regardless of whether we manage to overcome the speed of light. The consequences of time dilation and others would continue to be relevant. There is a common belief that slower space travel will become obsolete if faster-than-light travel is achieved. For shorter distances and specific tasks, sub-light speed travel is still crucial. In a perfect world, both forms of travel would exist side by side. One more thing. The idea that traveling at speeds greater than light would be easy to manage and steer. In actuality, it would need very exact computations and control systems. Navigation would be very difficult due to the complexity of space-time. This film aims to go into the intriguing realm of travel at speeds faster than light. The many hypotheses and ideas put out by scientists over the years will be explored in detail. The possibilities and difficulties of traveling faster than light may be better understood if we have a firm knowledge of these concepts. We strive to provide a thorough synopsis of the leading hypotheses. The merits and shortcomings of each hypothesis will be pointed out after a thorough examination. You will have a comprehensive grasp of the present state of research after reading this. Your understanding of the underlying scientific concepts will be much enhanced after seeing this video. Simple, easy-to-understand chunks of information will be presented to you. This way, people from all walks of life will be able to follow along. How these ideas may change space travel forever is something we'll investigate. Possibilities for exploration and colonization might be expanded with the development of faster-than-light travel. We will talk about how it might affect the future of humankind in space. Another important goal is to clarify frequent misunderstandings. When it comes to thoughts about traveling faster than light, a lot of people rely on science fiction instead of actual scientific evidence. We will distinguish between fact and fiction. Furthermore, we will emphasize the present status of research in this domain. It is easier to plan for the future when we know where we are right now. Theoretical and experimental endeavors that are currently expanding our understanding will be detailed for you. We hope that by doing this, people would feel more awe and interest about the cosmos. People are fascinated by the concept of moving at speeds greater than light. We want to pique your curiosity in space and the unfathomable potential that exists beyond our present horizons. In order to accomplish these aims, we will examine the technical developments that are necessary, identify potential materials, energy sources, and propulsion systems that may be necessary. Practical difficulties and innovations will be highlighted in this conversation. The philosophical and ethical ramifications are another crucial component. What would the consequences be for the human race if we could travel at speeds of light? We will investigate the wider ramifications of perhaps accomplishing such a remarkable achievement. For these theories, we will give historical background. Decades, if not centuries, have passed, and many concepts have changed. To fully grasp the strides taken and the challenges that lie ahead, one must comprehend their evolution. Pioneers in this industry will also be featured in the video. Who have been the most influential scientists and intellectuals in expanding our knowledge? Recognizing those who are pushing limits requires showcasing their effort and accomplishments. Our goal is to spark conversations and arguments. Many people have different views on the matter of faster-than-light travel. The main objective is to get people to think critically and interact with the information. We aim for our material to be both informative and entertaining. We will simplify difficult ideas by using visual aids, animations, and analogies. Studying these ideas will be both entertaining and enlightening using this method. The creative and speculative sides of this subject will also be discussed. Although some theories are based on science, some go beyond what is presently known. It may be entertaining and illuminating to investigate these ideas. Lastly, we strive to provide a fair perspective. The possibility of traveling faster than light is thrilling, but there are several obstacles and constraints that must be considered. A genuine grasp of the subject is assured by presenting a balanced viewpoint. An overview of the idea of travel at speeds greater than the speed of light will be provided first. A concise synopsis of the light speed and its physical relevance will be provided. We may provide the groundwork for more advanced theories by first establishing a framework using elementary ideas. We will go into relativity, Einstein's theory of light and space, next. To clarify, this theory establishes the speed of light as the upper limit for the speed of space and time. Also discussed here are time dilation and the amount of energy needed to travel at the speed of light. Then we will go into the idea of wormholes. Wormholes are going to be defined, discussed, and the theoretical and practical difficulties associated with their potential to allow speedier travel. The section will focus on the possibilities as well as the hazards. Next, we'll examine warp drives, more especially the Alcubierre drive after wormholes. We'll go out how manipulating spacetime might pave the way for travel at the speed of light. Here we'll go into the science of warp bubbles and the unique materials needed for them. Next, we'll discuss tachyons, which are hypothetical particles capable of traveling at speeds greater than light. We will explore tachyon characteristics, their theoretical significance, and the difficulties in identifying and harnessing them. In this part, we shall delve into the fascinating opportunities that they provide. Next up, we'll talk about quantum tunneling. In this introductory quantum mechanics lesson, we will go over the fundamentals of the theory of particle tunneling. The consequences of traveling at speeds greater than light, as well as the scientific data that backs up these claims, will be covered in this section. Our attention will then turn to cosmic threads. These hypothetical objects have the potential to shorten paths across spacetime, allowing for travel at speeds greater than the speed of light. We'll go over their characteristics, possible energy uses, and where the field is right now in terms of research. Dark energy and the cosmos's expansion will be discussed in the next section. We will investigate potential ways to use the universe's accelerated expansion to move quicker. Theoretical models and energy needs are covered in detail in this section. We will analyze the function of exotic matter and negative mass once we have covered dark energy. These ideas are fundamental to several theories of transport at speeds greater than light. We'll go over what they are, how they may be made, and the difficulties that come with them. Quantum entanglement will be the center of our attention as we move on to faster-than-light communication. Using entanglement as an example, we'll talk about the potential benefits and difficulties of instantaneous information transmission. Potentially reshaping communication is what this part will focus on. Practical initiatives, such as Breakthrough Starshot, will be discussed next. We'll give you the rundown on the project, its goals, and the technologies that are in the works. Here we shall highlight the real-world initiatives aimed at accomplishing travel faster than light. After that, we will look at connected global programs and activities. The worldwide quest for faster-than-light travel may be better understood by highlighting different initiatives. Possible future advancements and their associated timetables will also be covered in this section. After we wrap up the project talks, we'll talk about the bigger picture of what it would mean to achieve travel faster than light. This encompasses the possible effects on astronomy, colonization, and space travel. We will also discuss the ethical and social factors. A review of the major ideas and theories we've discussed will make up our last major portion. By doing so, you will be able to review the key ideas and solidify your comprehension. Before we wrap up, let's make sure everyone is on the same page with this summary. Visual aids, animations, and analogies will be used throughout the presentation to simplify otherwise difficult subjects. By taking this tack, we can keep viewers' attention and make sure they have fun while learning. When Albert Einstein proposed special relativity in 1905, it radically altered how we saw space and time. Fundamentally, it states that all observers who are not speeding adhere to the same physical principles. The use of this theory yields unexpected and counterintuitive outcomes. The unchanging nature of the speed of light is a well-known feature of special relativity. The velocity of light in a vacuum is independent of both the source's and the observer's motion. The speed of light in a vacuum is constant, which is a fundamental property of both the source and the observer's motion. An essential component of the theory is this consistency. Additionally, the idea of time dilation is introduced by special relativity. The relative passage of time for an object and a stationary observer both decreases as the object gets closer to the speed of light. Therefore, compared to a stationary person, a traveler traveling at high speeds would age more slowly. Length contraction is another important idea. Objects traveling at near light speed will seem to be shrunk in the direction of their motion when seen from a fixed point in space. At really high speeds, this impact becomes apparent. Simultaneity is likewise rethought in light of this idea. Things that seem to happen at the same time in one perspective could really be happening at different times in another. Space and time are inherently related, as this relativity of simultaneity demonstrates. According to special relativity, space and time are really one continuous four-dimensional field. Time is seen in this model as one of the four spatial dimensions. If we want to comprehend relativistic consequences, we must achieve this unity. From the field of special relativity arises the well-known equation EHmc2. The fact that mass and energy are essentially the same suggests that even a little quantity of mass may be transformed into a great deal of energy. Nuclear processes provide energy based on this idea. Also, motion and energy are impacted by special relativity. Contrary to what one would expect from classical physics, an object's momentum and kinetic energy both rise as its speed does. These amounts grow exponentially as one approaches the speed of light. Multiple experiments have verified the hypothesis. Particle accelerator observations of high velocities are in agreement with special relativity predictions. The results of these experiments prove that it is correct. Many parts of contemporary technology are affected by special relativity. To provide precise location data, the Global Positioning System, GPS, must, for instance, take relativistic effects into consideration. The system would rapidly start to mislead users if these adjustments weren't made. Cosmology and our knowledge of the cosmos are also affected by the idea. It is involved in star dynamics, black hole dynamics, and cosmic expansion. A crucial part of contemporary astronomy is special relativity. Special relativity has philosophical ramifications in addition to its effects on science. It makes us reevaluate ideas that seemed absolute, like space and time, which goes against our instinctive understandings. Our perspective is profoundly affected by this transition. The foundation for Einstein's subsequent work on general relativity was built by special relativity. General relativity expands the ideas of special relativity to include acceleration and gravity, whereas special relativity focuses on frames of reference that do not accelerate. Advanced physics ideas cannot be understood without first mastering special relativity. It lays the groundwork for investigating phenomena at high speeds and in harsh environments. Engineers and physicists must have a firm grasp of these ideas. Special relativity has had and will have far-reaching effects on scientific thinking because of its groundbreaking concepts. Its influence lives on in the never-ending search for truth, which is expanding the frontiers of human understanding. One of the most extreme limits on how fast something can travel in the cosmos is the speed of light. In a vacuum, nothing can move faster than light, according to Einstein's theory of relativity. The rules of physical science include this restriction as an essential component. The fact that an object's mass effectively grows as its velocity rises is one explanation for this limit. The mass of an item approaches infinite as it gets closer to the speed of light. To reach the speed of light, unlimited energy would be required. Light particles, or photons, may move at the speed of light because they do not have any rest mass. The limitless energy needed to achieve this speed makes it impossible for anything with mass to do so. To grasp light's exceptional status, this differentiation is fundamental. Additionally, the universe's causality is guaranteed by the speed of light. With causation, one event causes another to take place. This concept may be violated if travel at speeds greater than light became feasible, leading to paradoxes in which the consequences come before the causes. The structure of spacetime is preserved by the light speed limit, which also prevents causality violations. It checks that various reference frames don't mess with the spacetime connections. A fundamental aspect of relativity is this consistency, as seen via various lenses. According to the theory of relativity, all inertial frames of reference have the same speed of light. This constancy is true regardless of whether the light source or the observer is in motion. It's one thing that distinguishes light from other things. Light speed is more than a theoretical concept. It has real-world applications as well. This steady speed is crucial for technologies like as radar, communications, and GPS. It is crucial for contemporary technology to comprehend and make use of this constraint. Additionally, the velocity of light is critical to astronomical measurements. Light that has traveled millions or billions of years is what we perceive when we look at faraway things. This speed restriction sheds light on the vastness and age of the cosmos. On a vacuum, the speed of light is around 299,592 kilometers per s. Accuracy in scientific computations and observations depends on this precise number. It's a cornerstone of physics and a basic constant. Because of interactions with other materials, light travels at a slower rate through water and glass, among other media. But the rule that nothing can travel faster than light in a vacuum still stands, even under these conditions. Because of this difference, the applicability of the speed limit becomes more apparent. Time would dilate infinitely if one traveled at or above the speed of light, according to special relativity. A body traveling at the speed of light would cause time to stand still. This outcome further proves that this cosmic limit cannot be surpassed. There is a relationship between energy, momentum, and the speed of light. These values have unusual behavior at high speeds according to relativistic physics. Energy and momentum are kept limited and calculable by the speed limit of light. Many ideas suggest warping or bending spacetime in order to achieve faster-than-light travel. Without really surpassing the speed of light, these concepts seek to go around it. Scientists are researching unique techniques, and these approaches are highlighted. The immensity of space may be better understood if we know how fast light travels. Reaching the closest stars would take years, even traveling at the speed of light. From this vantage point, the enormous scales of interstellar distances become clear. Among the most fascinating features of contemporary physics is the concept of the speed of light as a cosmic speed limit. It influences how we think about the cosmos, directs new technologies, and motivates scientists to keep digging. One of the most intriguing effects of special relativity is the dilation of time. It explains how, for an object approaching the speed of light, time seems to stand still. At almost light speeds, this impact becomes noticeable. Think about how fast you could go in a spacecraft if you tried. An outsider looking in would see that your clock is ticking more slowly than a person at rest. You would have a slower rate of aging during your voyage. Time dilation describes this occurrence. Experiments have verified the consequences of time dilation. For instance, in particle accelerators, particles in motion have slower decay rates compared to those at rest. The predictions of special relativity are supported by these findings. Because of their very high orbital speeds, astronauts feel a little dilation of time. The impact is little, but quantifiable. Time dilation affects even human spaceflight, as this real-life case shows. Even GPS satellites are affected by time dilation. Their watches work at a quicker rate than ours because of the reduced force of gravity in orbit. It is clear how important this impact is in practice, since corrections are required to provide accurate positioning data. Another fascinating consequence of special relativity is the shortening of distances. Things that are traveling at a rapid pace seem to shrink as they go in the same direction. Similar to how time dilation becomes apparent at near-light speeds, this phenomenon does the same. Think of a spacecraft at almost the speed of light. Along its path of passage, the spacecraft would seem compressed to an outside viewer. Length contraction describes this occurrence. The speed of the item determines the magnitude of the contraction. The magnitude of the contraction is proportional to the object's speed. That the object's length might hypothetically shrink to zero at the speed of light is an extreme example of relativistic effects. The effects of length contraction on our perception of spatial relationships are far-reaching. It demonstrates how one's point of view affects the accuracy of spatial measurements. Relativity calls into question our common-sense understanding of constant distances. The length contraction has been verified in experiments with particles traveling at high speeds. For instance, muons produced in the high atmosphere decelerate after a longer than anticipated journey. Because of the length contraction caused by their great speed, they are able to reach the surface of the Earth. Aspects of special relativity that are interrelated include time dilation and length contraction. They both originate from the same fundamental laws that control the way space and time behave. One sheds light on the other when the other is understood. These impacts test the boundaries of what we consider to be normal. Time and length seem to be absolute constants at usual speeds. Relativistic speeds change our vision by revealing how these dimensions are fluid and dynamic. Modern cosmology and sophisticated physical theories rely on time dilation and length contraction. Objects' behavior near black holes or in high-energy particle collisions are examples of extreme situations that they shed light on. Research into these impacts continues to challenge established scientific norms. Their potential effects on future technology and our knowledge of the cosmos are being investigated by researchers. Both theoretical and experimental physicists continue to focus on the issues of time dilation and length contraction. Not only do these relativistic effects enrich our knowledge of the universe, but they also motivate future generations of researchers. Curiosity and new discoveries in physics are sparked by the peculiar and paradoxical properties of time dilation and length contraction. An huge quantity of energy is needed to achieve the speed of light. If you believe Einstein's theory of relativity, the mass of an item grows proportionally as its speed rises. It becomes more difficult to maintain acceleration as the object's mass increases. Increasing an object's speed requires more energy as it approaches the speed of light. This connection is not straight. The power needed increases at an exponential rate. The necessary energy becomes limitless at light speed, rendering it essentially unattainable according to our present knowledge of physics. No matter how little an item is, if it has mass, it must overcome this exponential energy consumption in order to achieve light speed. No amount of energy can get particles accelerated to speeds close to light, even in the most sophisticated particle accelerators like CERN. A major obstacle is the idea of endless energy. The levels required are much above the capabilities of our present energy sources and technological capabilities. According to the laws of known physics, this restriction is applicable to all possible propulsion systems. These energy needs are put into practice in particle accelerators. For instance, it is possible to increase proton speeds to more than 9,999% of the speed of light, but this endeavor requires massive quantities of energy and very specialized machinery. Think of something basic, like a spaceship, to get a feel for the amount of energy required. The kinetic energy of the spaceship is growing exponentially as it approaches the speed of light. Even a star's whole energy production wouldn't be enough to keep up with the ever-increasing energy intake. This energy barrier is present even in speculative propulsion technologies like antimatter engines. The large energy outputs produced by antimatter processes are insufficient to achieve light speed because the amount of energy needed is unlimited. This highlights how big of a task it is. An important consideration in these talks is energy efficiency. Chemical rockets and ion drives, the two main forms of propulsion now in use, are woefully inadequate. Just to get close to practical energy needs, new, revolutionary physics and engineering breakthroughs are required. Alternate methods, such warp drives or altering space-time, are put forward by certain theorists. In order to avoid using infinite energy, these strategies try to change the basic characteristics of space and time instead than just sending a mass hurtling towards the speed of light. For instance, a warp drive entails, among other things, the formation of a space-time bubble capable of traveling at the speed of light. The spaceship would stay in one place with relation to its local space-time inside this bubble. This method uses the elasticity of space-time to circumvent the endless energy conundrum. Nevertheless, substantial energy requirements are encountered by even these sophisticated ideas. Building and maintaining a warp bubble will need unconventional energy and materials that are now unavailable to us. Energy scales that are considerably beyond our current capabilities are often used in theoretical simulations. Theoretical physics is being tested as we investigate these energy demands. It calls into question our long-held beliefs about the nature of the cosmos, matter, and energy. In the hopes of finding a way to travel faster than light, scientists are constantly pushing the boundaries of what is already known. There are both theoretical and practical factors to think about. Massive technical challenges exist in producing, storing, and effectively using such enormous quantities of energy. It is just as important to overcome these challenges as it is to make theoretical discoveries. The pursuit of reaching or surpassing the speed of light motivates advancements in several scientific fields. We are getting closer to breaking through the enormous energy hurdles with every new development in energy generation, storage, materials, and propulsion technologies. Insight into the energy needs of light-speed transport sheds insight on the obstacles and motivates the search for novel solutions. The incredible possibilities and deep secrets of interstellar travel are brought to light by this. The discovery of space travel at speeds faster than light would revolutionize our view of the cosmos. We might travel to other galaxies and stars in a fraction of the time it takes us now if this were to succeed, completely changing the face of space research. Potentially new vistas for human exploration and development might be revealed by this revelation. Possessing the capability to surpass the speed of light would put our present physical laws to the test. The concepts that have guided our perception of time and space for more than 100 years would have to be rethought in light of this. We may learn more about the universe and develop new revolutionary hypotheses as a result of this. It is critical to investigate the consequences for causation. The prospect of time travel, with events possibly happening in a different order, is enhanced by the development of faster-than-light travel. Paradoxes that contradict our common understanding of cause and effect might emerge from this, creating formidable obstacles in philosophy and science. Distance communication would be revolutionized. We could have real-time communication between Earth and faraway space colonies if messages could be transmitted instantly over space and time. The way we communicate and work together in different locations would be completely changed by this. If this trend continues, the search for alien life may soon be within reach. Exoplanets that are now inaccessible to humans may be visited if we could travel faster than light. Our position in the cosmos might be drastically changed if this investigation reveals new ecosystems and life forms. International diplomacy and space policy would also be affected by the possibility of traveling faster than light. Because of the potential strategic benefits of this technology, new types of international rivalry and cooperation may emerge. This situation calls for fresh foundations for regulations and treaties. The capacity to travel at the speed of light has the potential to stimulate the growth of new economic sectors. Economic development, new investment possibilities, and job prospects might result from space mining, tourism, and colonization becoming viable industries. Our views on energy and propulsion may also shift if we are able to travel faster than light. Beyond space travel, the technology needed to reach such speeds would revolutionize energy generation, transportation, and other industries. Human psychology and society stand to gain a great deal from this. New cultural adjustments and adaptations would be necessary to live and travel across space at such speeds. We may have a different understanding of reality and our role in the cosmos if time and space were to shift in this way. Also, we need to think about how traveling faster than light will affect the environment. Unforeseen outcomes may result from the energy demands and the adverse repercussions of such travel. If we want to keep any bad effects to a minimum, we must develop and handle this technology responsibly. Greater possibilities for scientific inquiry would be made possible by travel at speeds faster than light. This would allow scientists to examine events up close that can only be seen from far away at the moment. A plethora of fresh information and understandings on the cosmos would result from this. A future when humans are able to explore and colonize other star systems is a real possibility. Asteroid strikes and other global disasters pose an existential threat to life on Earth. Setting up colonies on other planets would protect humanity from this danger. Different philosophies and cultural currents on humanity's role in the cosmos would develop. New kinds of literature, art, and philosophy would emerge if we could travel across space at such speeds. It would test and enrich our shared identity and creativity. There are serious moral questions with space travel at the speed of light. Thorough consideration must be given to matters such as the possible inequalities in access to this technology, the energy consumption, and the effects on indigenous species. In the end, the consequences of traveling faster than light go far beyond the domain of science and technology. From our cosmic perceptions to our social systems and moral compass, they permeate every facet of human life. We must investigate these consequences if we are to keep expanding the limits of what is achievable. What we mean when we talk about moving faster than light is going faster than the speed of light in a vacuum, which is about 299,792 kilometers per s. Although it is more often associated with science fiction, this concept really originates in theoretical physics. This idea casts doubt on many of the physical principles that we hold dear, most notably Einstein's theory of relativity. An item's mass grows exponentially as it gets closer to the speed of light, necessitating infinite energy to achieve light speed, according to general theory of relativity. Conventional methods of traveling faster than light appear to be rendered impossible by this. But this hasn't stopped people from coming up with ideas and speculations that might break beyond the speed of light. In these theories, bending or modifying spacetime is more common than just sending an object hurtling toward the speed of light. The notion of wormholes is one example of this. In theory, wormholes might connect seemingly unrelated locations in the cosmos, allowing for the creation of time travel via other realities. If they could be crossed, the distance needed to travel faster than light may be significantly reduced. A second well-known theoretical model is the Alcubierre warp drive. Physicist Miguel Alcubierre proposed this idea, which entails inflating space behind a spaceship while simultaneously contracting it in front of it by use of a warp bubble. The spaceship would be able to avoid the need to travel faster than light by remaining motionless inside this bubble. Tachyons are an additional intriguing speculative concept. Assumedly, these particles can never travel slower than light. Although their existence has not been verified, they provide fascinating opportunities for comprehending events that occur at speeds faster than light. In quantum physics, a phenomenon known as quantum tunneling allows particles to instantly traverse energy barriers. Despite its lack of direct relevance to lightspeed travel, it does raise the possibility that superluminal transit may make use of certain quantum phenomena. Another idea is cosmic strings, which are theoretically one-dimensional holes in space-time fabric. If they do in fact exist, their ability to distort space-time around them could make it possible to move at the speed of light. An other field that may be investigated is dark energy and the rapid expansion of the cosmos. There are hypotheses that propose we may potentially accomplish faster-than-light travel by using or imitating these cosmic forces. These ideas also include exotic materials and negative mass. For phenomena such as the Alcubierre warp drive to work, which requires exotic energy to warp spacetime, negative mass, if it exists, might provide the repulsive gravitational forces that are required. One idea behind faster-than-light communication is the idea of sending data at the speed of light. The story of a real-life project pushing the boundaries of high-speed space travel is Breakthrough Starshot. It aims for relativistic rates rather than faster-than-light travel, and represents the cutting edge of our current technological capabilities. One potential mechanism for this is quantum entanglement, where particles become interconnected regardless of distance. However, it does not violate relativity in the same way as physical travel. In their ongoing quest to expand our knowledge of space, time, and energy, theoretical physicists delve further into these concepts. All of these ideas are just that, conjectures, but they provide light on the possibility of travel at speeds faster than light. A lot of the time, the kinds of matter and energy needed to test these hypotheses are beyond our present capabilities. In both theoretical and experimental physics, the pursuit of exotic matter and methods to control spacetime remains a driving force. We can better grasp the difficulties and opportunities of faster-than-light travel if we are familiar with its theoretical foundations. Furthermore, it stimulates the imagination, which in turn encourages both the general public and scientists to think about what is conceivable in the future. Wormholes, or Einstein-Rosen bridges, are hypothetical holes in spacetime. In 1935, as part of their work on general relativity, Albert Einstein and Nathan Rosen first postulated them. One way to think of a wormhole is as a passageway that links two different locations in spacetime. In theory, this tunnel may eliminate the need for any kind of intermediate area and enable instantaneous passage between the two locations. A wormhole is a possible answer to the general relativity equations. They provide a picture of a gravitational bridge connecting two black holes or other massive holes in space. At least in principle, if additional substantial gravity wells could be stabilized, such a bridge may be possible. If this kind of bridge could be made to stay upright, it would theoretically allow us to travel faster across spacetime. An enormous gravity field may encircle the circular aperture that would serve as the entry to a wormhole. Taking this route will take you over the bridge to a place that may be light years distant. Wormhole stability is one of the key issues. Exotic stuff with a negative energy density would be necessary for them to stay open, according to theoretical theories. A wormhole couldn't collapse fast enough for anything to pass through if these materials weren't there. The characteristics of undiscovered exotic matter would be out of the ordinary. It might provide the negative energy required to resist the wormhole's inherent inclination to shut. It is quite difficult to find or make such material. In theory, time travel and travel faster than light are both possible via wormholes. The possibility of time dilation arises when one wormhole mouth is subjected to a strong gravitational field or propelled to near light speed. A potential time gap might be caused by this. In science fiction, the idea of wormholes that can be traversed has become rather popular. Many works of fiction portray them as portals to other realms or universes, enthralling viewers and readers. The intricate mechanics are often simplified in these fictional depictions. Extreme gravitational forces would probably be involved in actually traveling through a wormhole. Travelers might face serious risks from these pressures, which could cause spaghettification, excessive stretching and compression. Additional information on wormholes may be uncovered by studying quantum gravity. New insights on wormholes may be forthcoming from theoretical frameworks that seek to unite quantum mechanics with general relativity, such as loop quantum gravity and string theory. At this time, there is no experimental proof of wormholes. Finding them would need seeing impacts that are not accounted for by any other occurrences. In theoretical and observational astrophysics, this quest remains a significant focus. The ability to stabilize and travel via wormholes would completely alter the face of space travel. A faraway galaxy might be reached much more quickly with their help than with current rocket technologies. Our horizons might open out to the cosmos as a result of this discovery. Understanding the basic basis of reality is another area where wormhole research has ramifications. It raises fresh concerns about the organization of the cosmos by testing our ideas of space, time, and causation. The concept of wormholes still fascinates scientists, despite all the obstacles. As a result, it inspires fresh ideas on the potential of space travel and challenges the limits of theoretical physics. As we continue our journey into space, the intriguing prospect of Einstein-Rosen bridges looms large. They inspire us to explore the unknown via science fiction and real science, bringing the two worlds together. Wormholes are potential holes in the fabric of space-time that might allow us to travel to other parts of the universe far faster than we could with current technology. Spacecraft might travel immense cosmic distances in a fraction of the time it takes because to wormholes, which distort space-time and effectively minimize the distance between two sites. The premise that space-time may be bent or distorted by large bodies is fundamental to the wormhole theory. A tunnel-like structure made of modified space-time might link two geographically distinct areas of space, allowing a direct route that does not include the intervening space. A wormhole can only facilitate speedier travel if it is both stable and passable. To maintain the tunnel's openness, exotic matter with a negative energy density must be present. Such material would serve as a brake on the wormhole's inherent desire to close, making it a more solid conduit. The two ends, or mouths, of a wormhole that may be passed through are joined by a neck. Compared to the typical gap between two mouths, the distance via the neck may be much less. Regardless of the distance in the exterior cosmos, stepping inside one mouth would provide instantaneous transit to the other. According to theoretical models, time dilation effects may materialize when a wormhole is positioned close to a huge object, such a black hole, or when it is propelled to almost the speed of light. Since time would flow differently at each end of the wormhole, this might pave the way for speedier travel as well as time travel in general. Intense gravity forces near wormhole mouths would need accurate navigation for wormhole travel. Protecting the spaceship and its inhabitants from such harsh circumstances would need advanced propulsion and shielding technologies. The possibility of wormholes facilitating interplanetary travel is really intriguing. Stable wormholes allow us to travel much faster than we could with current methods of propulsion, which would take thousands of years. We may be able to colonize faraway star systems in our lifetimes if this holds. Wormholes have the potential to provide instantaneous communication over enormous distances, in addition to interstellar travel. Wormholes have the potential to completely alter the way we interact across space and time by eliminating the temporal lag that comes with light-speed transmission. Building and maintaining a wormhole consumes vast amounts of energy. It would need energy on a scale similar to that of whole stars, according to theoretical simulations. To tap into that kind of energy would require technological leaps forward in energy generation and storage that are now out of our league. Ongoing study in theoretical physics is driven by the potential advantages of wormhole travel, notwithstanding the limitations. To learn more about the potential for wormholes to be built and used for practical travel, scientists are investigating several models and mathematical frameworks. Wormholes, if man-made, would allow us to traverse enormous distances, therefore expanding our knowledge of the cosmos. We could visit other planets, study faraway phenomena up close, and maybe even meet alien civilizations if we could cut travel times in half. A great deal of science and technology is affected by this. By enabling humans to travel via wormholes, we may explore previously inaccessible regions of the cosmos and perform experiments and observations there. Wormhole transit raises philosophical questions about the nature of space, time, and causation. New thoughts and hypotheses on the basic structure of existence are prompted by the issues it raises regarding the nature of reality and our role in the cosmos. The eternal human desire to expand the limits of possibility is reflected in the development of wormhole technology. Inspiring us to probe the cosmos and the outer regions of our imagination, it stands as a meeting point for science fiction and scientific investigation. Although wormhole travel has not yet been proven, the theoretical work done by physicists lays the framework for such discoveries. Our capacity to travel at the speed of light and our comprehension of the universe more generally may be revolutionized if we persist in our pursuit of knowledge and develop our technology to that point. Stability is a big concern when it comes to wormhole travel. Wormholes have a high potential for collapsing before anything can go through them due to their intrinsic instability. Exotic matter. Having a negative energy density is required to keep a wormhole open for a sufficient amount of time to allow transit. Near a wormhole's opening, there are tremendous gravitational forces, which pose another major danger. An effect called spaghettification may occur if these pressures were to compress and stretch items. Everything trying to pass through a wormhole is in grave danger from this tremendous gravitational pull. We don't have the technology to find or create the unusual stuff that would stabilize a wormhole at this time. As a hypothetical substance, exotic matter has characteristics that are not found in ordinary matter. A big obstacle is that this content isn't there. Making a stable wormhole wouldn't solve the problem of how to go through it. Wormholes may transport you to dangerous and unexpected places. It would need cutting-edge technology and exact control to get it through these circumstances safely. Wormhole mouths being geographically far apart is another possible problem. The technological difficulty of aligning and synchronizing these openings is tremendous, requiring control on an astronomical scale and exact measurements. Another major obstacle is the amount of energy needed to create and sustain a wormhole. The energy required to create a wormhole may be enormous, perhaps more than what our planet can already generate. This restriction is a major roadblock to actual application. Wormholes, according to theoretical models, might allow us to travel across time, which has certain dangers and paradoxes of its own. Cases in which cause and effect are inverted might result from time travel-induced causality violations. The unexpected and perhaps harmful outcomes of these paradoxes are not out of the question. Another thing to think about is radiation exposure. Extreme radiation might be emitted by the high-energy environment close to a wormhole. We need strong safeguards to prevent this radiation from harming or destroying any equipment or passengers that happen to be passing through. Additionally, unexpected physical events might be encountered. If wormholes really do exist, they might lead to other universes where strange physical rules and circumstances govern space and time. Another element of peril to wormhole travel is these unknowns. Another thing to think about is security threats. Wormholes might be used for evil if they enable very instantaneous transit across great distances. To avoid abuse, it is critical to secure and regulate wormhole travel. Nobody knows how the human body reacts when a wormhole is entered or left. We don't yet know how a human body will react to the wormhole's intense environment. Investigation of these consequences is crucial prior to contemplation of human missions. There may be ethical and legal concerns with wormholes as well. Could be thought of. There may be ethical and legal concerns with wormholes as well. Wars over space territory and resources may break out as a result of the capability to swiftly cross great distances. To control these emerging trends, global rules and accords are required. We must also think about the environmental effects on the other side of a wormhole. Developing and sustaining a wormhole has the potential to have unforeseen effects on systems in the vicinity by interfering with local spacetime. Responsible usage necessitates an understanding of these implications. Because wormholes are theoretical, there is a lot we don't understand about them. A lot of what we know now comes from computer simulations and mathematical models. To verify these ideas and comprehend their practical consequences, observation and experimentation in the real world are required. The advantages of wormhole travel might outweigh the dangers and difficulties. Major developments in the fields of physics, engineering, and technology are necessary to overcome these challenges. To fully understand wormholes and everything they can do, more investigation and study are required. Scientific investigations on wormholes at the moment are mostly theoretical. To investigate wormholes and everything they can do, physicists turn to general relativity equations. Wondering what circumstances may lead to the existence and stability of wormholes is the driving force behind these speculative investigations. The kinds of exotic stuff needed to maintain a wormhole open are the subject of ongoing research. To be found in nature, this strange substance would have to have a negative energy density. Theoretical physicists investigate potential uses and models for these kinds of materials. Wormhole research is not complete without the involvement of quantum mechanics. Wormhole stability may be enhanced by quantum phenomena, according to certain hypotheses. New insights may be forthcoming from the active research taking place at the confluence of general relativity and quantum mechanics. Research into wormholes makes use of sophisticated computer models and simulations. The formation, behavior, and interaction of wormholes with their surrounding spacetime may be investigated with the use of these instruments. These intricate processes may be studied in a virtual laboratory thanks to computational physics. Also, the possibility of wormholes in the cosmos that form spontaneously is being investigated. The study of observational astrophysics is dedicated to the search for extraterrestrial structures by analyzing cosmic occurrences and gravitational field anomalies. Nevertheless, conclusive proof has not been discovered so far. Our knowledge of wormholes has been enhanced by the theoretical contributions of physicists such as Kip Thorne. The criteria necessary for safe travel through these structures are investigated in Thorne's work on traversable wormholes. He has laid the groundwork for connecting theory with possible application via his study. Studying how wormholes and black holes are related is another field of concern. Wormholes may be produced during the formation of black holes or be connected to them, according to certain hypotheses. Learn more about wormholes and their properties by studying black holes. The function of wormholes in the cosmos is another area of interest for scientists. If wormholes do in fact exist, they might alter our view of the structure and development of the cosmos by providing faster routes across it. The consequences for cosmology might be enormous if this holds. Researchers in experimental physics are trying to find wormholes in a roundabout way. As part of this process, we look for high-energy cosmic events or anomalous gravitational effects that defy explanation by existing theories. These findings may provide a clue as to whether or not wormholes exist. Wormhole research relies heavily on interdisciplinary cooperation. Collaboratively, a astronomers, engineers, and physicists investigate theoretical models and their real-world applications. Through working together, we may get a better knowledge from many angles. Developing man-made wormholes is an area of investigation for some scientists. A high level of theoretical physics and ideas for future technologies are involved in this very hypothetical work. Finding out the steps required to build a wormhole in a lab setting is the main objective. The study of quantum gravity is closely connected to wormhole research. The nature of wormholes can be better understood if we can learn how quantum gravity operates. By bringing together quantum physics and general relativity, this field of study hopes to provide a more complete picture of the cosmos. Wormholes are another topic that touches on string theory. The presence of more than one dimension is predicted by string theory, which postulates that basic particles are strings with one dimension. If our reality is multidimensional, wormholes may be an inevitable part of it. Theoretically grounded as it is, contemporary research is expanding our horizons. We are getting closer to knowing whether wormholes exist and how to use them with each new theoretical model or advancement. Wormhole theory is at the forefront of current theoretical physics. Even though there are still a lot of unsolved mysteries, scientists are still very interested in learning more about these intriguing formations and the cosmos as a whole. Physicist Miguel Alcubierre put up the idea of the Alcubierre drive in 1994 as a potential means of traveling at speeds greater than the speed of light. The concept revolves on the idea of bending spacetime to get speeds beyond the speed of light. A spaceship may use the drive to its advantage by enclosing itself in a warp bubble. Behind the spaceship, this bubble enlarges spacetime, while in front of it, it compresses. The spaceship would stay put within the sphere while it traveled across space. Using this approach hypothetically, it is possible to travel at speeds greater than light without breaking any physical restrictions. Bypassing the relativistic speed limit is possible since the spacecraft is not traveling at a speed greater than light. The Alcubierre drive relies on exotic matter, which is one of its primary properties. This strange, unfathomable stuff would have to have a negative energy density. The warp bubble cannot be formed or maintained without negative energy. An enormous amount of energy is needed by the Alcubierre drive. The first estimates put the energy requirements of the drive higher than the mass of the visible universe. These requirements were initially quite high, but have since been decreased by later modifications. Crucial is the warp bubble's form. It can't be perfectly balanced if it can't go ahead. The spacetime is compressed in front and expanded in the back, causing the bubble and spaceship to go ahead. Those inside the warp bubble would not feel any acceleration. Protected from the tremendous pressures often experienced during high-speed flight, they would be in a state of free fall. Because of this, the Alcubierre drive is considered to be human-safe. Specifically, the warp drives seen in Star Trek and other science fiction series served as inspiration for the Alcubierre drive. The concept appeals to our imaginations, even if the underlying science is considerably more complicated. Managing the warp bubble is a difficult task for the Alcubierre drive. To guide and direct the spaceship, one would have to precisely manipulate spacetime. Our present technical capacities do not provide such a degree of control. Researchers in theoretical physics are looking at potential sources of negative energy that may power the motor. Possible causes are being investigated, such as the Casimir phenomenon, which generates negative energy between plates that are tightly spaced. Research on ways to reduce energy use is another active subject. In order to lower the energy need, some have proposed employing combinations of many warp bubbles or changing the bubble's shape. New speculative directions in physics have been opened up by the Alcubierre drive. It makes us re-evaluate our assumptions about spacetime and inspires new ways of thinking about space travel. Skeptics argue that the enormous practical hurdles make the drive theoretically impossible. For the time being, it may be impossible to create, manipulate, and control a warp bubble. Investigating the Alcubierre drive also has consequences for comprehending the essence of spacetime. It provides new understanding of the universe's inner workings by expanding the frontiers of quantum physics and general relativity. The Alcubierre drive, with all its problems, is an intriguing point where theoretical physics and science fiction converge. It personifies humanity's desire to reach the stars via discovery and the dogged pursuit of information. A key tenet of the Alcubierre drive and similar ideas of faster-than-light travel is the manipulation of space-time. Changing the fabric of space-time to accomplish goals like speedier travel is what it entails. One way to manipulate space and time is via warp bubbles. An area of space-time enclosed by one of these bubbles may experience relativistic velocity, meaning it can outpace the speed of light in comparison to the surrounding space. Relativity has no impact on the spacecraft inside the bubble since it is contained in its local space-time frame. A careful manipulation of space-time is required to create a warp bubble. For the bubble to work, space-time must be compressed at its front and expanded at its rear. A difference is thereby generated, and the bubble is propelled forward by this. To create and sustain a warp bubble, exotic materials with a negative energy density is essential. The positive energy would normally force the bubble to burst, but this negative energy prevents it from happening. The warp bubble would be invalid in the absence of exotic stuff. General relativity, which Einstein developed, provides the theoretical basis for warp bubbles. In general relativity, these equations state how mass and energy are described by Einstein. The effect of mass and energy on space-time curvature is described by these equations. A warp bubble is defined as the result of solving these equations under certain circumstances. Such a massive scale of space-time manipulation requires tremendous energy, and first calculation put the required energy at a level where it could be used to transform the mass of the whole cosmos. These standards have been refined and are now lower, but they are still too high. It is quite difficult to control a warp bubble. To control and guide the bubble, one must precisely alter the space-time curvature. Unanticipated or disastrous outcomes could result from careless manipulation. Additionally, there is the matter of the warp bubble's stability. Constant negative energy input is required to keep the bubble from popping or leaking. For risk-free spaceflight, this steadiness is crucial. Everyone on board the spaceship would feel as if time stood still inside the warp bubble. They might escape relativistic effects like time dilation by staying within the bubble, which would keep them safe from the outer world's very high velocity. The possibility of fast interstellar travel is presented by warp bubbles. Warp bubbles might allow us to travel to faraway stars in our lifetimes by avoiding the relativistic speed restriction. Our approach to space exploration might be completely transformed by this. According to theoretical research, the warp bubble's stability and energy consumption may be influenced by its size and form. Although the notion is still much above our present technical capabilities, optimizing these characteristics might make it more viable. Implications for our knowledge of physics also arise from space-time manipulation via warp bubbles. It questions our current understanding of the cosmos and forces us to reevaluate our long-held beliefs. Novel insights and progress in the field of basic physics may emerge from such investigations. The idea of warp bubbles encourages creative problem-solving, even if it is very theoretical. It challenges scientists to think outside the box and challenge accepted norms. Progress in every scientific discipline requires this frame of mind. Warp bubbles and space-time manipulation research is still in its speculative early stages. Practical implementation and experimental verification are far-off objectives, but further research may lead to better understandings and better technology in the future. An example of humanity's insatiable curiosity and need for new knowledge is the quest to comprehend and maybe control space-time. It embodies the spirit of exploration and symbolizes our ambition to expand the boundaries of possibility. Warp bubbles are very energy-intensive to create and maintain. The amount of energy required would be enough to transform the mass of the whole universe, according to early estimations. For real-world application, this is a huge hurdle. The predicted energy needs have been lowered due to improvements in the theoretical models, but they are still quite high. Despite these cuts, the amount of energy required is still far more than what our present technology is capable of generating or using. Exotic matter is an essential part of the warp bubble idea. The creation and stabilization of the bubble depend on the exotic matter's negative energy density, which is theorized. This negative energy prevents the bubble from collapsing, which is its inherent propensity. We have not found or manufactured exotic stuff in the lab. The qualities are still in the realm of theory, and the discovery or synthesis of such stuff remains a formidable challenge. The quest for exotic matter is more tough since normal stuff does not have negative energy density. A number of processes that theoretical physicists have postulated have the ability to generate exotic matter. A process that falls within this category is the Casimir effect, which generates negative energy when two plates are very close together. The Casimir effect does generate some energy, but it's not nearly enough for a warp bubble to form. Creating negative energy by the use of quantum fields is an additional suggestion. Vacuum fluctuations, according to quantum field theory, might generate negative energy zones, but it's still pure speculation whether these oscillations can be controlled and used in a practical way. Exact manipulation of exotic matter distribution is also necessary for warp bubble production. The stability and proper operation of the bubble depend on this regulation. The technological hurdles of dealing with unusual materials on this scale are enormous. Producing enough energy to maintain a warp bubble would remain a formidable challenge, regardless of our ability to manufacture exotic matter. Nuclear power and chemical processes, two of the most common forms of energy today, are very inefficient. We would have to come up with whole new, very efficient energy sources. The possibility of antimatter as an extremely powerful energy source is being investigated by scientists. Even with the tremendous quantities of energy released by antimatter processes, a warp bubble may still be unable to contain it. Furthermore, there are unique difficulties associated with creating and storing massive amounts of antimatter. Another conceivable approach is to tap into dark energy, the enigmatic factor responsible for the universe's accelerating expansion. Nevertheless, our comprehension of dark energy is restricted, and we have a long way to go before we can control it in a practical way. The form and arrangement of the warp bubble also determine the energy needs of the warp drive. The idea becomes somewhat more practical according to certain simulations, which propose that specific forms may lessen the energy required. Nevertheless, these arrangements remain in a purely speculative state. Exotic matter and the energy required for warp bubbles are driving forces that are pushing the limits of current physics. It makes us rethink the building blocks of the cosmos, the forces and particles. In both theoretical and experimental physics, this study represents state-of-the-art work. Potentially far-reaching consequences may result from theoretical advances in this field. Understanding exotic matter and high-energy physics may not yet provide usable warp drives, but it may pave the way for innovations in other areas of research. Warp bubbles and travel at the speed of light remain a source of fascination for scientists and engineers, despite the difficulties they provide. We innovate and strive to expand the boundaries of what is possible because we dream of exploring faraway galaxies and stars. Achieving travel at the speed of light presents enormous hurdles, such as the need for vast amounts of energy and the pursuit of exotic materials. On the other hand, they highlight the significance of ongoing investigations as we strive to decipher and use the mysteries of the cosmos. Models of travel at speeds greater than the speed of light are based on complicated equations established from general relativity by Albert Einstein. Fundamental to comprehending ideas like wormholes and warp bubbles are these equations that define the way in which mass and energy distort space-time. These models rely on the Einstein field equation, among other things. This formula describes the relationship between the energy and mass distribution within space-time and its curvature. Black holes and, in theory, wormholes may be described by solutions to this equation under certain circumstances. The Alcubierre drive may be solved by using a certain measure that generates a warp bubble. By adjusting the space-time interval, the Alcubierre metric makes it possible for a localized area of space to travel at the speed of light in comparison to an external observer. To do this, we must modify Einstein's equations by adjusting the parts of the metric tensor. Another important part is the energy-momentum tensor. The density and flow of momentum and energy in spacetime are represented by it. An unusual matter component with a negative energy density would be required for the energy-momentum tensor to encompass a warp bubble. A well-tuned stress-energy tensor is required for the maintenance of a warp bubble. With the help of this tensor, we can see how pressure and stress affect the movement and distribution of momentum and energy. Precise control over these parameters is required to provide uniformity and stability in the warp bubble. Wormhole geometry is also investigated in mathematical models. Connecting two distinct locations in spacetime, the Einstein-Rosen bridge, also known as a traversable wormhole, requires a particular solution to the Einstein field equations. In order to maintain the wormhole's aperture open, these remedies usually include unusual substances. One kind of wormhole that may be traversed is the Morris-Thorne wormhole. A description of these wormholes, including the requirements for their stability and traversability, may be found in the Morris-Thorne metric. Making sure the wormhole neck doesn't fall is part of this. These models often use quantum field theory to investigate the impact of quantum fluctuations on spacetime. As an example, the Casimir effect demonstrates that quantum fields are capable of producing negative energy. The possible function of this phenomenon in the formation or stabilization of warp bubbles and wormholes is the reason for its study. These phenomena are governed by very nonlinear equations that need sophisticated mathematical methods for solution. It is common practice to investigate possible solutions and behaviors under different scenarios by use of numerical simulations and computer models. Further difficulties arise from the need to conserve energy and the second law of thermodynamics. Every theoretical model has to take these basic concepts into consideration. The development of workable ideas depends on avoiding violations of these principles in energy needs. String theory and loop quantum gravity are two examples of quantum gravity theories that attempt to bridge the gap between quantum mechanics and general relativity. These hypotheses suggest extra dimensions and basic particles that may affect the behavior of spacetime at very microscopic sizes. They may provide light on what has to be in place for travel at the speed of light to be possible. Spacetime shortcuts, similar to wormholes, may be possible in string theory due to the geometry of additional dimensions. The form and features of these additional dimensions are described by these models using complicated mathematical structures called Calabi-Yau manifolds. In contrast, loop quantum gravity suggests a distinct structure at the Planck scale in an effort to quantify spacetime itself. According to this hypothesis, new ways of manipulating spacetime may be possible if spacetime has a granular structure. The mathematical precision of these models lays the groundwork for investigating the physical viability of travel at the speed of light. Building these theoretical frameworks keeps expanding our knowledge, even if experimental verification is still a long way off. To keep improving these models, mathematics and computing approaches must continue to progress. We can get closer to knowing the actual possibilities of faster-than-light travel as our methodologies and instruments become better at exploring these theoretical landscapes. The revolutionary and expansive possibilities of travel at the speed of light are endless. Exploration of space between stars is one of the most fascinating prospects. New horizons for exploration and colonization may be unlocked if humans were able to use this technology to reach other star systems in an acceptable amount of time. Inside our own solar system, fast transit is another important use. Humans may colonize Mars, Jupiter's moons, and other celestial worlds with greater ease and sustainability if faster-than-light travel significantly reduced journey periods between planets. The scientific community would reap tremendous benefits. By collecting data in real time from faraway celestial events, our knowledge of the cosmos would be greatly enhanced by faster-than-light travel. Scientific fields like cosmology, physics, and others may find new answers as a result of this. Another possible use is communication that is faster than light. We could totally change the game when it came to sharing knowledge and coordinating cosmic scale operations if information could flow instantly over enormous distances. Intergalactic diplomacy and interstellar exploration might be facilitated by this. There may be groundbreaking developments in medical and humanitarian missions as well. Whether on Earth or in space colonies, the capacity to swiftly move supplies, troops, and relief over great distances might revolutionize crisis responses. Having said that, you should think about the substantial constraints. The existing theoretical and technical barrier is the main restriction. Our existing knowledge and skills do not allow us to meet the energy needs or the demands for exotic stuff. Mechanisms for traveling faster than light also have the potential drawback of being unstable. As things stand, wormholes and warp bubbles might collapse or act in an unexpected way, putting missions and passengers at peril. It is equally important to consider the moral consequences of traveling faster than light. This technology has a lot of room for abuse or exploitation. Thus, there has to be some kind of worldwide agreement or legislation to keep it in a responsible and equitable hands. A further worry is the effect on the environment. The environment in space and maybe on planets might be irreparably damaged if such a massive manipulation of space-time were to occur. To lessen the impact of any negative side effects, thorough research is required. We must not overlook economic considerations. It would be very expensive to design, launch, and maintain devices that could travel faster than light. This might worsen global inequality by limiting access to rich states or organizations. It is also crucial to think about the passengers' social and psychological impacts. Potentially isolating faraway space colonies and the effects of such rapid travel on human health and social dynamics are substantial concerns. Another restriction is the difficulty of navigating. Predicting and controlling travel routes via space-time manipulation accurately is crucial for avoiding disastrous mistakes. Ensuring safe and accurate navigation will need advanced technology and algorithms. It is also important to think about how this may affect already in place systems and technology. Current space travel systems, satellite communications, and even terrestrial technology might be irrevocably disrupted by the arrival of faster-than-light travel. The increasing capacity to swiftly access and claim faraway lands might lead to territorial conflicts and legal battles. Because of the new complexity that faster-than-light technologies bring, international agreements and regulations will have to change. There are still theoretical constraints. Many of the existing theories about travel at speeds greater than light rely on theories that have not been confirmed. These models could need major updates or be rendered useless if our knowledge of basic forces and particles advances. To sum up, faster-than-light travel has very exciting possibilities that might change the way we live and explore the world. But it also has formidable obstacles and constraints. It will need extraordinary scientific and technological breakthroughs as well as worldwide collaboration to overcome these obstacles. Particles with a kinetic energy greater than that of light are hypothetically known as tachyons. From the solutions to the special relativity equations, the notion of tachyons arises. In 1967, physicist Gerald Feinberg first put them forth. The Greek word tachys, meaning quick, is the origin of the English word tachyon. Assuming their existence, these particles would perpetually outpace the speed of light. In contrast to typical particles, tachyons would actually accelerate as their energy is dissipated. The imaginary mass of a tachyon is an important property. A particle's velocity exceeding the speed of light is a consequence of its imaginary mass according to the special relativity equations. Because of this, tachyons are unique among known particles that have a positive actual mass. When compared to more common particles, tachyons might act in an unexpected way. They accelerate when they deplete their energy stores, for example. Normally, as particles lose energy, their speeds decrease. However, in this case, the reverse is true. We may need to rethink our notion of causation in light of the potential existence of tachyons. In principle, tachyons, which travel at the speed of light, may go through time in reverse. This might lead to paradoxes since it opens the door to the idea that consequences could occur before their causes. It is not always the case that the rules of special relativity are violated by the putative presence of tachyons. Rather, they are part of an alternative framework that modifies the conventional laws of energy-mass connections and causation. Their unique properties make them an intriguing area of research for theoretical physicists. Experimental detection of tachyons has not been made. Their very existence is still up for debate. Physicists have come up with a plethora of experiments to look for tachyons, but none of them have succeeded in confirming their existence. It is possible that tachyons interact weakly with ordinary matter if they really exist. Their poor contact may render them very evasive to existing detection technologies. The search for these enigmatic particles has scientists investigating novel approaches and technology. For quite some time, tachyons have captivated science fiction writers. They provide communication or movement at speeds greater than light, and often make an appearance as a story device. Although creative, these fictional depictions often oversimplify the intricate scientific concept of tachyons. Tachyons may manifest as system instabilities in the context of quantum field theory. These aren't actual particles, but they do suggest a possible more stable condition for the system. Possible phase transitions in quantum fields may be better understood with the use of this theoretical notion. Complex numbers are the building blocks of tachyon mathematics. Their fictitious mass adds another dimension to the motion equations. Though they are compatible with the theory, these mathematical features cast doubt on our long-held assumptions about the physical world. It has been postulated that tachyons, should they exist, may produce Cherenkov radiation when contained in a vacuum. This is similar to the radiation that is released when particles in a medium travel faster than light. This is similar to the radiation that is released when particles in a medium, such as water, travel faster than light. Tachyons may be detectable by the use of such radiation. The string theory is likewise affected by tachyons. Tachyons stand for unstable states that strings may enter in some formulations of string theory. The idea of symmetry breaking, which may be brought about by these states, is crucial to comprehending the basic forces at work in the universe. The study of tachyons, however hypothetical, advances theoretical physics. They force physicists to reevaluate long-held assumptions about particle behavior and the cosmos, opening the door to novel ideas. New developments in theoretical and experimental physics are being propelled by the insatiable curiosity of tachyons, regardless of their existence. It piques the interest of both scientists and science fiction fans, while also leading to new lines of inquiry and bettering our understanding of the cosmos. Even before tachyons were formally introduced, the idea of particles flying faster than light was present. In the early 1900s, as scientists tried to make sense of Einstein's special relativity and its consequences, they conjured up ideas of hypothetical particles that might travel faster than light. The concept of particles traveling faster than light was investigated by Belanjuk, Deshpande, and Sudarshan in 1962. In order to set the stage for further conversations, they released a paper outlining the theoretical characteristics of these particles. Their contributions were critical to the concept's acceptance in standard theoretical physics. In 1967, Gerald Feinberg first used the word tachyon. His theory in the essay Possibility of Faster-Than-Light Particles was that hypothetical particles with an arbitrary mass may theoretically surpass the speed of light. These hypothetical particles can be understood mathematically thanks to Feinberg's work. In his suggestion, Feinberg relied on the special relativity equations. Using particles with an imaginary mass, he demonstrated that relativity may be violated if their speeds were to surpass the speed of light. In the realm of physics, this concept generated a great deal of attention and discussion. Interest in tachyons increased in the 1970s. They were investigated by physicists for possible consequences on spacetime structure and causation. The possible experimental signs of tachyons and their interactions with regular matter were the subjects of certain researchers' investigations. The evolution of quantum field theory was also impacted by tachyons. Theoretical physicists pondered the possibility that tachyons may manifest as quantum field instabilities. Because of this, we now know how fields behave and what circumstances could trigger phase transitions. Many researchers were interested in tachyons because of their possible ability to defy causality. Time travel via tachyons would allow for paradoxes in which consequences come before their causes. This feature of tachyons makes them an intriguing, albeit contentious area of research. Experimental searches for tachyons have shown no results, despite the interest in theory. There has been no conclusive proof of faster-than-light particles despite several attempts at detection. Tachyons' evasiveness is still a major obstacle. Additionally, tachyons have made it into the world of pop culture. Concepts including time travel, improved communication technology, and faster-than-light travel have been explored by science fiction authors and filmmakers using this idea. These creative applications have contributed to the idea's rising reputation. In string theory, tachyons stand for unstable states that might cause symmetries to break. This viewpoint has opened up new avenues of inquiry into the function of tachyons in theoretical physics, bridging their relationship to basic features of particle physics and cosmology. Periods of intensive theoretical investigation characterize the historical background of tachyons. The novelty of the notion has worn off a little, but it still makes people think of interesting things to investigate. As far as the search for new physical limits is concerned, tachyons will always stand as a metaphor. The discussion around tachyons has, throughout the years, brought attention to the relationship between theoretical predictions and their experimental confirmation. Because of the difficulty of detecting tachyons, new experimental methods are required to overcome the limitations of existing technology. Highlights the need for new experimental methods and the limitations of existing technologies. The study of tachyons has aided larger debates over spacetime as a whole. Although tachyons are still considered hypothetical, these debates have contributed to a better grasp of quantum physics and relativity. Research into tachyons has left an indelible mark on our continued pursuit of knowledge about phenomena that travel faster than light. Whether tachyons really exist, the theoretical models that were created to explain them have a lasting impact on contemporary physics. The tachyon narrative shows how science is always evolving. It demonstrates how theoretical predictions may motivate practical endeavors, and how even wild speculations can contribute to substantial progress in our knowledge of the cosmos. Because of their peculiar relativity-related characteristics, tachyons have the potential to travel faster than light. Tachyons are particles that defy relativity because they have an imagined mass rather than a real one, allowing them to outpace the speed of light. A particle's behavior changes depending on its imagined mass as compared to its true mass within the context of special relativity. The speed of a tachyon rises as its energy decreases. Typical particles, on the other hand, experience a significant slowing down when their energy is depleted. A tachyon's fictitious mass changes the energy-momentum connection. For tachyons, this connection means that their imaginary mass changes. It follows from this equation that tachyons, even at low energies, have velocities greater than the speed of light. That is why they are essentially superluminal. Their speed is certain to remain above the speed of light. From the time of their creation, tachyons have the potential to travel at the speed of light. To escape the infinite energy demand that ordinary particles encounter as they approach light speed, they would never move at or below light speed. Because of this essential distinction, tachyons are able to escape the standard particle limit of matter, which is the speed of light. The existence of tachyons would allow for the transmission of data over enormous distances in an instant. They may change the way we think about communication and causation if their speeds were superluminal, allowing us to transmit messages at the speed of light. Both real-life scientists and those who create science fiction are fascinated by this theoretical trait. The ability of tachyons to travel across time is an intriguing feature. They may conceivably reach their destination before they ever leave, thanks to their superluminal speeds. This property of time reversal opens up fascinating paradoxes and opportunities in the field of causation. A tachyon is a field having a negative mass squared, according to quantum field theory. The presence of these fields suggests that the system may be about to undergo a stable transition, since they are often linked to instabilities. This explanation sheds light on the potential role of tachyons in more general physical theories, which is useful for physicists. Despite tachyons' theoretical characteristics, discovering them is very difficult. They are challenging to examine using existing experimental approaches because to their unusual behavior and weak interaction with regular matter. Their confirmation would need state-of-the-art detectors and fresh methodologies. In high-energy cosmic events, tachyons may occur according to certain ideas. One possible way to detect tachyons is if these events create circumstances that allow them to be created. Indirect proof of tachyons is still being sought for by those who study cosmic events. Several theoretical disputes have arisen due to the possibility that tachyons might break the law of causality. Paradoxes in which an effect comes before its cause may be created if tachyons could go back in time. New understandings of time and causation are necessary to resolve these dilemmas. Some physicists have speculated that tachyons may only exist in certain cosmic settings. The fact that we have not seen them yet could be due to these limitations. Research into these circumstances may provide light on the possible locations and mechanisms of tachyons. Within the paradigm of special relativity, the mathematical models that describe tachyons are compatible. To better comprehend their characteristics and actions, these models serve as a foundation. But it's still quite difficult to make these mathematical ideas a reality in the actual world. The existence of tachyons, if confirmed, might provide light on the nature's most basic forces in a novel way. Their one-of-a-kind characteristics may provide light on hitherto unseen facets of spacetime and energy. Theoretical and experimental endeavors are motivated by this promise. Theories like wormholes and warp drives are also influenced by what we learn about tachyons. Many of these ideas are based on the same exotic matter and superluminal transport assumptions. These more general ideas may benefit from the knowledge acquired from tachyon research. New frontiers in current physics are being filled out by theoretical investigations of tachyons. The search for tachyons has sparked creative ideas and the creation of cutting-edge scientific tools, but their very existence is still up for debate. The peculiar features and speculative nature of tachyons make their detection very difficult. They are invisible to conventional detectors that look for particles moving at a slower rate than light because they move at such a high speed. One major obstacle is the poor interaction of tachyons with ordinary matter. If tachyons do in fact exist, they may not interact with regular particles in a manner that would lead to audible signals. Because of this, it is difficult to see them with current technologies. In a vacuum, tachyons, according to theoretical models, might release Cherenkov radiation, the same way that particles in a medium like water release light when they're moving faster than light. However, there is a lack of experience and complexity in the design of studies to detect this kind of radiation in a controlled environment or in space. Making tachyons in a controlled environment is another obstacle. Particles having actual mass can be accelerated using the current generation of particle accelerators. An enormous challenge necessitating substantial progress in experimental physics is the creation of novel technologies for the production and study of particles with imagined mass. It is difficult to capture or measure tachyons even if they could be made. Because of their superluminal velocity, they might perhaps pass through detecting equipment in a moment, if not entirely undetected. We need new kinds of detectors that can pick up on these kinds of fast occurrences. Additional complexity is introduced by tachyons' possible reverse time travel ability. Our traditional view of time and causality is called into question if tachyons are able to go back in time. In order to detect them, we may need devices that can detect particles that arrive before the detecting event. In order to identify tachyons, unusual circumstances may be necessary. Extreme settings, such those close to black holes or during cosmic events with a lot of energy, may make them easier to see, according to some beliefs. It is very difficult to duplicate these circumstances on Earth, or to plan experiments to be conducted in space. The hunt for tachyons relies heavily on mathematical models and simulations. By using these models, we can better predict when and where tachyons may appear. On the other hand, their projections can only be trusted as far as the speculative theoretical frameworks they are based on are concerned. The use of tachyons in real-world scenarios, such communication at the speed of light, is far more intricate. In order to harness tachyons, one must be able to identify them and then regulate their production and behavior. Jobs that are much beyond what our technology can handle right now. The consequences of using tachyons are still a matter of theoretical contention. The potential for tachyons to enable instantaneous communication across great distances is intriguing. But this begs the issues of data transmission limitations, latency, and information security. When talking about tachyon use, philosophical and ethical questions also come up. Particularly in light of questions of free will and reality itself, the possibility of altering time and causality raises serious philosophical and moral concerns. Unanticipated results may emerge from studies of tachyons. Unknown dangers may result from tinkering with exotic particles and high-energy occurrences. It is crucial to have thorough safety protocols and ethical standards. In order to overcome these obstacles, it is essential that experts from different fields work together. To investigate tachyons thoroughly and determine their possible applications, physicists, engineers, and philosophers should collaborate on research into both the theory and practice of the phenomenon. New developments in both theoretical and experimental physics are propelled by the hunt for tachyons. Even if tachyons are elusive, each obstacle promotes the development of new technologies and approaches that contribute to the field of scientific inquiry as a whole. The limitations of our present scientific knowledge are shown by the difficulties in both detecting and using tachyons. Yet, they also provide a chance to learn more about the universe's underlying principles and expand our understanding of the world around us. The majority of tachyon study at the moment is theoretical, looking at the consequences and possibility of their existence within the context of contemporary physics. Physicists are trying to figure out how tachyons may fit in with the established rules of the cosmos by using complex mathematical models. Tachyons are very important in string theory, among other fields. In certain formulations of string theory, tachyons manifest as signs of system instability. Scientists may learn more about elementary particles and forces when these instabilities cause phase transitions. The function of tachyons is also investigated in quantum field theory. Within this framework, tachyons may be seen as imaginary mass fields that elucidate vacuum conditions and provide novel physical possibilities. Research like this helps hone the theories that attempt to explain the cosmos in its most fundamental form. The possible interactions between tachyons and black holes are the subject of some current study. It is possible that the impacts of particles traveling faster than light will be more noticeable under the very harsh circumstances seen in the vicinity of black holes. This study may provide circumstantial evidence for tachyons. CERN and other high-energy particle physics labs are still looking for strange occurrences that could indicate tachyons are out there. These investigations serve to enhance our knowledge and rule out some theoretical theories, even when no direct proof has been uncovered. Astrophysicists are looking for tachyon signals in cosmic rays and other space-based high-energy events. Highly energetic particles from space known as cosmic rays may interact in ways that might indicate the existence of particles with velocities greater than the speed of light. The potential for particle collisions to generate tachyons is another area of study. Researchers are looking for patterns or outliers in the data from these high-energy collisions that could indicate the presence of tachyons. Tachyon behavior under different settings may be predicted by developing theoretical models. By predicting potential locations and methods for detecting tachyons, these models aid in directing experimental searches. In addition, they lay up the groundwork for comprehending what their life entails. The idea of tachyon condensation is being investigated by a number of physicists. Some string theory and quantum field theory events may be explicable by this process, in which tachyons might condense into a lower energy state. It offers a possible way out of these theories' instability problems. The study of tachyons also extends to quantum entanglement. One possible explanation for this puzzling quantum event is the function that tachyons may play in the instantaneous coupling of entangled particles. Additionally, tachyons are being thought about in relation to dark energy. The fast expansion of the universe may be better understood by examining the characteristics of tachyons, according to certain hypotheses. The fields of particle physics and cosmology may be able to meet thanks to this study. Research into tachyons keeps pushing theoretical boundaries, even in the absence of experimental proof. The nature of the cosmos as a whole is becoming better understood with each new model and theory, even if tachyons are still a mystery. Theoretical and experimental physicists must work together. Through collaboration, they may develop tests that evaluate tachyon model predictions, enhancing our knowledge of high-energy physics and possible particles traveling faster than light. New technological advancements are also spurred on by the hunt for tachyons. In an effort to discover these hypothetical particles, high-energy particle accelerators, advanced detectors, and complex data processing techniques are all being improved. In the grand scheme of things, tachyon-related theories and research constitute state-of-the-art physics. They make us question the very foundations of reality, test the limits of our knowledge, and test our comprehension. A subfield of theoretical physics known as quantum mechanics studies how subatomic particles act. A subfield of theoretical physics known as quantum mechanics studies how subatomic particles act. Particles like electrons and photons behave and interact in strange and contradictory ways, which are described in it. The duality of waves and particles is fundamental to quantum physics. According to this theory, particles may display characteristics more often associated with waves as well as particles. One example is the fact that light may appear as either a wave or a stream of individual particles called photons. The uncertainty principle is a fundamental idea in the field of quantum mechanics. The uncertainty principle, first put out by Werner Heisenberg, asserts that precise, simultaneous measurements of certain pairs of physical parameters, such as location and momentum, are not possible. The quantum universe is characterized by this basic uncertainty. The concept of quantization is also introduced by quantum mechanics. Distinct, rather than continuous, energy levels exist in atoms and other systems. This indicates that particles may only exist in discrete energy levels, and that quantized quantities of energy are required for transitions between these states. Superposition is another basic idea. The measurement process allows quantum particles to occupy several states simultaneously. One classic thought experiment that exemplifies this notion is Schrödinger's cat, in which a cat is both alive and dead until someone watches it. A phenomenon known as quantum entanglement occurs when two or more particles get so entangled that their states are immediately affected by each other, regardless of how far apart they are. Our conventional concept of locality is challenged by this eerie activity at a distance, as Einstein put it. The fact that particles behave like waves causes quantum tunneling. It opens up previously unbridgeable energy gaps in classical physics, allowing particles to move freely. This happens because there is a non-zero chance that the particle will be on the opposite side of the barrier, since its wave function extends across it. Many technological and natural processes rely on tunneling. The sun's energy allows protons to overcome their intrinsically strong forces and fuse together, a process known as nuclear fusion. This mechanism enables life on Earth by generating energy that powers the sun and other stars. Electronic gadgets such as quantum computers and tunnel diodes rely on quantum tunneling to function. By taking use of tunneling, these devices are able to perform operations at high speeds and unlock computing powers that were previously unimaginable. In quantum tunneling theory, the particle's interaction with a possible barrier is described by the Schrödinger equation, which must be solved mathematically. According to the answers, the particle's energy and the dimensions of the barrier determine the likelihood that it will be able to tunnel through the barrier. Radiation decay is not the only process that involves quantum tunneling. Degradation into more stable forms may be facilitated by the emission of particles by certain unstable nuclei. Even though nuclear forces may create a barrier, these particles are able to tunnel out of the nucleus. The basic mechanisms of the quantum universe may be better understood with knowledge of tunneling. It throws a wrench into our traditional understanding of how the world works and sheds light on the probabilistic character of quantum physics, which states that results are not predetermined, but rather characterized by odds. From cosmology to chemistry, quantum mechanics and tunneling have far-reaching consequences. Atomic and molecular behavior, star formation, and the laws of the cosmos may all be better understood with their aid. New occurrences and cutting-edge technology are being revealed by researchers as they delve further into quantum physics. Tunneling and other quantum processes are still a mystery, but they hold great potential for expanding our knowledge of the universe and radically altering many different businesses. The intriguing and peculiar quantum world is brought to light via the fundamentals of quantum mechanics and tunneling. Their findings both challenge and broaden our understanding of reality by revealing a cosmos that functions very differently from the macroscopic world we encounter on a daily basis. As a result of quantum mechanical principles, particles are able to tunnel past obstacles. Since they are wave-like, quantum particles are able to traverse energy barriers, in contrast to classical particles, which are severely limited by them. A particle's location, momentum, and quantum state are all described by its wave function. The wave function of a quantum particle does not halt suddenly when it hits a barrier. Rather, it progressively loses amplitude as it passes through the barrier. Within the barrier, the wave function does not completely converge to zero, but it does decrease. In other words, the likelihood of finding the particle on the other side of the barrier is limited. The particle's energy, the breadth and height of the barrier, and the probability of tunneling are all factors to consider. Think about a possible obstacle that a particle has to overcome to grasp this better. Particles cannot pass a classical barrier if their energy is smaller than its height. The non-zero wave function within the barrier, however, leaves the door open quantum mechanically for the particle to tunnel through. This effect may be expressed mathematically by finding the particle's wave function in the presence of the potential barrier and solving the Schrödinger equation. The wave function exhibits exponential decline within the barrier as shown by the solutions, but reemerges on the other side, suggesting tunneling. If the barrier is thinner or the particle's energy is near the height of the barrier, the likelihood of tunneling is greater. On the other hand, the tunneling probability is drastically reduced when barriers are thicker or much greater in relation to the particle's energy. The effects of quantum tunneling are tangible, rather than only theoretical. For instance, tunnel diodes and other electronic components may conduct current thanks to semiconductors, which enable electrons to pass through energy barriers between various materials. The process of alpha decay is explained by tunneling in nuclear physics. By passing past the nuclear potential barrier, an alpha particle in a nucleus is able to escape and cause radioactive decay. Many radioactive elements would have far more stability if tunneling did not occur. Additionally, quantum computing relies heavily on the idea of tunneling. Qubits, short for quantum bits, are able to do calculations at the speed of light because they use tunneling to go between states very rapidly. There are biological processes in which tunneling is involved. As an example, enzymes often use quantum tunneling to accelerate biological processes compared to what could be achieved using just classical principles. Responses that are far quicker than what could be achieved using just classical methods. The scanning tunneling microscope, STM, which employs tunneling to capture atomic-level images of surfaces, is another intriguing use. In order to produce very detailed pictures, scanning tunneling microscopy, STM, monitors the tunneling current between a pointed metal probe and the surface under investigation. The quantum realm is non-intuitive, as quantum tunneling shows. Our classical knowledge of impassable boundaries does not hold true at the quantum scale since particles may evade classical limitations. Quantum physics is shown to be probabilistic by this phenomena. Tunneling is a famous example of the probabilistic occurrences predicted by quantum physics, as opposed to classical mechanics, which predicts certain results. Our knowledge of quantum physics and the development of new technologies are both boosted by ongoing research into tunneling. More and more uses and consequences of quantum tunneling will certainly be revealed as our tools and approaches become more advanced. New scientific and technological opportunities arise when we learn how particles tunnel past walls, which goes against our conventional intuitions. It demonstrates the allure and mystique of quantum physics while unveiling a cosmos teeming with shocking and paradoxical actions. The future of faster-than-light travel is profoundly and hypothetically affected by quantum tunneling. This finding provides a clue that particles may escape the traditional bounds of energy barriers, which raises questions about the limits of what we can currently know about the physical universe. The subject of the quantum realm's speed constraints becomes more pressing in light of the possibility that particles might instantly tunnel through boundaries. It seems like tunneling can go around the speed of light, which contradicts the conventional wisdom that nothing can move faster than light. Coming up with new forms of propulsion is one possible consequence. It is now unthinkable that spacecraft might travel across space at superluminal speeds, but this may change if we can control tunneling effects on a macroscopic scale. Additionally, tunneling hints for novel ways of communicating. Overcoming the restrictions of the speed of light would enable instantaneous communication over enormous distances if information could be conveyed via quantum tunneling. Finding better ways to create and stabilize wormholes or warp bubbles may be possible with further research on tunneling effects in various materials and settings. Potentially better understood by quantum tunneling research are these theoretical constructions that depend on exotic matter and energy conditions. The possibilities are further expanded by quantum entanglement, which is strongly connected to tunneling. No matter how far apart they are, entangled particles may have an immediate impact on one another. This finding suggests potential processes that might enable interactions that occur at the speed of light. From the quantum level to the macroscopic level, researchers are investigating the possibility of scaling up tunneling. A major hurdle on the road to practical applications, this requires comprehending and regulating quantum coherence across longer distances and timescales. Our knowledge of space-time might be enhanced by theoretical models that include tunneling. Possibilities for faster-than-light travel that do not contradict relativity may be revealed by these models, which may shed light on new features of the structure of the universe. Our knowledge of event horizons and black holes may also be affected by quantum tunneling. Particles may be able to provide light on the nature of these mysterious phenomena and put an end to several paradoxes related to information loss if they can escape from black holes by tunneling. Potentially new particles or forces could be uncovered if experimental progress in quantum tunneling is sustained. The Alcubierre drive and traversable wormholes are proposals for faster-than-light travel. These findings potentially provide the exotic matter or negative energy required for these ideas. This has far-reaching consequences for how we conceptualize causation. Hyperspace travel has the potential to create temporal paradoxes in which the normal flow of events is inverted. The probabilistic character of quantum mechanics raises the possibility that it may provide answers to these dilemmas and bring them into harmony with the rules of physics. Another potential new energy source is quantum tunneling. The ability to effectively manage tunneling has the potential to unlock hitherto untapped energy levels, which might lead to a paradigm shift in power production and propulsion technology. New forms of transportation may emerge as a result of efforts to alter spacetime via tunneling effects. New kinds of teleportation or instantaneous travel inside confined zones could also be possible using these approaches, in addition to faster-than-light travel. Collaboration across disciplines is essential for the ongoing investigation of quantum tunneling and its potential applications in space travel at the speed of light. Cooperation between theoretical thinkers and doers in the fields of physics, engineering, and technology is essential for investigating various avenues of inquiry. Boundaries will keep expanding as our knowledge of quantum physics increases. This never-ending quest for knowledge is forcing us to reconsider the very boundaries of our cosmos, and the consequences of quantum tunneling for travel at the speed of light are just the tip of the iceberg. So yet, there has been no concrete proof of travel at speeds greater than the speed of light. The majority of ongoing investigations are aimed at determining the limits of special relativity and the cosmic speed limit, which is the speed of light. No experiment has shown superluminal transport as of yet, but quantum tunneling tests show that particles may act in ways that defy traditional ideas of velocity and obstacles. Particles like electrons and others may tunnel through potential barriers in these studies, emerging on the other side in an almost immediate manner. The scanning tunneling microscope is a well-known experiment that shows quantum tunneling in action. In order to generate atomic-level surface pictures, it employs the tunneling effect. This doesn't prove that particles can move faster than light, but it does show that they can act in unusual ways. Theoretical models are constantly being refined to investigate potential larger-scale applications of the concepts found in quantum tunneling. Complex mathematics and ideas from general relativity and quantum field theory are often used in these simulations. Quantum teleportation is one example of such a paradigm. Quantum teleportation enables the instantaneous transmission of quantum states between entangled particles, while it does not provide classical faster-than-light travel. Possible ways of communicating beyond the light speed of light are hinted at by this occurrence. Hypothetical particles like tachyons, which might theoretically move at the speed of light, are also being studied by researchers. Despite the lack of detections, tachyons provide new theoretical challenges and opportunities for advancements in particle physics. Experiments in high-energy physics, such as the Large Hadron Collider at CERN, look for outliers that might indicate the existence of new particles or forces. These may pave the way for findings that are pertinent to theories of transport at speeds faster than light. In theory, wormholes, also called Einstein-Rosen bridges, could link two places in space-time, enabling travel at the speed of light. To maintain the wormhole's stability, which is still a notion in its speculative early stages, these models need exotic matter. The study of dark energy and its impact on the expansion of the universe is another intriguing field of inquiry. Theoretically, deciphering dark energy could provide insight on how to manipulate spacetime and accomplish travel at the speed of light. The Casimir effect, in which negative energy is produced by quantum fluctuations between two plates that are very tightly separated, is another area of experimental physics that is being studied. A better understanding of how to produce the exotic matter required for potential faster-than-light travel structures may be gleaned from this event. Quantum information science and computers have made great strides, opening us new avenues for investigating these hypotheses. The limits of what can be tested and seen at the quantum level are being pushed by quantum simulations and high-precision experiments. By compressing and extending spacetime around a spaceship, mathematical models such as the Alcubierre drive provide a path toward faster-than-light travel. These models provide a foundation for future research and are theoretical in nature, yet they are based on the general relativity equations. Some scientists think we might learn more about the existence of particles or effects that travel faster than light by studying high-energy cosmic events like gamma-ray bursts or neutrino emissions. The use of sensitive sensors and sophisticated data processing methods is essential for these kinds of observations. In this area, theorists and experimentalists must work together. Both theoretical models and experimental designs are influenced by the findings of experiments. Improving our comprehension of potential faster-than-light travel requires this ongoing method. Experimental evidence and theoretical models for faster-than-light travel are at the forefront of current physics, notwithstanding the hurdles. We get closer to knowing the universe's actual boundaries and potential with each new finding, whether it confirms or disproves these theories. There are substantial obstacles and constraints to faster-than-light travel. A major concern is the massive amount of energy needed. As things stand, our energy generation and storage capabilities are woefully inadequate to power superluminal speeds, as predicted by existing models. Another big problem is exotic matter, which is crucial to many theories of faster-than-light travel. The characteristics of this hypothetical substance are unlike those of any known particle. there is still a long way to go before we can create or find unusual stuff. It is an enormous challenge to remain stable when traveling at speeds greater than light, even if unusual stuff could be created. To avoid collapse or other disastrous failures while traveling, theoretical constructions like as wormholes and warp bubbles need exact management. Controlling navigation at speeds faster than light has its own unique set of obstacles. When traversing altered spacetime, conventional navigational aids and course correction techniques may not be useful. It is critical to create new technology that can provide exact control and direction. No one knows how the human body would react to travel at speeds greater than the speed of light. Potential exposure to strange matter or powerful gravitational fields are only two examples of the extreme circumstances that might put visitors in harm's way. It is vital for human missions to understand and mitigate these impacts. Another unsolved problem is communication during travel faster than light. If you wanted to communicate in real time with a spaceship that could move faster than light, you would need to use a different signal. It is necessary to create new ways of communicating. A significant theoretical hurdle is the possibility of temporal paradoxes and violations of causality. If time travel could be accomplished faster than light, it may be possible to go back in time and see how things turned out. Consistent physical laws depend on overcoming these dilemmas. Building a time machine that can travel faster than light would be financially impossible. An enormous amount of money would have to be invested in research, development, and building the required infrastructure. This makes one wonder how feasible such initiatives are financially and how they will be funded. It is presently not possible to travel faster than light due to a lack of regulatory and legal structures. To handle concerns related to sovereignty, space traffic management, and possible militarization, international agreements and rules are required to oversee the use of this technology. We don't yet know how such massive manipulations of spacetime will affect the surroundings. Unforeseen alterations to local spacetime are one possible adverse outcome that may affect space and planetary habitats in ways that are not immediately apparent. Another matter of worry is the potential interference with current space missions and satellites. To keep present systems running smoothly and safely, new procedures and coordinated efforts will be needed in the event that transport at speeds faster than light is introduced. Time travel at the speed of light raises serious moral questions. Equal access to this technology, the risk of exploitation, and the ramifications of contacting alien life are all important issues that need to be thoroughly examined and resolved. A role will also be played by how the public perceives and accepts travel at speeds faster than light. A role will also be played by how the public perceives and accepts travel at speeds faster than light. To garner significant support and involvement in these activities, it is crucial to overcome mistrust and address concerns about safety and ethical consequences. Another obstacle is the fact that our present knowledge of general relativity and quantum physics is technologically limited. Theories and models for travel at the speed of light depend heavily on ideas that have not been confirmed or completely understood as yet. Improving our understanding in these domains is crucial. The quest for travel at speeds faster than light is still motivating physics research and development, despite these obstacles. To overcome these challenges, we need to work together across disciplines and be prepared to challenge the status quo. To overcome these challenges, we need to work together across disciplines and be prepared to challenge the status quo. A faster-than-light FTL traveler is one who, in theory, might move or communicate at a speed greater than the speed of light in a vacuum, which is around 299,792 kilometers per s. Our present knowledge of physics is called into question by the idea of FTL travel, especially by Albert Einstein's theories of general and special relativity. These hypotheses state that the speed of light is the maximum possible speed in the cosmos. The Alcubierre drive and other warp engines provide a theoretical foundation for investigating FTL travel. The idea is to construct a warp bubble that, when seen from the outside, causes spacetime to compress in front of a spaceship and expand behind it, enabling the spacecraft to travel at the speed of light. Wormholes, or Einstein-Rosen bridges, are another well-known theoretical concept. Wormholes are hypothetical holes in space-time that might allow fast transportation between faraway places in the cosmos. Also, tachyons, hypothetical particles with a speed greater than light, have been discussed by theoretical physicists. These hypothetical particles, with their imagined mass, may, in principle, provide light on FTL occurrences. One common argument for the existence of warp bubbles and wormhole stabilization is the presence of exotic materials with negative energy density. Important yet elusive in field theory of light, FTL ideas, this matter type exhibits characteristics drastically different from ordinary matter. When discussing FTL ideas, quantum physics adds another layer of complexity. When talking about fast time travel, quantum physics adds another layer of complexity. Possible methods for superluminal communication have been hinted at by ideas like quantum entanglement, which propose that particles may influence each other instantly over enormous distances. The consequences of dark energy and the universe's accelerating expansion are being investigated in theoretical models. New ways of altering spacetime and accomplishing FTL travel may be revealed by understanding these cosmic forces. The Einstein field equations and other general relativity-derived mathematical equations provide the groundwork for investigating these theoretical objects. Mass and energy distort spacetime according to these equations, which may lead to solutions that do not include gravity. The fascinating potential notwithstanding, the whole idea of FTL travel is still just that, a theory. Many obstacles must be surmounted before these ideas can be put into reality, and there is currently no experimental proof that they are feasible. The massive amount of energy needed to build and maintain FTL transport systems is a big obstacle. The enormous quantities of energy required for these hypothetical constructions are much beyond the capability of current technological systems. The reliability of FTL transport protocols is a further obstacle. A major threat to any effort at practical application is the presence of unstable configurations in theoretical models, which might collapse or function in an unpredictable manner. Another big worry is how FTL travel would change spacetime and causality. Deep concerns about the coherence of physical principles are prompted by the potential for temporal paradoxes in which the order of cause and effect is inverted. We can't progress in our knowledge of FTL travel without interdisciplinary cooperation. Theoretical and practical considerations of these ideas need collaborative investigation by scientists, engineers, and physicists in order to further our understanding. Both scientists and artists are still captivated by the idea of FTL travel. Although it is still a topic of speculation, FTL ideas are being studied and might change our view of the cosmos and our role in it. According to several cosmological and particle physics theories, there should be one-dimensional flaws in the fabric of spacetime called cosmic strings. Despite their minuscule thickness, these threads are laden with tremendous force and strain. Cosmic threads have the intriguing property of distorting spacetime around them. In theory, this warping effect may make circumstances ideal for traveling at the speed of light. An area of extremely bent spacetime may be created if two cosmic strings were to pass near one another. This may take the shape of a wormhole-like tunnel across spacetime, and it's called a string interaction. A spaceship might be able to travel a shorter route between two faraway locations in space if it uses this tunnel. By essentially avoiding the typical interval in between, the spacecraft might significantly shorten the voyage time. Gravitational waves, which are ripples in spacetime that travel at the speed of light, may potentially be produced by the energy and strain of cosmic strings. The spacetime structure around the strings might be further altered by these waves. Theoretically, a spaceship might theoretically ride these gravitational waves to greater speeds. The idea behind this is to use the inherent characteristics of cosmic strings to make travel quicker. It is believed that cosmic strings are artifacts from the early cosmos, created during phase transitions not long after the Big Bang. Their density is so high that a single thread, thinner than a nucleus, could span the whole visible universe. Cosmic strings are very thin and cover enormous distances, making their detection very difficult. Nevertheless, it may be possible to discern their massive gravitational pull by observing how they affect neighboring objects and light. One method for detecting cosmic strings is gravitational lensing. Astronomers would be able to tell a cosmic string apart because of the distinctive visual distortions it would cause when light from faraway galaxies and stars passed near it. The discovery and use of cosmic strings could pave the way for a new way to travel across space, one that doesn't rely on the exotic materials or massive amounts of energy needed by previous ideas for travel faster than light. Another possible source of information is the way cosmic strings interact with black holes. Black holes' powerful gravitational fields interacting with cosmic strings may give rise to novel phenomena that can be harnessed for more rapid transportation. To learn more about cosmic strings and their possible impacts on space-time, scientists are also looking at mathematical models of these entities. By using these models, we may better foretell the potential behavior and interactions of cosmic strings with other cosmic structures. Although the idea of cosmic strings is still in its early stages, our knowledge is constantly expanding because of developments in observational cosmology and astronomy. The discovery of cosmic strings would be a significant scientific milestone with far-reaching consequences. Cosmic threads, according to theoretical research, might link various parts of the cosmos in the same way as wormholes do. These links have the potential to transform our approach to space travel by allowing instantaneous transport to faraway celestial bodies. The fascinating prospect of using cosmic strings for travel at speeds greater than light motivates both scientific inquiry and creative speculation. If this were to be successful, it would revolutionize our capacity to explore space and open up new horizons. Antimatter might be a source of energy for traveling faster than light. Antimatter reactions are very efficient power sources because they release huge quantities of energy when they interact with matter. Nuclear fusion, the same mechanism that generates solar energy, is another potential energy source. Fusion reactions have the potential to provide a steady stream of tremendous energy, which is essential for modern propulsion systems. Dark energy, the driving force behind the universe's rapid expansion, is another fascinating contender. Possible manipulation of spacetime and realization of faster-than-light travel might be facilitated by tapping into dark energy. The zero-point energy state, which is the lowest potential energy of a quantum mechanical system, might potentially be used as well. There is an infinite potential supply of energy in this ubiquitous background energy that might be harnessed. The stabilization of warp bubbles or wormholes is commonly postulated to require exotic materials with negative energy density. Although it is essential for many conceptions of faster-than-light travel, finding or manufacturing such matter is a huge difficulty. Additionally, gravitational waves, that is, space-time ripples produced by very large objects, could be used. Technological advancements may one day allow us to use these waves for space-time manipulation or propulsion. Another such method involves the use of high-energy particle accelerators. If we could accelerate particles to speeds close to the speed of light, we could investigate other matter and energy states that might be used to achieve travel at the speed of light. An interesting and speculative notion is to harness the energy of black holes. Powerful spacecraft might be powered by harnessing the vast gravitational energy around black holes. Solar sails, which harness the kinetic energy of the sun, have the potential to integrate with other cutting-edge propulsion technologies. Even if they can't go faster than light on their own, they may be a component of a hybrid system that can. By enabling instantaneous data transport over enormous distances, quantum entanglement has the potential to radically alter current means of communication. This technique is essential for the management and coordination of missions traveling faster than light, but it does not provide energy. Another option is to tap into the potential energy of cosmic strings, should such things ever exist. Cosmic strings, with their tremendous mass and tension, may provide a novel and potent energy source for interstellar transport. Another potential source of novel energy generation mechanisms is the fusion of unusual particles, such as the hypothesized quark-gluon plasmas. These very energetic states may provide propellant systems with power densities never before seen. Another possible source of energy is the Casimir effect, which is a quantum phenomena in which fluctuations in a vacuum may be quantized as forces. It is possible to harness this phenomenon and use it at a larger scale to power sophisticated space travel. A more radical concept would be to harness the power of supernovae and other celestial phenomena. A more radical concept would be to harness the power of cosmic phenomena like supernovae. Spacecraft might be powered for lengthy galactic expeditions by harnessing the energy from such tremendous explosions. Lastly, improvements in energy storage and transmission may be possible as a result of developments in materials, science, and superconductors. Any possible energy source for faster-than-light travel must include these technologies in order to be feasible. Space travel, if it could move faster than light, would be a game-changer. New opportunities for colonization and resource acquisition would arise as a result of humanity's ability to reach other star systems much more quickly than with present technology. Additionally, our knowledge of the cosmos would be revolutionized if we could travel at speeds faster than light. Potentially uncharted areas of space might be explored by us, allowing us to collect data and make discoveries that could revolutionize our understanding of the cosmos. Space travel across galaxies might be possible. New potential for scientific study and economic growth might arise as a result of this capacity, leading to the discovery of livable or resource-rich planets. Additionally, we might investigate astronomical events up close with faster-than-light travel. To learn more about strange things like neutron stars, black holes, and other exotics than can be learned from Earth-based telescopes, we might launch probes into space. Time itself would undergo a radical transformation. Time dilation and even reverse time travel are possible outcomes of faster-than-light travel, which would force us to reevaluate our current understanding of cause and consequence and need the development of new theories. It would become possible to communicate instantly across great distances. For the purpose of organizing interplanetary voyages and keeping in touch with faraway colonies, this is vital, since it allows for the real-time sharing of information. It would considerably improve the hunt for alien life. Exoplanets and habitable zones orbiting other stars might be within our grasp, enhancing our prospects of discovering and understanding extraterrestrial life and maybe even establishing first contact. There would be major ramifications for our knowledge of dark energy and matter if we could travel faster than light. We may be able to get data that could shed light on these basic cosmological questions if we go into space where it has never been before. It would have a profound impact on the space industry's bottom line. Space exploration would become more appealing to both public and commercial entities if faster-than-light travel could shorten and lower the expense of long-duration trips. Space exploration would become more appealing to both public and commercial entities if faster-than-light travel could shorten and lower the expense of long-duration trips. Technology that can move faster than light has the potential to give rise to new economic sectors. Jobs and economic development might be created and boosted by spaceship manufacturing, energy generation, and space tourism. There is also the matter of the moral consequences of space travel at light speed to think about. It would be necessary to handle matters like the effect on native species, the possibility of exploitation, and the fair allocation of resources. Also, new regulatory frameworks would be required for travel faster than light. Managing the use of this technology, including territorial claims, space traffic management, and conflict avoidance, would need international agreements and rules. Space and planetary ecosystems would have to be assessed for the potential environmental effects of traveling faster than light. It would be our responsibility to avoid damaging the ecosystems we investigate, or the planet Earth as a whole. There would be far-reaching consequences for human culture and civilization. Extraterrestrial exploration and colonization has the potential to give rise to new human communities and cultures, each with the potential to enrich our own understanding of the universe. Last but not least, scientific and technical advancements would be propelled by the obsession with faster-than-light travel. It would challenge our present understanding and encourage subsequent generations to seek out new information. The majority of the present study on travel at speeds greater than light is theoretical. Concepts like as wormholes, warp drives, and tachyons are being investigated by physicists who are using the equations of quantum mechanics and general relativity to their mathematical analysis. Research into high-energy particle collisions is ongoing in labs like CERN in the hopes of uncovering physics-related oddities. However, these investigations are still expanding our knowledge and have not yet proven the existence of particles that travel faster than light. In order to detect gravitational lensing effects, which may point to the existence of cosmic strings, astronomers are making use of sophisticated telescopes. Possible faster-than-light travel might be enabled by these one-dimensional space-time anomalies with enormous mass and tension. Possible hints could be found in research on high-energy cosmic occurrences such as gamma-ray bursts. In order to discover new physics, scientists are searching for evidence that these events create or interact with particles that travel faster than light. Additionally, pertinent are experiments using quantum entanglement. A greater understanding of entanglement may provide light on non-local interactions that may be used for superluminal transit, even if entanglement does not permit faster-than-light communication in and of itself. As a possible generator of negative energy, physicists are looking at the Casimir effect. A modest force is generated by this quantum event between two closely separated metal plates. This force might, in theory, be magnified to create the exotic matter required for warp drives. Studying the universe's rapid expansion owing to dark energy could lead cosmologists to new ways of altering space-time. The discovery of dark energy may hold the secret to traveling at speeds greater than the speed of light. The idea of building man-made wormholes is also being considered by researchers. A large part of these endeavors is theoretical research into the best ways to use unusual materials to sustain such constructions so that they can stay open for practical travel purposes. This study relies heavily on advanced simulations. The viability of notions for faster-than-light travel is tested with the assistance of supercomputers, which mimic the complicated interactions between particles and fields under severe circumstances. The goal of the experiment is to find any medium in which the predicted speed of light deviates from reality. The goal of these tests is to find proof of faster-than-light occurrences while also examining the boundaries of special relativity. Cooperation between fields is crucial in order to put these complex ideas to the test and maybe uncover the first signs of travel at speeds faster than light. A team of cosmologists, engineers, and physicists is collaborating on experiment designs. Plans are afoot for space missions to collect data on cosmic occurrences that might be relevant to travel at speeds greater than light using sensitive detectors. Extremely precise observations of gravitational waves and high-energy events are the goals of these projects. Black hole and neutron star observations are also intriguing. Natural laboratories for testing these hypotheses, these severe settings may create situations where impacts quicker than light might be seen. Recent developments in quantum computing are facilitating this study. The possible mechanics for faster-than-light travel may be better understood with the help of these robust technologies, which enable more intricate simulations and data analysis. Research keeps improving our grasp of physics, even if no conclusive proof of travel faster than light has been discovered. The question of whether or not superluminal flight is feasible is becoming closer with each experiment and observation, which in turn opens the door to new discoveries. An enigmatic element known as dark energy is propelling the cosmos toward ever faster growth. Although its existence is still a major mystery to current physicists, it accounts for about 68% of the universe's entire energy content. The concept of dark energy was first proposed in the late 90s. The expansion of the cosmos is really speeding faster, contrary to earlier assumptions, according to observations of faraway supernovae. This sudden acceleration suggested the existence of an unidentified energy. The idea that dark energy exists in space is a popular theory. This theory proposes a self-reinforcing loop in which the expansion of space leads to the creation of even more dark energy, which in turn drives even greater growth. Albert Einstein's initial proposal of the cosmological constant provides the clearest explanation for dark energy. It stands for a uniformly filled area with a constant energy density. Even if it agrees with what we know now, this model still doesn't explain a lot. A second theory proposes that dark energy is a field that fluctuates, like inflation, which accelerated the expansion of the cosmos immediately after the Big Bang. As this field evolved, it would have different impacts on the rate of growth at different points in time. A dynamic model that fits this description is the idea of quintessence. According to this theory, dark energy is a scalar field that changes its state over time and has varied effects on the expansion of the universe. In order to quantify dark energy, one must study the cosmos at a cosmic scale. Scientists may deduce the role of dark energy in the expansion of the universe over billions of years by analyzing the distribution of clusters and galaxies. Furthermore, crucial information is provided by the cosmic microwave background, CMB, radiation. Microwave temperature and polarization variations in the cosmic microwave background, CMB, provide clues about the early cosmos and dark energy's impact on its development. Cosmological structure formation is impacted by dark energy. It prevents galaxies and clusters from forming faster by acting against gravity. The layout of large-scale structures that we see today is shaped by this interaction. It is essential for cosmology to comprehend dark energy. It is the final destiny of the cosmos that it contains. The cosmos will keep expanding at an accelerated pace if dark energy remains dominant. Eventually, this will cause a massive freeze in which galaxies will become inaccessible to one another. On the other hand, other outcomes may result from dynamic dark energy, such as a large rip in which the acceleration is so great that it rips apart galaxies, stars, and even atoms. There are ramifications for basic physics from studying dark energy as well. It calls into question our long-held assumptions about space-time, quantum field theory, and gravity. These fields could see revolutionary improvements if the enigma of dark energy is resolved. It is the hope of experiments such as the forthcoming Euclid mission and the Dark Energy Survey, DS, to better understand the characteristics of dark energy. The goal of these studies is to find out what this mysterious force is by gathering a ton of data on cosmic structures and expansion. Additionally, new models and ideas are being investigated by theoretical physicists. To account for dark energy, some have suggested updating general relativity or introducing new theories of gravity. These concepts challenge the limits of what we know about the cosmos at the moment. One of the most intriguing and perplexing topics in cosmology is dark energy. Our understanding of this cosmic force, which acts on the largest scales, is expanding as our observations and theories are fine-tuned. An exciting new frontier in the quest for travel faster than light is opening up as space continues to expand. The goal is not to travel across space, but rather to bring together previously separated locations by manipulating space-time. The Alcubierre warp drive is one such idea. It entails reducing the amount of space in front of the ship while simultaneously increasing it behind it. This generates a warp bubble, which enables the spaceship to practically move at the speed of light without really surpassing it at any one location. Within the warp bubble, the spaceship stays still in this model. The spaceship does not defy the principles of special relativity, since the space-time around the bubble is in constant motion. Space-time manipulation has the potential to pave the way for interplanetary travel. Exotic stuff with a negative energy density would be required for this to be accomplished by the warp drive. The circumstances for the needed warping of space-time would be provided by this substance. Exotic matter is essential to this idea, yet it is very difficult to find or create. Taking use of the universe's inherent expansion is another possibility. Constructing corridors of quickly growing space that reduce the distance between two sites might be possible if we could control or improve this growth. This may operate in a manner analogous to a cosmic highway. Wormholes are another potential use of expanding space. These theoretical frameworks provide a direct path between two faraway locations in spacetime. If we could stabilize a wormhole, we could traverse tremendous distances in what seems like a moment. Exotic matter is necessary for wormholes and warp drives to stay open and usable. Since the gravitational forces at work may be enormous, it would be of the utmost importance to guarantee the passage's stability and security. Dark energy is the driving force behind the universe's accelerating expansion. Understanding it might lead to new ways of manipulating space-time. Achieving travel at speeds greater than the speed of light may depend on our ability to understand and manage dark energy. We may learn more about the behavior of space-time under various settings from the latest studies of the cosmic microwave background and the universe's large-scale structure. Any real-world use of space-time manipulation requires this information. Possible methods for manipulating space-time are also presented by quantum field theory. Possible methods for manipulating space-time are also presented by quantum field theory. Physicists seek novel methods to manipulate and use space-time by studying the interplay of quantum fields with gravity. This area relies heavily on theoretical models and sophisticated simulations. With their aid, researchers are better able to foretell how warped space-time would operate, as well as determine the necessary energy levels and stability parameters for such applications. Advancements in engineering and theoretical physics are necessary for the practical use of space-time manipulation. Constructing and manipulating wormholes or warp bubbles is an enormous undertaking that challenges the limits of present-day scientific knowledge. Research that spans disciplines and countries is essential. Spelling out wormholes is an enormous undertaking that challenges the limits of our present scientific knowledge. Research that spans disciplines and countries is essential. To overcome the immense complexity and hurdles of traveling faster than light, a multidisciplinary team of scientists, including physicists, engineers, cosmologists, and others, must collaborate. Achieving mastery of space-time will have far-reaching consequences. The ability to travel to other galaxies, find uncharted planets, and maybe even meet extraterrestrial intelligence would be a game-changer for space exploration. We are getting closer to knowing if expanding space can really allow speedier travel with each new finding in the field of study. Seeking this information not only enhances our comprehension of science, but also ignites our creativity and optimism. To comprehend and maybe accomplish travel at the speed of light, one must have access to theoretical models and equations. These theories often originate from the general relativity equations, which outline the ways in which mass and energy distort spacetime. Among the equations that form the basis of general relativity is the Einstein field equation. The energy and momentum of any matter or radiation present are related to the curvature of spacetime by this equation. It is the cornerstone of knowing how cosmic gravity works. Answers to the Einstein field equation give rise to the Alcubierre drive, a theoretical framework for travel at the speed of light. A warp bubble, suggested by Miguel Alcubierre, may compress space in front of it and expand space behind it, enabling it to travel faster than light. The Alcubierre metric describes the warp bubble's structure and behavior by use of complicated computations. According to these computations, in order to sustain the bubble and make travel faster than light possible, unusual stuff with a negative energy density is required. These models rely heavily on the energy-momentum tensor. It lays forth the rules for how energy and motion move across space and time. In order to get the required space-time curvature for a warp bubble, the tensor has to include negative energy. Additional theoretical models that are solutions to the Einstein field equations include wormholes. According to these calculations, a wormhole may enable faster-than-light travel by connecting two faraway locations in space-time. Once again, unusual stuff with a negative energy density is needed to maintain a wormhole open. According to the wormhole calculations, the absence of this material would cause the wormhole's throat to collapse, blocking any passage through it. Additional equations and models introduced by quantum mechanics collide with general relativity. One example is the Schrödinger equation, which may be used to comprehend the actions of particles in distorted spacetime by describing the evolution of quantum states across time. The Casimir effect illustrates the negative energy production mechanism in quantum field theory via quantum fluctuations. Equations describing the force between two closely spaced conductive plates provide hints on how to create exotic matter and explain this phenomena. Potentially faster than light particles called tachyons are another area of study for theoretical physicists. Particular difficulties and opportunities arise from the fact that the equations controlling tachyons include imaginary mass and alter the conventional energy-momentum connection. Another theoretical framework that can be used to explain travel at speeds faster than light is string theory. It postulates additional spacetime dimensions and basic string vibrations that govern particle characteristics. Possible new understandings of spacetime manipulation are provided by the string theory equations. As an alternate method, loop quantum gravity seeks to quantify spacetime modification. As an alternate method, loop quantum gravity seeks to quantify spacetime, potentially providing new insights into and tools for shaping the cosmos. This theory employs equations to depict spacetime as a network of discrete loops. To solve these equations, one has to know advanced mathematical concepts like tensor calculus and differential geometry. With these methods, physicists may characterize and foretell the actions of energy and spacetime-related complex systems. It is essential that these theoretical equations and models undergo ongoing study and development. Our knowledge of the physical principles grows with each new development, and the prospect of traveling faster than light becomes ever closer with each passing day. Working together across disciplines is essential in this area. A collaborative endeavor spanning several scientific fields is necessary to back up theoretical models with experimental data and workable technical solutions. Traveling at the speed of light requires an enormous amount of energy. According to theoretical models such as the Alcubierre drive, the amount of energy needed to generate a warp bubble is comparable to that of whole planets or even stars. Antimatter is one possible place to find this energy. There is a tremendous burst of energy released when antimatter and matter smash against one another. The required power might be supplied by harnessing antimatter. However, there is a great barrier in creating and storing enough antimatter. Another possible energy source is nuclear fusion. The sun's power comes from fusion processes, which combine light atomic nuclei and produce massive quantities of energy. A reliable and powerful energy source might be achieved with the development of feasible fusion reactors. An intriguing prospect is dark energy, the unexplained factor that is causing the cosmos to expand at an accelerated pace. The ability to comprehend and control dark energy could pave the path for space-time manipulation and the realization of travel at the speed of light. Zero-point energy is yet another hypothetical wellspring. The lowest energy state that a quantum system may achieve is represented by it. Although still in the realm of theory, harnessing this ubiquitous background energy may offer an almost endless supply of electricity. Many ideas for travel at speeds faster than light need exotic substance with a negative energy density. This kind of matter possesses qualities that are completely unlike any other known stuff, making its creation or discovery a formidable challenge. Propulsion might be achieved by the use of gravitational waves, which are disturbances in space-time created by large objects. Although this concept is currently in its speculative early phases, advanced technology may one day be able to catch and use these waves. New energy sources may be discovered with the help of particle accelerators like CERN's. The goal of scientific particle accelerator experiments is to find previously unseen particles or forces that might be used to create faster-than-light travel by sending particles into space and studying their behavior. A different kind of energy may be available from black holes. It is possible to harness the enormous gravitational force around black holes and turn it into usable electricity. Nevertheless, there are tremendous theoretical and technological obstacles to obtaining energy from black holes. Solar sails use the kinetic energy of the sun to power spaceship propulsion. Although they cannot travel at the speed of light on their own, they might be used in conjunction with other forms of propulsion to accomplish this feat. By enabling instantaneous data transport over enormous distances, quantum entanglement has the potential to radically alter current means of communication. This technique is essential for the management and coordination of missions traveling faster than light, but it does not provide energy. If there are cosmic strings, they might be a one-of-a-kind power source. Even if cosmic strings don't really exist, their tremendous mass and strain may be used to propel spacecraft into orbit. Theoretical. Unprecedented power densities may be available in quark-gluon plasmas, which are hypothetical matter states that exist at very high densities and temperatures. The generation of energy may require the creation and manipulation of these unusual forms of matter. It is possible to generate substantial power for sophisticated space travel by expanding the Casimir effect, a quantum phenomena in which fluctuations in vacuum generate observable forces. There are potential applications for this phenomena that we are just scratching the surface of. Finally, these energy sources can't be put into practice without major developments in engineering and theoretical physics. An enormous undertaking lies ahead in the development of technologies to generate and regulate the conditions required for travel faster than light. Theoretically, one may move or communicate at speeds greater than the speed of light in a vacuum, which is about 299,792 kilometers per second. This is known as faster-than-light travel. Rapid time travel contradicts Einstein's theory of relativity, which states that nothing can surpass the speed of light without breaking the rules of physics. This contradicts the very principles upon which modern physics is based. The concept of warp drives, like the Alcubierre drive, is a well-known theoretical framework that investigates movement at the speed of light. In this theory, superluminal travel is possible even without a localized acceleration of the speed of light by use of space-time manipulation in the form of a warp bubble, which causes the space immediately around it to shrink while the space behind it expands. General relativity solutions to Einstein's field equations provide the theoretical groundwork for the Alcubierre drive. These answers point to the possibility that, under some circumstances involving exotic stuff, space-time may be bent to allow movement at the speed of light. In several theories of faster-than-light travel, exotic substance with a negative energy density is an essential component. The warp bubble or wormhole cannot be stabilized or maintained without this special kind of matter, which has characteristics not seen in regular matter. Einstein-Rosen bridges, often known as wormholes, are an additional theoretical paradigm for travel at the speed of light. These made-up constructions link two faraway places in space-time, so forming a shortcut that would enable rapid transportation between them. Potential insights into events occurring at speeds faster than light may also be found in quantum mechanics. Particles may have an immediate and far-reaching effect on one another, according to quantum entanglement and other related concepts, which calls into question the traditional ideas of location and causation. In order to enable travel at speeds greater than the speed of light, theoretical physicists are exploring potential intersections between general relativity and quantum field theory. Exploring the behavior of spacetime under extreme circumstances is the goal of these endeavors, which include complicated mathematical models and simulations. Another theoretical framework that can be used to explain travel at speeds faster than light is string theory. It adds dimensions beyond the well-known four and proposes that basic particles are one-dimensional strings vibrating at certain frequencies. New routes for faster-than-light travel may be revealed by these additional dimensions. As an alternate method, loop quantum gravity seeks to quantify spacetime. Theoretically, this might provide light on how to influence the cosmos to achieve travel at the speed of light by describing spacetime as a network of discrete loops. The energy needs of traveling faster than light present a formidable obstacle. We are now unable to produce the vast quantities of energy required to construct and maintain a warp bubble or to stabilize a wormhole, according to theoretical models. There are continuing experimental attempts to find signs of faster-than-light events or exotic stuff. The hunt for novel physics that might enable faster-than-light travel involves particle accelerators, astronomical studies, and high-energy physics experiments. Time, causality, and the structure of the cosmos are all profoundly affected by the prospect of faster-than-light travel, which has far-reaching consequences outside the realm of physics. It forces us to ponder the ultimate mysteries of life and the boundaries of our knowledge. There should be a focus on both practical and ethical aspects. New rules, international accords, and procedures will be needed to control the hazards and advantages of faster-than-light travel if it becomes a reality. Research into travel at speeds faster than light can only progress with the help of multidisciplinary teams. Various scientific disciplines, including cosmology, engineering, and physics, need to collaborate to overcome the theoretical, experimental, and practical obstacles to achieving faster-than-light travel. In ideas of faster-than-light travel, exotic matter plays a crucial role. Many theoretical models rely on it to stabilize warp bubbles and wormholes, as it supplies the negative energy density needed for these processes. Exotic matter permits the formation of a warp bubble in the Alcubierre drive concept. The spaceship can travel faster than light within this bubble because it reduces space-time in front of it and expands it behind, allowing it to do so without locally breaking the rules of physics. Another idea, wormholes, can only be accessed by means of exotic matter. In its absence, the wormhole's aperture would close, rendering realistic the concept of faster-than-light travel useless. Exotic matter has negative energy, which prevents the warp bubble or wormhole from closing due to the positive energy. The structure required for superluminal flight relies on this fine equilibrium. Possible methods for producing negative energy have been proposed by quantum field theory. For instance, the Casimir effect illustrates how between two closely separated plates, quantized negative energy may be produced by quantum fluctuations. If exotic matter could be created or found in a variety of ways, theoretical physicists would study these possibilities using different models. Interactions or collisions of high-energy particles at quantum sizes are common in these scenarios. Extra dimensions may contain the exotic particles needed for transit at the speed of light, according to string theory. Extraterrestrial dimensions may include the exotic stuff required to manipulate spacetime, in addition to the well-known four. Spacetime may really possess a granular structure, according to loop quantum gravity, which presents an alternative viewpoint. Possible new approaches to faster-than-light travel could be revealed by manipulating its structure at a basic level. Another intriguing topic is dark energy, the force responsible for the universe's rapid expansion. The ability to control spacetime on a galactic scale may depend on our ability to understand and use this energy. Scientists also hunt for hints in high-energy astrophysical events. Exotic matter may be able to emerge in response to events such as gamma-ray bursts or interactions with black holes, which might provide light on the possibility of traveling faster than light. There are theoretical and experimental endeavors that go into the search for exotic matter. Particle accelerators, such as the one at CERN, look for outliers that may indicate that new particles with the right characteristics are hiding out somewhere. Physicists are able to anticipate the behavior and interactions of exotic matter with other particles via the use of sophisticated simulations. Theoretical models are refined and experimental designs are guided by these simulations. Collaboration across disciplines is crucial. Collaboratively, cosmologists, engineers, and physicists investigate the feasibility of creating and using exotic matter for travel faster than light. Achieving success with exotic matter has far-reaching consequences. It would completely change the way we can study the cosmos, opening the door to visiting other galaxies and beyond. Despite the enormous obstacles, one of the most fascinating areas of contemporary physics is the search for exotic matter with the potential to enable travel at speeds greater than light. Our perception of the cosmos and our role in it might be profoundly altered by this. One of the main goals in the race for faster-than-light travel is the creation and use of negative mass. One of the main goals in the race for faster-than-light travel is the creation and use of negative mass. Using the Casimir effect, which generates negative energy due to quantum fluctuations between two plates with close spacing, is one such approach. An additional source of negative mass might be created by enlarging this effect. Particle accelerators, which produce collisions between very charged particles, provide an alternative method. As a result of these collisions, unusual particles with negative mass attributes may be created. In order to find these outliers, scientists are always tweaking their studies. A number of methods for producing negative energy are presented by quantum field theory. Researchers are aiming to manipulate quantum fields in a way that would allow negative matter to develop, which would then provide the material for warp bubbles or wormholes. Negative mass might be a result of certain astrophysical processes, according to some theorists. Negative energy zones may be created, for instance, by the very harsh circumstances close to neutron stars or black holes. Creating negative mass may be better understood by keeping an eye on and learning about these settings. Extra dimensions in string theory may include unusual mass-negative particles. Physics researchers are trying to find or create the negative mass needed for travel faster than light by delving into these unseen realms. Dark energy is another topic that researchers are looking at. The creation of negative mass may be conceivable via the manipulation of space-time if the dark energy that propels the universe's fast expansion could be captured. The creation of novel materials with characteristics analogous to negative mass is one area of active investigation in the experimental community. Negative energy densities may be created as a result of these materials' unusual interactions with quantum forces. Employing Bose-Einstein condensates, which are forms of matter created at very low temperatures, is another possible approach. Behaviors that resemble negative mass are among the peculiar quantum features that these condensates may display. According to theoretical models, negative mass might be produced by fundamentally modifying spacetime. Methods borrowed from loop quantum gravity, which models spacetime as an interconnected system of discrete loops, may provide novel approaches to this problem. Potentially usable as well are gravitational waves, or the spacetime ripples produced by very large objects. Scientists may be able to generate the conditions for negative mass if they are able to capture and use these waves. Another intriguing topic is the idea of vacuum energy, sometimes known as zero-point energy. Though still very much in the realm of speculation, drawing on this ubiquitous background energy could provide a way to produce negative mass. In these endeavors, interdisciplinary cooperation is of the utmost importance. Researchers in the fields of physics, materials, science, and engineering collaborate to investigate the potential theoretical and practical applications of negative mass. This study relies heavily on advanced simulations. Predicting the production and use of negative mass for faster-than-light travel is possible by studying the behavior of exotic particles and quantum fields. Making negative mass is a huge step toward many possible uses. Possible applications include the stability of wormholes and warp bubbles, the realization of faster-than-light travel, and the unlocking of hitherto unexplored regions. Despite the enormous obstacles, the search for negative mass is an essential component of the race to travel faster than light. With each new discovery, we get closer to understanding and controlling the underlying forces that form our cosmos. In physics and cosmology, traveling at the speed of light would have far-reaching consequences. Reaching speeds above the speed of light would put our present knowledge of the physical laws to the test, especially in light of Einstein's theory of relativity. The possible need to reevaluate our conception of causation is one significant consequence. Possible outcomes of faster-than-light travel include reversals of cause and effect, necessitating alternative explanations free of paradoxes. A paradigm shift in particle physics would occur with the discovery of exotic matter or negative mass. It would broaden the conventional model and provide fresh insights into the universe's nature by introducing additional types of matter and energy. In cosmology, travel at speeds greater than light has the potential to alter our perception of the universe's structure and development. It may open up hitherto inaccessible parts of the universe to human exploration, shedding light on the history and present state of stars, galaxies, and other astronomical entities. Our understanding of the Big Bang and the early cosmos may also be affected by the possibility of traveling at speeds greater than light. Close observation of faraway cosmic occurrences might provide evidence for or against current theories of cosmic inflation and the universe's early state. A practical way to test and confirm theories of quantum gravity, string theory, and other sophisticated frameworks that aim to unify general relativity and quantum mechanics might be provided via faster-than-light travel, if it is conceivable. Dark energy and dark matter are profoundly affected. Possible advances in our knowledge of these enigmatic cosmic components might result from first-hand observations and tests made possible by faster-than-light travel technology. Another possibility to consider is the idea of a multiverse. The possibility of traveling faster than light might throw light on whether or not there are numerous parallel worlds if it opens up new areas of space-time to exploration. As far as technical progress is concerned, the creation of travel faster than light has the potential to usher in novel energy and material sources. Beyond spaceflight, these advancements would impact sectors including energy generation, transportation, and communications. The development of more accurate models and computational physics will most certainly be driven by the need to achieve travel speeds greater than the speed of light. In order to describe complicated systems and anticipate the behavior of exotic matter and distorted spacetime, these tools are indispensable. Additionally, philosophical and ethical issues will surface. New discussions over humanity's role in the cosmos and our duties as explorers may arise if we were able to travel at the speed of light, which would drastically change our view of space, time, and existence. The potential social effects of traveling faster than light are enormous. The variety and durability of human society might be enhanced if it leads to the formation of other civilizations on faraway planets, each with its own culture, laws, and technologies. These uncharted territories would need educational system adaptation. For faster-than-light technology to remain relevant and useful, it is essential to educate and train the scientists, engineers, and explorers of the future. There must be cooperation across countries and international groups. Cooperation on a worldwide scale is necessary for the development and regulation of faster-than-light travel to guarantee an equitable distribution of benefits and responsible management of hazards. Beyond physics and astrophysics, faster-than-light travel has far-reaching effects. They provide unparalleled chances for exploration, creativity, and progress, touching on every facet of human understanding and society. As we've dug into the topic of travel at the speed of light, we've come across a number of important ideas and theories that both expand our horizons in terms of what we know about the universe and the laws of motion in the cosmos. One idea underlying warp drives, the Alcubierre drive in particular, is to build a warp bubble that follows spacetime ahead of a spaceship and enlarges it behind, enabling superluminal flight without really going faster than light in any one area. Known as Einstein-Rosen bridges or wormholes, these are hypothetical gaps in spacetime that may link faraway places, thereby allowing for faster-than-light travel. To be sturdy and passable, these constructions need unique materials. Many theories of faster-than-light travel rely on exotic matter, which has a negative energy density. Despite being nebulous and speculative, it provides the conditions needed to sustain warp bubbles and maintain open wormholes. The Casimir effect and quantum entanglement are two examples of the new phenomena introduced by quantum mechanics. They point to possible ways of producing negative energy and faster-than-light communication, respectively. A challenge to classical ideas of location and causation is posed by these quantum regulations, theorizing basic strings and extra dimensions. String theory provides a framework for comprehending the possibility of controlling or discovering exotic particles inside these extra dimensions, which might lead to faster-than-light travel. Another method of quantizing spacetime, loop quantum gravity, proposes that spacetime is made up of individual loops. This idea has the potential to provide light on how the cosmos may be bent to achieve movement at the speed of light. In theory, there are new obstacles and opportunities associated with tachyons, which are hypothetical particles with a speed greater than light. Their presence would need the introduction of new particle categories and a re-evaluation of the conventional energy-momentum connection. Dark energy is the driving force behind the universe's accelerating expansion. Understanding it might lead to cosmic-scale manipulation of spacetime. In order to create technology that moves faster than light, it may be necessary to understand this enigmatic force. The creation of unusual stuff might be facilitated by high-energy astronomical events like gamma-ray bursts and interactions close to black holes. If we can learn anything from these occurrences, it may be how to travel faster than light. The exploration of these ideas requires sophisticated mathematical models and simulations. They are useful for informing experimental designs and theoretical model refinements by providing predictions about the behavior of exotic matter and warped spacetime. In order to discover new physics that might allow travel faster than light, particle accelerators, such as those at CERN, play a crucial role. It is believed that new particles or forces may be revealed by studying high-energy collisions. The search for a way to travel faster than light has far-reaching consequences for how we conceptualize the cosmos, its history, and the rules of physics. It makes us question what we know and motivates us to look for fresh explanations. This study has the potential to transform several industries, including as energy generation, transportation, and communications, via technical breakthroughs. Space exploration wouldn't be the only field to benefit from these breakthroughs. As the prospect of traveling faster than light becomes more real, many philosophical and ethical problems will be raised. Among them, we must think about our duties as explorers, our obligations to other possible cultures, and how to oversee the development of new technology. Achieving travel at the speed of light is an arduous and complicated task that calls for cooperation across disciplines and nations. Our scientific and cultural perspectives are broadened as we continue to explore these frontiers, pushing the limits of what is possible. Recent developments in our knowledge of cosmology and physics have kept faster-than-light research in its present, mostly theoretical condition. Mathematical underpinnings of exotic stuff, warp engines and wormholes, are now being investigated by scientists. Worldwide, particle accelerators are expanding the frontiers of high-energy physics at various research institutes. Research at labs like CERN seeks to identify novel particles and forces that might pave the way for travel at the speed of light. Models for manipulating spacetime are being developed by theoretical physicists. In their pursuit of consistent solutions that permit superluminal transit, these models often include intricate computations grounded in quantum physics and general relativity. Scientific inquiries into quantum entanglement and the Casimir effect are being conducted within the field of quantum mechanics. The goal of these investigations is to learn how quantum mechanics can generate the negative energy required for warp bubbles, or how faster-than-light communication may be made possible. Astrophysicists are looking for indirect proof of impacts that travel faster than light by studying cosmic occurrences with extraordinary energies. Black hole interactions, gamma-ray bursts, and other extreme occurrences may offer light on the presence of exotic matter and other prerequisites. The nature of dark energy is still shrouded in mystery. Achieving travel at the speed of light may depend on it. Thus, scientists are trying to figure out what it is and how to use it for space-time manipulation. This study relies heavily on advanced simulations. The stability and practicability of warp drives and wormholes may be better predicted with the use of supercomputer models that simulate spacetime behavior under severe situations. Cooperation between fields is crucial. Together, cosmologists, computer scientists, physicists, and engineers are investigating the theoretical and practical obstacles to travel at speeds faster than light. The hunt for unusual substances is ongoing. Experiments are being conducted to find negative energy density particles by observing unusual quantum phenomena that might be a hint of their existence. New ideas for propulsion, including the Alcubierre drive, are under development. These models are the subject of state-of-the-art theoretical work because they need a thorough familiarity with general relativity as well as the capability to control spacetime. New methods for movement at speeds greater than light are being investigated by using quantum field theory. Researchers want to discover new methods to influence spacetime by studying the interaction between quantum fields and gravity. There are plans to send space probes with high-tech detectors to study the cosmos. The goal of these missions is to study gravitational waves and high-energy phenomena as precisely as never before in the hopes of discovering hitherto unknown information. In order to direct experimental endeavors, theoretical advances are crucial. We get closer to practical applications and a better grasp of quantum physics, general relativity, and cosmology with each new finding in these fields. For this area to progress, international cooperation is essential. Cooperation between scientists from different parts of the globe is essential in order to overcome the enormous obstacles in the field of faster-than-light research. Even if traveling at the speed of light is still a pipe dream, scientists are constantly expanding our understanding via their investigations. Not only does progress get us one step closer to superluminal travel, but it also increases our knowledge of the cosmos and its underlying rules. If we can travel at the speed of light, it will change the way we perceive the universe and offer up new possibilities for space travel. The formation or finding of exotic matter with negative energy density, which is essential for maintaining warp bubbles and wormholes, is one of the most fascinating possibilities. Progress in the field of particle physics may lead to the discovery of new particles or forces that pave the way for travel at the speed of light. Breakthroughs in high-energy particle accelerators may be the key to unlocking the mysteries of superluminal speeds. To propel anything faster than light, the enormous amounts of energy needed may be provided via the creation of workable fusion reactors. The development of a sustaining fusion reaction would mark a significant milestone in the evolution of fusion technology. Revolutionary approaches to space-time manipulation may emerge from our quest to understand and exploit dark energy. We may find the secret to creating technology that moves faster than light if we can master this enigmatic energy. More complex models and simulations of manipulating space-time may become possible as quantum computing advances. Complex models and simulations of manipulating space and time. The development of realistic systems for superluminal travel may be aided by these state-of-the-art computer resources. Finding wormholes in nature or proof that they exist would be a huge step forward. Observing these structures in space might offer light on how to intentionally build and stabilize them, as well as confirm theoretical models. New materials that can endure the harsh circumstances of faster-than-light travel may be developed as a result of advancements in material science. Warp drives and other forms of sophisticated propulsion would not be possible without these materials. If faster-than-light particles like tachyons could be detected, it would completely alter the field of physics. If they really exist, it would throw existing hypotheses into a loop and lead scientists in a new route when studying superluminal transit. If our knowledge of quantum entanglement continues to grow, it may find use in technologies that allow for instantaneous communication across great distances. In order to keep in touch with faraway explorers and coordinate interplanetary expeditions, this is essential. A more complete foundation for travel at the speed of light might be provided by the development of new theories that combine quantum physics with general relativity. If these hypotheses pan out, humans may be able to control hitherto unknown features of spacetime. Findings in cosmology, including how the universe formed or how black holes behave, may shed insight on how to travel at the speed of light. Potentially useful insights may be gleaned by studying these harsh settings. Internationally coordinated initiatives have the potential to accelerate development in this area. The enormous obstacles of creating technology that travels faster than light may be met if countries collaborate and share resources. New forms of propulsion that integrate many cutting-edge ideas may soon appear. Possible workable options for interstellar travel might include hybrid systems that combine warp drives with other forms of high-speed propulsion. Major progress may be possible if both the public and business sectors contribute to space exploration. The development of new technology and experimental techniques would be supported by increased funding and interest in pursuing faster-than-light travel. Every new development, whether in theory or in practice, moves us one step closer to our ultimate goal of traveling faster than light. Not only does this keep us curious and engaged in learning, but it also gives us hope for the future. There are many different kinds of obstacles and moral questions that arise while trying to travel faster than light. The massive amount of energy needed is a big problem. The development of technology that can produce and maintain the necessary amounts of energy is an enormous undertaking. Making and keeping exotic matter stable is another major challenge. The generation of exotic matter is a major scientific issue since its characteristics are not yet known or seen. This makes it essential for ideas like wormholes and warp drives. Methods for traveling faster than light are often predicted to be unstable in theoretical models. The practical use of warp bubbles or wormholes depends on their stability during passage, meaning they must not collapse or have negative side effects. Significant navigational difficulties arise at speeds beyond the speed of light. We need new innovation to make sure we're secure and have exact control, since old navigation systems may not work in these situations. Another worry is the effect on human physiology. Extensive study into safety precautions and long-term impacts is required, since the harsh circumstances linked with faster-than-light travel could endanger human health. Another issue that comes with faster-than-light travel is communicating over enormous distances. For mission coordination and safety, it is crucial to develop ways for dependable and immediate communication with spacecraft traveling at superluminal speeds. Questions of theory and ethics are prompted by the possibility of temporal paradoxes and breaches of causality. Possible outcomes of traveling faster than light include reversal of cause and effect, which would call into question our current conception of time and need other theoretical frameworks. Creating technology that can travel faster than light will have a major financial impact. We require massive investments from the public and private sectors, which begs the issue of how we can fairly divide up the rewards and resources. An enormous moral dilemma arises when faster-than-light technology is considered for possible military use. International agreements and regulations must be strong to prevent the reckless use of such powerful technology. The effects on the environment also need to be thought about. Unforeseen effects on space ecosystems and planets' biomes may result from such massive manipulation of spacetime. Strict precautions and evaluations of the surroundings are required. There are moral concerns over how to handle any alien species found as a result of space travel and possible colonization of other planets. It is critical to establish protocols for the appropriate and courteous engagement with extraterrestrial ecosystems. There is also the matter of fair access to technology that can travel at speeds faster than light. Fostering global collaboration and equality requires making sure that the advantages of modern technology are shared internationally, not monopolized by a few governments or firms. The social effects of traveling at speeds greater than the speed of light would be enormous. It may cause new civilizations to emerge in other star systems, which raises the important question of how these societies will interact with one another and with Earth. How people see and embrace faster-than-light travel will have an impact on how it is developed and put into practice. It will be crucial to interact with the general population, respond to their concerns, and encourage a spirit of collective curiosity and investigation. In the end, there has to be a balance between ambition and accountability in the race toward faster-than-light travel. We can accomplish this remarkable feat in a manner that benefits everyone and protects the future if we tackle the obstacles and ethical issues together, thinking carefully and working together. We delved into the scientific principles and theoretical notions that test our present knowledge of physics as we investigated the intriguing and intricate realm of faster-than-light travel in this video. We started with a brief history of light speed to lay the groundwork for the tremendous difficulties and fascinating opportunities that come with traveling faster than light. Warp engines, wormholes, and tachyons were among the major ideas we covered, along with their possible applications to superluminal travel. A key component in stabilizing these theoretical structures and making faster-than-light travel viable was the function of exotic matter and negative energy density. We traversed quantum physics and the Casimir phenomenon on our quest to understand how quantum principles may lead to methods for manipulating spacetime and communicating at speeds beyond the speed of light. Additionally, we investigated the possible uses of dark energy and the universe's rapid expansion for interstellar travel, as well as their ramifications. We discussed some of the difficulties and moral questions that arise with trying to travel faster than light. There are several obstacles that need to be carefully considered, such as the enormous energy demands, the necessity for exotic materials, the possible effects on human physiology, and environmental issues. While we were out there, we kept thinking about how new discoveries may change the way we understand physics and lead to exciting new opportunities for space travel. The future is filled with intriguing possibilities, such as advances in particle physics, fusion technology, material science, and the finding of natural wormholes. We also spoke about where research stands at the moment, with an emphasis on the value of working together across disciplines and across borders. Physicists, engineers, cosmologists, and other scientists must work together, and public and commercial sectors must spend heavily if we are to accomplish faster-than-light travel. A foundation of contemporary physics and astronomy is cosmology, the study of the creation, evolution, and ultimate destiny of the universe. It makes the connection between exact scientific findings and wide philosophical issues. Cosmology has undergone several phases historically. Every step, from the prehistoric cosmic models to the groundbreaking change brought about by Einstein's theory of general relativity, has massively increased our knowledge. Nevertheless, we are at a crossroads now, dealing with anomalies that the theories of today are unable to completely explain. This issue is a serious problem that may completely change cosmological theoretical underpinnings and future study, not simply a little blip. The stakes are high as new physics that changes our knowledge of everything from the tiny world of particles to the enormous universe might result from the solutions. We shall expose the layers of this disaster over the following few hours. We will look at the major issues including the Hubble tension, the enigmas surrounding dark matter and dark energy, and the odd discoveries that present theories find difficult to explain. Every one of these problems suggests possible fissures in the very basis of our knowledge of the cosmos. As we push the limits of known science, our trip will lead us through the depths of theoretical physics, challenging the firmness of Einstein's ideas and the completeness of quantum mechanics. We explore competing ideas, including changes to our conception of gravity itself, that try to explain these cosmic puzzles. Leading this investigation are also the instruments we employ to see and understand the cosmos. Technology breakthroughs have given us previously unheard of volumes and precision of data, posing fresh problems and providing new insights. Significant players in this narrative are the Event Horizon Telescope, the James Webb Space Telescope, and other equipment. We shall examine how these instruments not only improve our capacity to observe the known, but also enable us to explore the unknown, pushing the boundaries of our ideas and occasionally exposing their flaws. A new physics or undiscovered aspects of the cosmos are hinted at by the increasing conflict between various estimations of the universe's expanding pace. We shall take into account the philosophical ramifications of these scientific endeavors throughout this investigation. How does our presence inside the universe get reflected in our knowledge of it? What is the meaning of a theory offering a realistic universe description? In closing, we will consider the future and speculate on how fresh ideas, developments, and experiments can someday overcome the cosmological challenges of today. Among the philosophical and ethical issues raised by exploring such deep concerns about our cosmos will be discussed. Lastly, we shall consider the significance of cosmology as a basic human endeavor that answers our deepest questions about the world around us, as well as a science. We maintain alive the most fundamental features of our nature, our unrelenting desire of knowledge, as long as we keep exploring, questioning, and challenging the universe. Cosmology is the study of the large-scale characteristics of the cosmos as a whole, conducted scientifically. It tries to comprehend the whole universe with the greatest models and scientific facts already accessible. Cosmology is important because it can explain the history, present, and future of the universe physically. Combining physics, astronomy, mathematics, and even philosophy, this area addresses some of the most important cosmic mysteries. Cosmology tries to find the basic rules governing the universe by investigating its beginning, structure, evolution, and ultimate destiny. Developing the Big Bang theory was one of cosmology's major accomplishments. This tells how the cosmos grew from a very hot and dense condition and is still growing now. It is the mainstay that backs up most of the cosmological observational research. Cosmology has profound consequences for not only our knowledge of the universe, but also for the whole field of physics. It investigates the dynamics of galaxies and galaxy clusters while investigating the role of dark matter and dark energy, which together make up most of the mass-energy content of the universe. Under circumstances that are unfeasible in terrestrial facilities, it tests physics laws. Astronomical observations, for example, frequently guide ideas of basic particles. Furthermore, cosmology poses essentially philosophical issues, including the origin of the universe and the nature of the world itself. These are difficult problems that demand for novel theories and approaches to be addressed. Additionally, important ramifications are associated with the observational component of cosmology. With a range of techniques for seeing the universe at various wavelengths, from radio waves to gamma rays, it offers a thorough picture of the cosmos. By use of these discoveries, cosmologists have been able to map the cosmic microwave background radiation, which offers a window into the early cosmos, calculate the pace of expansion of the universe, and deduce the existence of phenomena such as black holes. Radiation offers an early universe glimpse. Because cosmology is multidisciplinary, it has spurred cooperation across many scientific fields and resulted in important technical breakthroughs. These include developments in sensors, telescope technology, and data processing techniques, all of which progress science and engineering in turn. By contradictions and anomalies arising from observational data, it also questions our knowledge of the cosmos and generates continuous discussions and studies to find solutions. Regular investigation not only improves but sometimes completely transforms current models. Education of the public about science and our role in the cosmos depends on an understanding of cosmology. It tackles basic issues of life and promotes a feeling of common history and destiny among the many peoples of our planet. Cosmology reflects our aspirations and our curiosity by educating us about ourselves as much as the cosmos. It represents our attempt to study and comprehend the cosmos down to the tiniest subatomic particles and the biggest galaxies. As it lies at the nexus of philosophy, science, and culture, cosmology is among the most fascinating and dynamic fields of human study. It increases our interest in the cosmos in addition to satisfying it, therefore raising our intellectual potential to hitherto unheard-of levels. Cosmology not only provides answers to long-standing issues, but also raises new ones as we remove layers of the cosmos, making our trip through it a constant experience. Motivated by theory as much as observation, this trip keeps reshaping our knowledge of the fundamental nature of reality. Over millennia, cosmology has undergone tremendous change influenced by many civilizations and scientific discoveries. Ancient societies like the Greeks and Babylonians at first saw the cosmos as a flat planet or a central globe encircled by the sky. Myth and religion were intimately linked to these early models. When Nicholas Copernicus postulated in the 16th century that the Earth orbited the Sun rather than the other way around, cosmological thought underwent a revolution. Modern astronomy owes much to this heliocentric paradigm, which upended conventional wisdom and changed our understanding of the cosmos. Expanding Copernican theory, in the 17th century, Johannes Kepler and Galileo Galilei presented telescopic data in favor of the heliocentric model and laws of planetary motion, respectively. These developments emphasized how crucial empirical facts are to forming our knowledge of the universe. With the mathematical description of the gravitational force governing the motion of celestial bodies found in his law of universal gravitation, Isaac Newton further revolutionized cosmology in the late 17th century. This gave celestial as well as terrestrial events a single explanation. A single explanation for celestial and terrestrial events. A new age of cosmological discovery began in the 20th century with the 1915 publication of Albert Einstein's theory of general relativity. With its suggestion that huge objects bend spacetime itself, this theory provided a fresh framework for comprehending the gravitational forces in the cosmos. When Edwin Hubble discovered that far-off galaxies are traveling away from us in all directions in the 1920s, he made even another enormous contribution. The Big Bang theory was formulated in part because of this finding, which offered the basic proof for the expanding cosmos. Critical evidence for the Big Bang hypothesis was provided in 1964 when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, which provided a window into the early cosmos. New paths to comprehending the beginnings and early phases of the cosmos were also made possible by this finding. Alan Guth and colleagues' creation of inflationary theory in the late 20th century suggested that the early cosmos experienced an exponential expansion, which resolved a number of Big Bang model difficulties. Nowadays, this idea is an essential part of contemporary cosmology. The startling finding that the universe is expanding faster occurred in the 1990s and beyond. Dark energy, a mystery factor causing this acceleration, was proposed in response to this discovery, which was made via research of far-off supernovae. Our knowledge of the structure and composition of the universe has been improved by the thorough mapping of the cosmic microwave background by missions such as NASA's Cosmic Background Explorer, and later, the Wilkinson Microwave Anisotropy Probe, which has produced a clear image of the universe shortly after the Big Bang. A cosmic network of galaxies and dark matter has been revealed by cosmologists studying the large-scale structure of the universe, thanks to large-scale simulations and observatories. The distribution of matter in the universe and the function of dark matter in cosmic development have been clarified by these formations. Gravitational wave astronomy became possible after LIGO discovered gravitational waves in 2015. By using this finding, scientists may now investigate phenomena like black hole mergers that are normally inaccessible with conventional telescopes. In 2019, the Event Horizon Telescope project made another historic achievement by taking the first picture of a black hole event horizon. Together with confirming a general relativity prediction, this amazing accomplishment showed the value of international scientific cooperation. Exploring the nature of dark matter, the characteristics of dark energy, and the potential of multiverse ideas, current cosmology research keeps pushing the limits of our understanding. Every finding and theoretical development advances our knowledge of the universe's inner workings. Even as new discoveries loom, cosmology is still a dynamic area of study that uses observation, theory, and audacious conjecture to constantly change our knowledge of the cosmos. This continuous trip represents our never-ending attempt to solve the secrets of the universe. The progress of cosmology depends on the resolution of the present problems as they have an immediate effect on our basic knowledge of the cosmos. Our cosmos models remain incomplete and may miss important facets of cosmic events if these disparities are not resolved. These concerns are important for reasons other than purely theoretical ones. They will affect our future scientific studies and the technologies we create practically. From satellite trajectories to our more general space exploration plans, advanced cosmological models have an impact. Moreover, improvements in other branches of physics may result from improving our cosmic models. Particle physics, for instance, may benefit from the resolution of the nature of dark matter and dark energy, which may reveal new particles or forces that might completely transform the area. Furthermore, a deeper knowledge of cosmic expansion and the destiny of the cosmos might enable us to forecast and maybe even lessen cosmic dangers against Earth. It is not just scholarly to understand these basic cosmological principles, it is also necessary for long-term survival and strategic planning. Especially in fields like telescope design, sensor technology, and data processing, the attempt to tackle these challenges also spurs technical innovation. Every theoretical or observational advance can result in new methods and instruments that have applications in many scientific fields. Taking up these problems encourages multidisciplinary cooperation by uniting mathematicians, computer scientists, physicists, and astronomers. These partnerships improve every subject by increasing the breadth and depth of research approaches and discoveries. Educatively, addressing these important issues piques the curiosity and attention of the upcoming scientific generation. Resolving these crises offers engaging case studies for teaching that highlight the dynamic character of scientific research. Philosophy-wise, knowing the cosmos tests and sharpens our ethical and existential viewpoints. Our philosophical perspective on life and our perception of our role in the cosmos are influenced by the greater thoroughness of our cosmological models. Financially speaking, the large expenditures in space exploration and expensive astronomical observatories may be justified by obvious outcomes and answers to cosmological concerns. Progress may be ensured by proving it with money and assistance from the public and commercial sectors. Fixing these problems also improves our capacity for prediction. Resolving the cosmological crisis also helps to maintain public trust and interest in science by demonstrating that science can tackle and solve big existential questions. The drive to resolve cosmological issues promotes global cooperation. Accurate cosmological models allow us to better predict celestial events and understand the universe's long-term behaviors, which is essential for future space missions and long-term planning. International cooperation and finance are needed for many of the infrastructures and research initiatives, which promotes goodwill and common objectives amongst many countries. In order to guarantee responsible and ethical behavior in these activities, a richer knowledge of the universe through resolved cosmological models might direct our choices about space exploration, the use of space resources, and our general approach to the cosmos. At last, like the changes brought forth by Copernicus or Einstein, a new philosophical and scientific paradigm might result from resolving the cosmological crises. Such a change may bring fresh perspectives and maybe even new natural laws, hence redefining humanity's understanding of reality. Every one of these arguments emphasizes how crucial it is to address the present problems in cosmology for the benefit of the discipline, as well as for the wider effects on philosophy, science, technology, and society at large. We not only increase our knowledge, but also our capacity to innovate and comprehend our universe at a deeper level as we keep investigating these issues. Given that it gauges the speed at which the cosmos is expanding, the Hubble constant is among the most important numbers in cosmology. Named for the American astronomer Edwin Hubble, who made the crucial finding in the 1920s, it measures the speed at which galaxies are drifting apart. This constant is given in kilometers per second per megaparsec, which indicates that the expansion of the universe causes a galaxy to be seen to be moving away from us at a specific speed for every megaparsec, or around 26 million light-years, away from us. The cosmos is expanding equally, since Edwin Hubble's studies showed that galaxies farther away from us are moving faster. Because it suggested a beginning to the cosmos, which led to the Big Bang theory, this was a momentous finding. Astronomers determined the Hubble constant by measuring the distance to distant galaxies and their rate of motion away from us. Viewing the light from a galaxy and analyzing its redshift, which results from the light stretching as the universe expands, will reveal this speed. Ongoing discussion and improvement have surrounded the exact value of the Hubble constant. Measurement techniques involving far-off supernovae, cosmic microwave background radiation, or other astronomical markers have produced somewhat varied outcomes. This measurement disparity is more than a little technical problem. It suggests a deeper cosmological catastrophe. Is not only a little technical problem, it suggests a deeper cosmological catastrophe. Should the pace of expansion of the universe vary among measurements, it may point to undiscovered physics, including dark energy characteristics or the behavior of gravity on cosmic scales. Understanding the Hubble constant is essential to the study of cosmic phenomena since it influences calculations pertaining to the cosmic microwave background and models of dark matter and dark energy, which together make up most of the universe's total energy density. It also helps us infer the age of the universe. A higher Hubble constant suggests a younger universe while a lower value indicates an older universe. A better knowledge of the structure and history of the universe is also obtained by adjusting the Hubble constant value. It has an impact on our theories of the formation and evolution of galaxies, the interactions between galaxy clusters, and the destiny of the universe. Though it goes by that name, the Hubble constant is not really constant across time. As the universe's dominating forces shift, so does the pace of expansion, according to models. Dark energy has accelerated the universe's expansion after gravity slowed it down early on. Finding the precise value of the Hubble constant is difficult because of this change of the universe's expansion rate. It calls both very accurate observations and a thorough grasp of cosmic history from the Big Bang to the present. The argument over the Hubble constant captures the dynamic character of cosmology. Our knowledge of this constant and what it reveals about the cosmos is always changing as new technology and observational methods are developed. Finding the correct value alone cannot resolve the discrepancies in Hubble constant measurements. Knowing the fundamental principles guiding the universe's growth is crucial to its future. Every new Hubble constant investigation pushes the limits of known physics and challenges our presumptions while providing a new window into the mechanics of the universe. It is a key that facilitates the solution of the past, present, and future puzzles of the cosmos. The Hubble constant is thus not only a quantity, it is a basic component of our cosmic structure, the cornerstone around which most of contemporary cosmology and astronomy is erected. Different values of the Hubble constant, the universe's expansion rate, taken from observations of the early universe, and those from the local universe, are among the most perplexing anomalies in cosmology. This disparity raises serious questions about our comprehension of the universe and implies that our models as they stand might be lacking. Usually, studies of the cosmic microwave background radiation, the Big Bang's afterglow, form the basis for measurements from the early cosmos. Cosmologists may deduce the expansion rate at that time by examining the characteristics of this radiation, which offers a picture of the universe at its age of only 380,000 years. Local measurements, however, come from observations of supernovae, Cepheid variables, and other common candles in neighboring galaxies. Because these objects have known luminosities, astronomers can determine distances and velocities and therefore directly measure the present rate of expansion. The difference results from the tendency of the Hubble constant value obtained from the cosmic microwave background to be less than that obtained from local observations. This implies that, given circumstances seen in the early cosmos, the universe is expanding more quickly now than would be predicted. Several things add to this stress. The expansion of the cosmos may be influenced by unidentified kinds of matter or energy that are not taken into consideration in the models already in use. Alternatively, the difference might be indicating something novel about physics that goes beyond the conventional paradigm of particle physics and our present knowledge of gravity. A further thing to think about is the part played by dark energy, an enigmatic element propelling the universe's fast expansion. The reason the expansion rate seems different when measured at different epochs might be explained if dark energy has changed throughout the history of the universe. Biases and measurement mistakes could potentially be factors in the difference. Because astronomy observations are so sensitive to the techniques and equipment utilized, even minute biases may provide very different findings. These metrics are always being improved by new developments in technology and technique. Astronomers may lower uncertainty and use several observational methods to cross-check data as telescopes and sensors get more advanced. Cosmologists model the cosmos and forecast what various measurements should be based on different theoretical assumptions, using computer simulations as well. These models make it easier to determine which hypotheses fit the data the best and where new ones might be required. One possible strategy to reconcile the disparity is to search for other methods of determining the expansion rate, like gravitational waves as cosmic rulers. This technique has now become practical since a whole new approach to measuring cosmic distances is offered by the discovery of gravitational waves from merging neutron stars. The argument over the Hubble constant affects our knowledge of the cosmos in practical ways as well as academically. By resolving it, we may learn more about cosmic history, from the Big Bang to the present, and maybe forecast the course of cosmic expansion going ahead. A lively field of cosmology inquiry is the continuous investigation of this disparity. It unites several fields, from theoretical physics to observational astronomy, all of which provide insights that can assist answer this riddle. In the end, a fresh knowledge of the basic forces sculpting the universe could result from the resolution of these disparate observations. Whatever the result, new particles, forces, or a new gravity theory, our knowledge of the cosmos will probably be completely changed. Cosmology continues to push the frontiers of our knowledge about the universe and our role within it as we investigate these disparities. In addition to expanding our knowledge of cosmology, the search for these solutions propels methodological and technical breakthroughs that improve science as a whole. The differences in Hubble constant readings seriously affect cosmological theories and raise doubts about our knowledge of the basic characteristics and dynamics of the cosmos. The behavior of galaxies and the eventual destiny of the universe are all predicted by these models, mostly using exact constants. Local universe data point to a younger universe if the Hubble constant is greater. This calls for modifications in cosmological models to explain how stars, galaxies, and other cosmic structures may have formed more quickly than previously believed. On the other hand, the earlier universe measurements that yielded the lower Hubble constant point to an older and slower expanding cosmos. This scenario questions notions of dark energy and the speed at which the universe is expanding, but it also gives cosmic evolution more time. Cosmologists are compelled by these contradicting data to re-evaluate the universe's matter, and dark energy equilibrium. Universe's balance of dark energy, dark matter, and matter. A certain rate of expansion is the foundation of the lambda CDM model, the conventional model of cosmology that incorporates cold dark matter and a cosmological constant. Different expansion rates may indicate that dark energy operates differently from the cosmological constant, maybe evolving over time. Significant ramifications would follow for the model's future universe forecasts. Different values of the Hubble constant may also point to phenomena not included in the conventional cosmological model. This may include new particles, forces, or changes to gravity that call for a reworking of our most basic notions. The effect goes beyond our knowledge of cosmic inflation, the rapid expansion of the cosmos thought to have happened shortly after the Big Bang. The expansion rate is intimately related to inflationary theories. Various rates can need for whole new theories or justify various interpretations of inflation. Furthermore, impacted by these differences is precision cosmology, which tests the bounds of physical theories using precise measurements. Uncertainty in the Hubble constant affects other measurements and tests, therefore distorting our understanding of cosmic facts. More complex models and simulations are therefore required to handle a variety of expansion rates and their consequences for cosmic history. These models have to be strong enough to provide correct predictions under different assumptions while also being adaptable. Fixing these disparities involves improving our mental foundation for comprehending the cosmos as much as modifying statistics. Because new models and concepts are put out and evaluated against observable evidence, it promotes theoretical innovation. The disparities encourage the creation of new tools and methods for observation as well. Pushing the limits of technology, astronomers and physicists produce discoveries that progress other branches of research. Internationally, this problem promotes cross-border cooperation. Such basic problems need for the international scientific community to be fostered by combining data, resources, and knowledge. It emphasizes morally how crucial rigor and openness are to scientific study. Because cosmological models have so many consequences, preserving public confidence in science requires that they be founded on the most trustworthy facts and interpretations. These differences, as a useful teaching tool, show how dynamic and always changing scientific knowledge is. They demonstrate that better questions are as important to science as the search for solutions. In conclusion, there is a wide and profound influence of differences in Hubble constant measurements on cosmological theories, as well as the ethical, technical, and philosophical underpinnings of science. As such, a major goal of contemporary cosmology is to reconcile these disparities, which is essential to expanding our knowledge of the cosmos. Two of the most enigmatic and interesting elements in cosmology, dark matter and dark energy, are essential to our knowledge of the cosmos. Both, for all their significance, are still mostly unknown and are characterized by the influence they appear to have on cosmic structures and events. Because it does not emit, absorb, or reflect light, dark matter is totally opaque to existing electromagnetic radiation-based detection techniques. Its gravitational impacts on observable matter, galaxies and galaxy clusters, for example, define it. Galaxies would not be held together as they revolve at the measured speeds by the gravitational attraction of visible stuff alone. Creation and stability of cosmic structures depend critically on the function of dark matter in the cosmos. By giving galaxies and galaxy clusters enough gravitational pull to offset the expanding forces of the cosmos, it serves as their scaffolding, determining their shape and assisting in their development. Conversely, an unidentified energy type known as dark energy permeates all of space and tends to quicken the universe's expansion. Its characteristic of possessing a substantial negative pressure, which is thought to be the cause of the observed acceleration in the cosmic expansion rate, defines it. Dark matter and dark energy together make about 95% of the universe's total mass energy content. Dark energy makes up about 68% of the total, while dark matter makes up about 27%. Dark energy not only accelerates the universe's expansion but also affects its destiny. A whole picture of cosmic dynamics depends on an understanding of them because of their overwhelming dominance in the composition of the cosmos. Dark matter and dark energy, for all their important functions, are only indirectly detected. This discovery of dark matter is made possible by gravitational effects of the substance on visible matter and gravitational lensing, a phenomena of light bending. Dark energy is deduced from measurements of the universe's expansion rate made using the cosmic microwave background and distant supernova. WIMPs, or weakly interacting massive particles, are theoretical theories of dark matter. Since these particles have not been directly found, but have been postulated based on extensions of the conventional model of particle physics, cosmology and particle physics are both heavily researching them. The cosmological constant, a constant energy density filling space uniformly, to more dynamic phenomena like quintessence, which change in time and space, are examples of hypotheses regarding dark energy. The observable characteristics of dark energy and its influence on the cosmos are attempted to be explained by each explanation. Finding dark matter and dark energy is not only a quest for basic knowledge, but also a motivation for detector and observational technology progress. It strains the limits of quantum mechanics, astronomy, and particle physics. In addition, the investigation of dark matter and dark energy has important philosophical ramifications that question our ideas of what makes up matter and energy. It also puts to the test our capacity for understanding the cosmos and our scientific methods. To sum up, dark matter and dark energy define the structure, development, and destiny of the universe and are essential to cosmology. Their enigmatic character and dominating position still arouse some of the most important concerns in contemporary science and propel a multitude of studies meant to reveal the mysteries of the universe. By clarifying these elements, cosmologists and physicists not only improve our knowledge of the universe, but also improve our theories and models of it, therefore advancing the science of physics and improving our understanding of basic forces and particles. Investigating these dark elements, then, is not just about comprehending the world, but also about pushing the boundaries of human knowledge, examining the cosmos at its most basic level, and questioning our conception of reality itself. Dark matter discovery is one of the hardest problems in particle physics and cosmology. Even though dark matter has a strong gravitational pull on visible stuff, it is invisible and very hard to find by traditional techniques. since it does not interact with electromagnetic radiation. Direct detection tests, which seek to record the few interactions between dark matter particles and ordinary matter, are one of the main ways that scientists look for dark matter. To protect themselves from cosmic rays and other background noise that may impede the finding of small signals, these investigations frequently take place in remote or deep subterranean places. Attempts at indirect detection center on collecting the results of interactions between dark matter or decays that might happen in space on their own. Using gravitational lensing, a phenomena where the gravity of a massive object like a cluster of galaxies bends the light from objects behind it, astronomers can infer the presence of mass, including dark matter, even if it emits no light. For instance, if particles of dark matter may destroy each other, they might produce gamma rays, neutrinos, or other particles that can be identified by high-sensitivity equipment. Additionally, advancing the search for dark matter are theoretical physicists who have put forth novel models that forecast several kinds of dark matter particles, including sterile neutrinos or axions. Through their suggestion of possible characteristics and detection methods, these models aid in directing experimental searches. Even said, dark matter has so far escaped direct discovery that some scientists are considering even more creative approaches. For example, scientists are investigating the potential of detectable effects of dark matter on the fundamental constants of physics, could have quantifiable effects on the fundamental constants of nature. Setting possible signals apart from background noise is one of the most difficult tasks in dark matter detection. Dark matter interactions should be so faint and infrequent that it will be difficult to separate them from random oscillations in the data. In this effort, technical developments are essential. It will need more sensitive detectors and more accurate measuring methods to find dark matter. Collaboration between several scientific fields and technology is also essential. For instance, developments in machine learning and quantum computing might improve the way experimental data is analyzed, maybe identifying the faint signals that point to dark matter. Machine learning and computation could improve experimental data processing and help to identify the faint signals that might point to dark matter. A crucial aspect is also financial investment. Because dark matter interactions are so uncommon, large-scale studies need substantial financing for both long-term data collecting and processing, as well as facility building and upkeep. Equally significant are political and public backing. Without broad awareness of its significance and its influence on our knowledge of the cosmos, the quest for dark matter frequently demands a long-term commitment that can be difficult to maintain. Still, second difficulty is theoretical flexibility. Theoretical models also need to change as experiments keep defining what dark matter is not. The key to limiting down the potential properties of dark matter is this recurrent interaction between theory and experiment. Training and educational outreach. Crucially important are the upcoming generation of scientists in the methods and difficulties of dark matter detection. New ideas and viewpoints are essential as old theories are investigated and new ones are developed. The hunt for dark matter also begs philosophical concerns regarding the nature of the cosmos and our approaches to its investigation. If a sizable fraction of the mass of the cosmos is unobservable directly using any conventional techniques, what does it mean? Dark matter detection eventually calls for tenacity, creativity, and a readiness to venture into the unknown. Whether a detection is obtained, every experiment advances our knowledge of the actual properties of dark matter and, consequently, the cosmos. Among the deepest enigmas in contemporary cosmology is dark energy. It speaks of an energy form that is still unknown but is believed to pervade all of space and quicken the universe's growth. This acceleration, which was found by late 1990s studies of far-off supernovae, was totally unanticipated and has since presented serious problems to our knowledge of the universe. Dark energy implies that the cosmos is not just expanding, but doing so more quickly. The conventional wisdom was that the gravitational force of stuff would cause the universe's expansion, resulting from the Big Bang to progressively slow down contradicts this acceleration. At around 68% of the universe's total energy density, is dark energy. Even if it rules, conventional methods cannot see it. It interacts mostly with the observable cosmos by gravitational forces and does not emit, absorb, or reflect light. Light, and mostly communicates with the visible cosmos by means of its gravitational forces. The cosmological constant, a notion Albert Einstein added to his general theory of relativity, is the most generally acknowledged explanation for dark energy. This constant denotes an energy density that fills space uniformly and is constant both in space and time. According to a different idea, dark energy is dynamic and changes with place and time. The notion of quintessence, a field that fluctuates across the universe and influences its expansion rate differently at different times and locations, is introduced by this hypothesis. Dark energy is mostly supported by observations of the universe's expansion rate made with distant supernovae, the large-scale structure of the cosmos, and variations in the cosmic microwave background radiation. Understanding dark energy is hampered by its great weakness. It is very hard to investigate and measure using laboratory-based tests, even though it dominates the energy density of the universe since its effects are only apparent on cosmic scales. Deeply rooted effects of dark energy affect basic physics as well as cosmology. It questions our grasp of gravity and the general dynamics of the cosmos, implying that Einstein's theory of general relativity may need to be modified. Solving the riddle of dark energy could reveal fresh information about the destiny of the cosmos. Depending on its characteristics, the cosmos could start to constrict, slow down, or expand endlessly. Many techniques are now being used by researchers to try to understand the nature of dark energy. These comprise thorough surveys of galaxies and galaxy clusters, investigations of the cosmic microwave background, and the distribution of dark energy seen by gravitational lensing. Projects like the Dark Energy Survey and the impending Euclid task by the European Space Agency are intended to map the universe's expansion history and structure more precisely than ever before. Theoretical physicists are also investigating the possibility that dark energy might be linked to other unresolved problems in physics, such as the nature of dark matter and the unification of quantum mechanics with general relativity. Sustaining research into dark energy depends on financing and public attention. The size and complexity of the tests required to address these issues call for a significant, long-term commitment. Explanation of the importance of dark energy to the general population also depends on educational initiatives. Exploring basic issues about the nature of space and energy is just as important to comprehending dark energy as it is to increase our understanding of the universe. In the end, solving the riddle of dark energy is one of the most fascinating astronomy and physics frontiers, as it promises to change our knowledge of the cosmos and maybe result in new theories that might solve other cosmic riddles. Many competing ideas and fresh study paths have surfaced in the effort to comprehend the cosmos, questioning accepted models and putting forward fresh explanations for the observable cosmological occurrences. Many times, these ideas deal with the oddities and disparities that come from conventional frameworks like as the lambda cold dark matter hypothesis. One well-known substitute theory is MOND, or modified Newtonian dynamics. This idea offers modifications to Newton's equations for extremely low accelerations, as those observed at the outer margins of galaxies, to explain the spinning speeds of galaxies without using dark matter. Though he has some difficulty describing larger-scale formations like galaxy clusters, Mond has had some success explaining some cosmic occurrences. An alternate strategy is the modified gravity theory, which proposes modifications to general relativity as stated by Einstein. These changes seek to explain, without the need for dark matter or dark energy, the universe's accelerating expansion and galaxy behavior. Under this heading are ideas such as scalar tensor theories and FR gravity. Cosmology is likewise illuminated by string theory, a more general theoretical framework. It implies that the basic particles we see are tiny, vibrating strings rather than point-like dots. Regarding the early cosmos, string theory provides a foundation for a unifying theory of physics and may explain inflation. Another important field of theoretical study aiming at quantifying gravity is loop quantum gravity. Particular attention is paid to comprehending the Planck scale fabric of space-time, which may provide light on the circumstances of the early universe and provide knowledge of the places where general relativity fails, including within black holes. A competing idea in cosmology is the multiverse. It raises the possibility that our universe is only one among several with unique physical rules. Advanced computer models enable researchers to simulate the evolution of the universe under different conditions and with different theoretical assumptions. This helps in understanding the formation of large-scale structures and the effects of dark energy and dark matter, and it may also explain the fine-tuning of some physical constants in our universe. The James Webb Space Telescope and the Event Horizon Telescope are two of the new equipment causing an era of observational cosmology to flourish. Higher resolution and more sensitive measurements made possible by these technologies enable more thorough testing of alternative theory predictions. Cosmological study and particle physics experiments cross, as seen by the Large Hadron Collider experiments. These tests could find new particles that make up dark matter or offer proof for theories like supersymmetry, which is intimately connected to string theory. A fresh window into the universe has been made possible by gravitational wave astronomy, which enables the study of processes that are invisible to electromagnetic radiation. This area may challenge ideas about the basic character of space and time and offer important insights about the early cosmos. Astrology is seeing a growing importance of machine learning and artificial intelligence. Large amounts of data are sifted through by these technologies to find patterns and abnormalities that may be indicators of new physical occurrences or proof for competing ideas. Integrating concepts from information theory, statistical mechanics, and quantum mechanics, cosmology also gains from multidisciplinary study. Creative methods to resolving cosmological mysteries, including the nature of the anomalies in the cosmic microwave background, may result from this cross-pollination. Increasingly, theoretical physicists are investigating the cosmic scale consequences of thermodynamics and entropy. More understanding of the cosmic destiny and the arrow of time may result from this study. In cosmology, study is conducted on the extremely tiny sizes of the early cosmos as well as the enormous scales of galaxies and clusters. New physics that closes the gap between quantum mechanics and cosmology may be revealed by understanding the quantum features of the early cosmos. And last, one of the most active fields of science is still cosmology, even as we investigate these other hypotheses and new study paths. Every theory pushes the limits of our knowledge about the universe by not only providing a possible answer to current issues, but also by posing new ones. Fundamental components of cosmology, its topology and form, have been described by a number of hypotheses. One of the most important questions is attempted to be answered by these ideas. How is the cosmos organized generally? The flat universe hypothesis is one of the main theories. It postulates that the universe has a large-scale zero curvature, like a flat sheet. Measuring the cosmic microwave background radiation supports this idea, which also fits with the broad predictions of inflationary theories. An alternative idea suggests a closed universe, according to which the cosmos has a positive curvature akin to that of a sphere. According to this idea, the cosmos is finite yet unbounded, and you would ultimately return to your starting position if you traveled far enough in one way. On the other hand, an open universe hypothesis contends that the cosmos has a saddle-shaped negative curvature. According to this hypothesis, the universe is limitless in size and will continue to grow at an accelerating pace forever. The cosmos's structure can be more intricate than straightforward geometric representations as well. Several theories postulate a multi-connected world in which spaces are multiplicatively linked at various sizes. This could indicate that the cosmos has a more complex structure that permits strangely shaped loops back on themselves. Another fascinating theory is the toroidal universe, which postulates a donut-shaped topology for the cosmos. This idea permits a fascinating feature whereby going straight in some directions may ultimately bring you back to where you started. A 12-faced polyhedron, the dodecahedron, is suggested to represent the form of the universe by the Poincare dodecahedron space theory. A couple cosmic microwave background data that suggest a certain sky pattern of repeating serve as the impetus for this idea. Some cosmologists investigate the potential of a fractal structure in which matter distribution on enormous sizes replicates itself at smaller scales. A homogeneous and isotropic cosmos as observed in the cosmic microwave background is questioned by this hypothesis. Concepts relating the form of the cosmos to quantum events that took place in the very early universe are introduced by quantum cosmology. Many times these theories produce situations in which quantum fluctuations affect the universe's topology, resulting in a dynamic and maybe shifting structure. Additionally, offering models for the form of the cosmos, string theory implies that the seemingly four-dimensional world is really a representation of higher dimensions space. These models allow the additional dimensions to be complicatedly compacted in ways that affect spacetime's features. The holographic principle in the field of speculative theories implies that any piece of information contained in a volume of space may be represented on a boundary to such space. This idea suggests a very different topology of the cosmos, in which our sense of volume is only projections of data stored on a far-off 2D surface. Originating in string theory, the Eque-Parodic model postulates that our three-dimensional world is one of two branes divided by a higher-level space. In this idea, the interactions between these branes greatly impact the shape of the universe. A notion of discrete topology at the tiniest scales, made up of microscopic loops woven into the fabric of spacetime, is introduced by loop quantum gravity. The Planck scale granularity of space may have a possible explanation provided by this idea. Applications of chaos theory have been made to cosmology to investigate whether minute variations in the early universe's topology or form would have resulted in appreciable variations in the structure of the cosmos on larger scales. This method investigates how sensitively the universe's outcome is to its starting circumstances. The multiverse idea adds to the debate on the form of the cosmos by speculating that our world may be only one bubble inside a bigger cosmic foam. Every bubble in this foam could have a unique physical law and form. In the end, much research and discussion surround the actual structure and form of the cosmos. Every theory adds special data and forecasts to our developing knowledge of the universe. These many hypotheses highlight how rich and complicated cosmology study is, as scientists explore the deepest mysteries of the cosmos using both mathematical models and empirical evidence. The foundation of cosmological theory testing and universe refinement is observational evidence. Every bit of information adds important details and has a big impact on our universe models. Among the most important cosmological observations is the cosmic microwave background radiation, or CMB. Discovered in the middle of the 20th century, this faint light from the Big Bang offers a window into the cosmos at its earliest age of 380,000 years. The Big Bang scenario has been supported, and the composition and dynamics of the early cosmos studied in large part by the uniformity and small changes in the CMB. Rotation curves of galaxies are even another important piece of observational data. Dark matter has been deduced by astronomers from examining the rotation rates of galaxies at different distances from their centers. The curves indicate that galaxies have a lot more mass than observable matter alone can explain. When the gravity of a large object bends the path of light traveling close to it, a phenomenon known as gravitational lenses results. Because intervening dark matter bends light from far-off galaxies, indicating its existence even if it cannot be directly observed. This phenomenon has been used to map the distribution of dark matter in the cosmos. Distant Type E supernova observations led to the discovery of the universe's expanding at an accelerating rate. The universe's expansion is speeding due to dark energy, as concluded by these studies, which indicated that supernovae were dimmer than anticipated and hence further away than previously believed. Massive galaxy surveys have shown the universe's large-scale structure to be a web-like structure made up of galaxy clusters, filaments, and voids. Models of cosmic evolution and the function of dark matter informing the cosmos have been developed and tested in great part because to this structure. Redshift surveys have measured galaxy redshifts to produce a three-dimensional picture of the cosmos across appreciable regions. These studies help us to comprehend the distribution of galaxies and their history throughout time, as well as the magnitude of the universe's expansion. A standard ruler for gauging the expansion of the cosmos is made available by the discovery of the baryon acoustic oscillations. These oscillations provide an approach to determine the size of cosmic structures apart from supernovae and the CMB, since they are maintained in the distribution of galaxies. Age limitations of the cosmos are provided from observations of the oldest stars and galaxy formations. Astronomers may verify theories of cosmic development and the timing of significant cosmic events by figuring out the age of the oldest star populations. Gravitational wave discovery recently has created a new portal into space. Through these space-time ripples brought on by catastrophic events like black hole mergers, theories of gravity may be directly tested and otherwise undetectable objects and phenomena studied. Specifics regarding the magnetic fields of the cosmos and the function of energetic particles and processes have been made public via radio astronomy. The electromagnetic environment and dynamics of the cosmos are filled in part by research of radio emissions from galaxies and other cosmic sources. Understanding the processes taking place in the universe's most intense settings is made possible by studying cosmic rays, high-energy particles that impact the Earth's atmosphere. The nature of high-energy astrophysical events and the source of these particles may be inferred from observations of cosmic rays. Celestial body spectrum analysis facilitates knowledge of the physical parameters and chemical makeup of stars and galaxies. Astronomers can deduce the existence of elements and compounds by dissecting light into its constituent wavelengths, therefore exposing the mechanisms governing star creation and development. Dust clouds that block visible light have been broken through using infrared astronomy, enabling the study of star formation in molecular clouds and galaxy cores, and revealing processes that are not apparent to optical observatories. Higher energy processes that are not visible from the ground because the Earth's atmosphere blocks most ultraviolet light are studied in ultraviolet astronomy. Specifics regarding the intergalactic medium and the hottest stars have been made known by observations in this band. Every observable piece of data not only confirms or refutes current hypotheses, but also poses fresh queries that propel cosmic science forward. By use of these findings, cosmologists assemble the background and organization of the universe, therefore revealing its deepest mysteries. Theoretical difficulties and unanswered issues abound in cosmology. Each pushes the boundaries of scientific research and expands our knowledge of the cosmos. Many times these difficulties center on expanding current ideas to account for new evidence or reconciling observed occurrences with accepted theories. The nature of dark matter is one of the main theoretical problems in cosmology. Even if dark matter is a fundamental component of the contemporary cosmological theories that explain the gravitational effects in galaxy rotation and clustering, its precise composition is yet unclear. Scientists still can't figure out what makes up black matter. Understanding dark energy and its part in the universe's expansion is another major problem. The Einstein introduced cosmological constant, which was subsequently linked to dark energy, is compatible with general relativity mathematically, but provides no dynamic explanation for the way, if any, that dark energy varies with time. Among the biggest theoretical challenges is still the combination of general relativity with quantum mechanics. The extremely small and the very huge are governed by these fundamental foundations of physics. Still, one of the biggest theoretical obstacles is quantum mechanics and general relativity. While they do not smoothly combine, these fundamental pillars of physics control the extremely tiny and the very enormous, respectively. One of the key objectives of theoretical physics is to develop a theory of quantum gravity that may unite these fields. Galaxy distribution and the homogeneity of the cosmic microwave background are explained by the inflationary model of the early universe, which postulates a rapid expansion soon after the Big Bang. Still unanswered are the precise causes of inflation and its termination. Considerable theoretical and philosophical problems are raised by the potential existence of a multiverse. How do we start to investigate if there are several worlds, each maybe with its own set of physical laws? The fine-tuning issue asks why nature's constants are exactly positioned to support life. Is our cosmos by accident, necessity, or some anthropological principle that demands more philosophical and scientific investigation, especially suitable for life? Furthermore, posing serious theoretical problems is the issue of the universe's starting circumstances. With the particular characteristics and dimensions listed, why did the Big Bang occur? This issue questions our grasp of causation and existence and lies on the line between physics and metaphysics research. An important area of ongoing study is the reconciling of observable anomalies in the cosmic microwave background radiation with the conventional model of cosmology. These irregularities can represent statistical abnormalities or indications of novel physics that need to be included into cosmological models. The observable imbalance between matter and antimatter in the cosmos, known as baryon asymmetry, presents theoretical physics with a puzzle that has to be solved. Without this kind of process, matter-dominated universe as we know it cannot be adequately described. Deeply linked to the characteristics of dark energy, the future of the cosmos is yet unknown. Should dark energy stay constant, the cosmos may keep expanding indefinitely. Should that alter, though, the cosmos may someday implode or come to some other tragic end. Another difficulty is comprehending the tiniest sizes of the cosmos and how they affected its early evolution. Though it is thought that the large-scale structure of the world seen today originated from quantum fluctuations during the Big Bang, it is still challenging to relate these quantum origins to the cosmological results. We still don't quite understand how black holes, particularly supermassive black holes at galaxy centers, fit into cosmic development. Though their ultimate influence on galaxy formation and development is still being investigated, these enormous objects have a tremendous effect on their surrounds. It is yet unclear how galaxies develop and the precise mechanisms by which matter first gathered to create stars and galaxies. A difficult conundrum is presented by the way that gas dynamics, gravity, and dark matter interact in these processes. Massive computer capacity and a deep grasp of physics at all scales, from the quantum to the cosmic, are necessary to simulate the cosmos with enough precision to test cosmological ideas against observations. The complexity of the cosmos and the dynamic character of cosmology, as a discipline continuously pushing the limits of human knowledge, are both highlighted by each of these theoretical difficulties and unanswered problems. As these issues are investigated, fresh paradigms and more profound understanding of the universe open up. Albert Einstein's 1915 theory of general relativity depicts gravity as a curvature of space-time brought about by mass and energy rather than as a force between masses, as Isaac Newton's theory had proposed. General relativity holds that the geometry of space-time is altered by the existence of matter, and this curvature determines the motion of matter and the propagation of light. Early in the 20th century, physics at very tiny scales, where particles and waves display behaviors that defy conventional physics, was the subject of quantum mechanics. Wave-particle duality is the fundamental idea of quantum physics, according to which every particle or quantic object can have characteristics of both waves and particles. The idea of quantum states is presented, and wave functions that encode the probability of all conceivable locations, energies, and other characteristics of a particle characterize them. Reliance on the metric tensor, a mathematical construct that characterizes the curvature of space-time close to mass and energy, is one of the main features of general relativity. This tensor is related to the energy momentum tensor, which describes the density and flux of energy and momentum in spacetime via the Einstein field equations, the general relativity equations. Werner Heisenberg's uncertainty principle is another feature of quantum mechanics. It says that some pairings of attributes, such as location and momentum, cannot be correctly measured at the same time. Less precisely, the other property may be controlled or determined the more exactly one attribute is measured. The equivalency principle, another tenet of general relativity, holds that the resistance to motion in reaction to a force and the gravitational mass, which defines the intensity of a gravitational field, are comparable. That establishes the equal resistance to motion in reaction to a force. The fact that, in a gravitational field, things fall at the same rate independent of their mass is an example of this principle. The superposition principle in quantum mechanics holds that a physical system exists concurrently in part in all of its theoretically conceivable states. When measured, nonetheless, the findings relate to one of the many configurations. Schrödinger's cat, the well-known thought experiment, exemplifies this idea. A deterministic theory, general relativity predicts, given starting conditions, a single unique future. The rules of physics and the starting conditions of the items inside the cosmos define their motion and the evolution of the universe in full. In contrast, quantum mechanics is essentially probabilistic, that is, it forecasts probability distributions of results rather than definite ones. This feature of quantum physics exposes a basic unpredictability in the natural processes at the tiniest possible sizes. Furthermore, implied by the general relativity theory are the presence of objects like black holes, which are spaces where the space-time curvature is so great that not even light can escape. It also forecasts gravitational waves, light-speed propagating disturbances in space-time curvature. In turn, quantum mechanics presents the idea of quantum entanglement, a physical phenomena that arises even in cases when particles are separated by a great distance, when pairs or groups of particles are produced, interact, or share spatial proximity in a way that makes the quantum state of each particle indefinable from the state of the others. Among the biggest problems in contemporary physics is still the unification of quantum mechanics and general relativity. The description of gravity as the consequence of space-time curvature provided by general relativity is essential for comprehending large-scale phenomena, including planet orbits, galaxy dynamics, and the evolution of the universe itself. The two theories operate on very different scales and under very different conditions. Attempts to reconcile them in a single theoretical framework have led to the development of theories such as string theory and loop quantum gravity. In the meanwhile, atom structure, chemical bond nature, and condensed matter characteristics are all explained by the interactions and properties of atoms and subatomic particles, which are all dependent on quantum mechanics. Both theories have a great deal of applications and have been well tested. A key component of astronomy, general relativity, is necessary for precise satellite placement and the GPS technology that depends on them. Most of today's technology, including computers, lasers, and nuclear power, was made possible by quantum physics. Theoretical physics is still focused on comprehending and maybe combining these fundamental ideas, which offer not only more understanding of the nature of reality, but also open the door for next technical developments. Two fundamentals of contemporary physics, general relativity and quantum mechanics, are both quite successful in their respective fields. When it comes to explaining the cosmos under extreme circumstances, including as seen close to black holes or in the early stages of the Big Bang, they are essentially incompatible. A geometric characteristic of space and time, or space-time general relativity, developed by Albert Einstein, explains gravity. It describes how the curvature of space-time, which governs mass motion, is determined by mass and energy. Numerous tests and observations, including the gravitational wave detection and the bending of light by gravity, have verified that this theory operates very well at enormous scale. Conversely, the tiniest sizes of atoms and subatomic particles' energy levels are addressed by quantum mechanics. It presents ideas such as wave-particle duality, in which particles have characteristics of both waves and particles, and the uncertainty principle, according to which some pairs of attributes, like as momentum and location, cannot be simultaneously known to arbitrarily high accuracy. Because general relativity is a classical theory in which objects have fixed attributes and states determined by deterministic rules that forecast particular results, the incompatibility results. But by nature, probabilistic, quantum physics forecasts the likelihood of many events rather than definitive ones. A key problem is that, whereas quantum physics implies that space and time should be discrete and quantized at the lowest scales, general relativity predicts that they are smooth and continuous. The gravitational field is therefore difficult to conceptually and mathematically define in quantum terms. Calculations of the gravitational field attempting to use quantum mechanics frequently produce what are known as infinities, which are physically absurd. The way quantum field theories manage very high energy and small distances, something that is typical in the domains where both gravity and quantum effects are strong, is the reason these infinities emerge. A further instance of their conflict is the time problem. A backdrop parameter in quantum physics, time is a constant, unchanging stage on which particles travel. But according to general relativity, time varies across the cosmos and is dynamic, impacted by gravity. Furthermore, general relativity predicts a point where density becomes infinite and space-time curvature becomes infinite under situations similar to the singularity at the heart of a black hole. Based mostly on the uncertainty principle, quantum physics disputes the existence of such solitary points with well-defined positions. Moreover, general relativity states that spacetime is dynamic and molded by energy and matter, which creates a basic contradiction concerning the nature of spacetime itself. Quantum mechanics needs a stable spacetime background to determine the characteristics of the particle. This inconsistency implies that one of the hypotheses is lacking at least. It indicates the necessity of a theory of quantum gravity capable of integrating these two fundamental theories into a single framework applicable to all energies and scales. Two attempts at a single theory are loop quantum gravity, which attempts to quantify spacetime itself, and string theory, which postulates that the point-like particles of particle physics are really one-dimensional strings. Among the deepest and most basic problems in theoretical physics is the incompatibility of these two ideas. It not only calls into question our conception of the cosmos, but also motivates a large portion of cosmological and particle physics study. Approaching a comprehensive and coherent explanation of the basic forces of nature requires resolving this problem, which may provide new light on the early universe, black holes, and perhaps even the ultimate destiny of the universe. Practically speaking, until a single theory is created, scientists have to decide when to use general relativity or quantum mechanics. General relativity is enough for most commonplace applications involving gravity on Earth or in the solar system. Quantum mechanics is employed when dealing with atoms and particles. One of the main goals of theoretical physics is still to close the gap between general relativity and quantum mechanics, which motivates new concepts, methods, and experiments meant to explore the universe's fundamentals. Among the biggest problems in contemporary theoretical physics is to develop a theory of quantum gravity. It is putting the macroscopic universe, described by general relativity, and the tiny world, governed by quantum mechanics, together. The need to address the basic contradictions between these two pillars of physics and to have a better knowledge of the cosmos drive the search for such a theory. String theory is one of the main efforts in this approach. It holds that particles are one-dimensional strings rather than zero-dimensional spots. Different particles correlate to the various frequencies at which these strings vibrate. The reason string theory appeals is that it offers gravity in its framework and may bring all of nature's basic forces under one roof. Combine under one roof all of nature's basic powers. An additional important method that aims to quantify space itself is loop quantum gravity. It implies that space is woven into a fabric rather than being continuous. A key obstacle in creating a theory of quantum gravity is the dearth of experimental evidence. The Planck scale, which is roughly 10 dvr to 35 meters far beyond the reach of current or foreseeable experimental technology, is where the singularity and infinite density predicted by general relativity in black holes and the Big Bang are expected to become significant. This complicates empirical data-based theory refinement and prediction testing. Furthermore, loop quantum gravity and string theory need sophisticated mathematics and provide hypotheses in situations that are challenging to link to observable physics as well as to verify. For example, the granular structure of space proposed by LQG has not yet received empirical validation, and additional dimensions proposed by string theory are not immediately observable. The task of guaranteeing that any proposed theory of quantum gravity reduces to general relativity in the macroscopic limit and to quantum mechanics in the microscopic limit also falls on theoretical physicists. The correspondence principle is the need that guarantees the new theory honors what has already been investigated and known. Exploring the characteristics of black holes is another endeavor in this area, as they represent the convergence point of the effects of general relativity and quantum physics. Any reasonable theory of quantum gravity has to deal with the information paradox, which concerns what happens to information that falls into a black hole. One new possible avenue for verifying quantum gravity ideas is provided by gravitational wave astronomy. A unique approach to collect empirical data pertinent to quantum gravity theories is to detect the quantum components of gravitational waves, which may reveal information on the quantum character of space-time itself. Philosophical ramifications of the creation of a quantum gravity theory include challenges to our conceptions of causation, reality, and the nature of space and time. Together with the mathematical and experimental problems, these conceptual ones need to be solved. A theory of quantum gravity, according to many theorists, could need the development of previously undeveloped mathematical notions and instruments. Combining such essentially distinct ideas might be too difficult and call for a revolution in mathematical physics. A holographic concept developed from string theory implies that every bit of information in a volume of space may be recorded on its border. The bulk of space-time and its border are treated as two expressions of the same physical reality in emerging approaches to quantum gravity that are motivated by this idea. Another theoretical difficulty is the cosmological constant problem, which results from the difference between the values of dark energy that are computed and measured. Why the cosmological constant is so tiny is still one of the greatest physics puzzles, and a theory of quantum gravity may help to explain it. A more basic theory that does not mainly concentrate on gravity, but rather derives it as an emergent phenomena from deeper quantum mechanical principles is being investigated by some scientists. Furthermore, illuminating the circumstances of the cosmos at the instant of the Big Bang, a theory of quantum gravity may also provide light on how the universe started and developed, and perhaps explain what occurred before it. Finally, the goal to combine all known forces, including gravity, under a single theory still motivates basic physics research. In addition to stretching our creativity and technical prowess, this endeavor broadens our perspective on the cosmos. These attempts and difficulties highlight the depth and complexity of the search for a theory of quantum gravity. It's a search that unites the most profound knowledge of the universe, from the smallest particles to the vast dance of galaxies, all connected by the need to comprehend reality itself. Galaxies, all constrained in their understanding of the nature of reality itself, specifically designed to describe galaxy dynamics without using dark matter, modified Newtonian dynamics, or MUND, is an alternative theory to general relativity and Newtonian gravitation. In the very low accelerations typical of the outer regions of galaxies, MOND suggests a modification of Newton's second rule of motion. MOND claims that the gravitational force felt by a star on the periphery of a galaxy does not follow the inverse square law. Rather, it rises above Newtonian predictions, giving the force required to explain the observed flat rotation curves of galaxies without the need for dark matter. galaxy curved without the requirement for dark matter. Tensor vector scalar theory, or TVS, is an extension of a MOND developed to include MOND-like phenomena into a relativistic gravitational theory. TVS extends the tensor field of general relativity by adding vector and scalar fields, a development of Jacob Bekenstein. With this theory, galaxy dynamics should be explained, and cosmological phenomena, like gravitational lensing and the cosmic microwave background, should be consistent under a single theory devoid of dark matter. Salutations. Gravity is a kind of modified gravity theory that extends general relativity by changing the theory's Lagrangian to be a function of the Ricci scalar RR rather than merely being proportional to it. Different predictions at cosmic scales may result from changes FR theories bring to the gravitational action. These changes are intended to offer substitute explanations for various cosmological and astrophysical phenomena, as well as the rapid expansion of the universe without the necessity of dark energy. By arguing that variations to the rules of gravity, rather than the existence of invisible stuff, might explain the anomalies seen in galaxy rotation curves, MOND, and its relativistic version, TVS, question the dark matter paradigm, particularly in the context of elucidating the intricate dynamics of individual galaxies. These hypotheses have generated a great deal of discussion and investigation. MOND, however, struggles at bigger scales, like in galaxy clusters where more unseen mass is required even with MOND's altered dynamics. Some scientists have thus begun to think about hybrid theories that include some kind of dark matter in addition to changes to gravity. Even if TVS fixes some of the problems with MOND at cosmic scales, its intricacy and the incorporation of new fields whose physical nature is yet unknown have drawn criticism. Notwithstanding these objections, TVS continues to be a major step toward the creation of logical substitutes for dark matter. Cosmological consequences of gravity theories have been thoroughly investigated. These ideas are very interesting because they can change the evolution of structure in the universe and imitate the cosmological constant at large scales, maybe producing observable fingerprints that deviate from general relativity plus dark matter predictions. The mathematical elegance and, in certain cases, simplicity of FR gravity are two of its most attractive features. A rich framework for elucidating cosmological phenomena with fewer assumptions about the contents of the cosmos may be produced by just changing the functional form of FR. These hypotheses are tested by exact astronomical measurements. Important for MAND and TVS are gravitational lensing data and measurements of star and gas migration in galaxies. Important for FR gravity are cosmological measurements including the large-scale structure, high redshift supernovae, and cosmic microwave background. None of these ideas, for all their promise, have yet offered a whole and widely acknowledged answer to the issues they seek to address. Everyone has advantages and effectively explains some empirical occurrences, but it also has flaws and problems that call for further evidence and theoretical development. Theoretical physics and astrophysics are active fields of debate and study concerning MOND, TVS, and FR gravity. They stand in for a larger scientific effort to investigate deviance from the dark matter and dark energy-dominated conventional cosmological paradigm. In scientific investigation, these theories emphasize the need of maintaining an open mind. These alternative ideas are continuously honed and either acquire support or are ruled out as new evidence becomes available and our theoretical and computational capabilities advance. Investigating these options is not only academic. Deep ramifications for our knowledge of the cosmos follow. They present alternative theories on gravity and the dynamics of the universe and question the accepted elements of the cosmos. Finally, MOND, TVS, and FR gravity are significant elements in the current debate and study of the basic forces of the universe. It is yet unclear if any of these hypotheses will eventually supersede or materially alter the existing understanding of dark matter and dark energy. In the end, The worth of looking into these ideas is found in their ability to explain as much as in the fresh problems and study paths they spur, which add to the dynamic and always changing field of cosmological science. Theoretical reasons for investigating competing gravity theories are found in the unsolved problems in cosmology and general relativity, especially the enigmas of dark matter and energy. To explore whether changes to our present understanding of gravity can account for cosmic evidence without the requirement for unidentified, enigmatic materials, scientists suggest alterations. One important driving force is the incapacity of the lambda cold dark matter model to explain some astronomical data without assuming the presence of dark matter and dark energy. Theories that alter gravity instead have been prompted by the inability to directly observe these components, which account for around 95% of the total energy density of the cosmos. The issue of galaxy rotation curves, which defy Newtonian gravity's predictions unless extra mass, supposed to be dark matter, is incorporated, provides even another theoretical justification. Rather than using invisible mass to explain these curves, some theories of gravity, including modified Newtonian dynamics, MOEND, try to modify the laws of gravity. An alternative reason is the universe's rapid expansion as shown by observations of far-off supernovae. It implies that the growth is being propelled by dark energy, a kind of repulsive energy. FR gravity and other alternative gravity theories look at whether this acceleration may be explained without dark energy by alterations to Einstein's field equations. Wanting a more cohesive physics is another source of theoretical motives. The goal of gravity modifications is to provide a theory that can explain general relativity and quantum mechanics, therefore revealing new information about quantum gravity. Constrictions are essential for observing the feasibility of these hypotheses. One important restriction results from the exact observations of the cosmic microwave background radiation, which provides comprehensive information about the circumstances of the early universe and firmly backs the conventional cosmological model. These observations of gravitational lensing offer even another crucial test. Every workable gravity theory has to explain the bending of light by enormous objects like galaxies and galaxy clusters. Differential lensing data may frequently exclude or restrict alternative gravity theories that do not need dark matter. Constraints are likewise imposed by the vast structure of the cosmos as seen by galaxy surveys. Tests of several gravitational theories versus the conventional model may be done by looking at how gravity functions on vast scales through the distribution of galaxies and their clustering features. Tests of the solar system place very severe limitations on modified gravity theories. Under the circumstances of our solar system, where general relativity has been verified to great accuracy by measurements such as the precession of Mercury's orbit and the deflection of light by the Sun, any new theory must reduce to Newtonian gravity. Furthermore, acting as observational constraints are binary pulsar systems, which offer a natural laboratory for evaluating general relativity. Any competing theory is challenged by the near match between the energy loss through gravitational waves seen in these systems and the predictions of general relativity. Theories can be constrained in novel ways by the behavior of black holes and neutron stars, especially as seen by gravitational wave astronomy. It can be difficult for some modified gravity theories for the merger rates, mass distributions, and waveform signals from these events to match observable data. A cross-check against theoretical expectations is provided in cosmology by the age of the universe determined from various observations. Every revised theory of gravity needs to explain the universe's age and observable expansion history in accordance with data from supernovas, cosmic microwave background, and other astrophysical clocks. Constrained are also the thermal history and nucleosynthesis observations of the early cosmos. The proper amount of light elements, notably helium and lithium, as predicted by Big Bang nucleosynthesis, must still be possible in gravity theories that change the dynamics of the early universe. And further observational test is provided by the integrated Sachs-Wolf effect, in which photons from the cosmic microwave background gain energy by traveling through potential wells created by large-scale structures. Different gravitational behaviors anticipated by other theories may be hinted at by variations in this phenomenon. Alternative gravity theories are ultimately shaped by the interaction between theoretical objectives and empirical limitations. Every observation functions as a jigsaw, and each new hypothesis needs to fit in with the others to offer a logical and scientifically supported picture of the cosmos. These initiatives not only test our present knowledge, but also motivate the basic search for a more thorough and all-encompassing explanation of gravity. According to the multiverse idea, there may be many worlds, each perhaps controlled by distinct physical rules and constants. This notion of a huge landscape of potential universes originates from several branches of theoretical physics, such as string theory and cosmic inflation theories. The multiverse notion has one basis in inflationary theory, which postulates a rapid expansion of the early cosmos. This idea holds that certain parts of space may stop expanding at different periods, creating a space-time bubble that might operate as an independent universe with its own physical rules and constants. Different periods resulted in a space-time bubble that may have its own physical rules and constants. By its range of solutions, string theory bolsters the multiverse idea even more. It raises a plethora of potential universe states, each of which corresponds to various ways the additional dimensions put forth by the theory may be condensed. Every distinct state may, in theory, stand in for a distinct world inside a larger multiverse. The idea of a multiverse questions the conventional cosmological belief that the universe as it is visible is all that exists. Scientists have been baffled by the appearance of some physical constants being precisely calibrated for the birth of life for decades. If our universe is only one among many, this may help to explain why. Philosophy-wise, the multiverse begs the issues of what reality is and where we fit in it. It implies that our universe, being one of many in a far bigger cosmos, may not be as unique or extraordinary as we previously believed. Being one of a huge number of universes in a much bigger cosmos makes the multiverse idea difficult, if not impossible, to prove scientifically. Because direct testing of the multiverse idea is challenging, if not impossible, it is contentious scientifically. As humans are unable to detect these other worlds, the hypothesis is still hypothetical and mostly depends on theoretical physics assumptions rather than actual observations. Predictability is a key consequence of the multiverse for cosmology. The notion that there are universal rules of physics that apply everywhere and always may be called into doubt if physical laws might differ from one universe to another. Furthermore, affected by the multiverse is the idea of starting circumstances in cosmology. With numerous worlds existing where such conditions never occur, the fine-tuning of conditions required for life in our universe may not be as unlikely as previously believed if each universe inside the multiverse can have distinct starting conditions. With the multiverse, anthropological reasoning, which has been employed to explain the precise tuning of physical constants in our universe, gains new perspective. According to this logic, we notice these criteria only because we could not live in a universe where they were not satisfied. A possible approach to get proof for the existence of other universes is suggested by some theorists who suggest that collisions between these universe bubbles might leave detectable fingerprints in the cosmic microwave background radiation of our universe. Additionally, related to the multiverse idea is the study of black holes. According to certain hypotheses, every black hole may give birth to a new reality that is maybe distinct from the original world, therefore extending the multiverse even further. As it deals with things, other worlds, that we could never be able to see or interact with directly, the idea of the multiverse pushes the bounds of cosmology into the domain of metaphysics. This begs important concerns regarding the standards for scientific hypotheses, namely, the need for empirical testability. A position for the multiverse in quantum mechanics is found in the many worlds interpretation, which holds that all conceivable results of quantum measurements are physically realized in discrete, non-communicating branches of the multiverse. This view has all outcomes happen in distinct universes, therefore removing randomness from quantum theory. The multiverse idea is still a lively field of theoretical study, even with its difficulties in being proven. It motivates fresh approaches to consider basic cosmological issues and the nature of scientific ideas, which may result in fresh discoveries about the cosmos. Whether the multiverse hypothesis can eventually go from a theoretical concept to a testable scientific framework will rely on the creation of new theories and technologies that can recreate settings that mimic multiverse dynamics or deduce the existence of other worlds. The multiverse's deep consequences for comprehending the universe are reflected in the ongoing discussion it sparks in many fields. Offering a structure that tries to bring general relativity and quantum physics together, string theory is a strong contender for a single theory of the fundamental forces of existence. This hypothesis first appeared in the late 20th century as a possible explanation of everything that would use the dynamics of microscopic vibrating strings to describe all particles and basic interactions. The fundamental thesis of string theory is that the particle physics point-like particles are one-dimensional strings rather than zero-dimensional points. The vibrations of these threads at different frequencies correspond to various particles, and they can be open or closed loops. Thus, distinct particles are represented by their vibrations at various frequencies. Much like various musical notes arise from different vibrations of guitar strings, the mass and charge of a particle rely on the vibration of the string. Uniquely, string theory proposes that gravitons, fictitious quantum particles that mediate gravitational forces, emerge spontaneously inside the theory as modes of string vibration. One of the main problems in theoretical physics is addressed by this integration, developing a quantum theory of gravity. String theory is notable for requiring more dimensions. Although there are 3 spatial dimensions and 1 time dimension in our known cosmos, string theory suggests that there are more hidden dimensions that are compressed at scales too tiny to be seen by present technology. The mathematical soundness of the theory depends critically on these additional dimensions. Furthermore, introduced by string theory, is the idea of supersymmetry, a put-forth symmetry between the 2 fundamental particle classes, fermions, which comprise matter, and bosons, which carry forces. According to supersymmetry, every particle has a superpartner with comparable characteristics, but a half a unit of spin different. Among the theoretical issues this symmetry helps to answer is the hierarchy problem about the mass of the Higgs boson. The possibility of string theory to clarify the fine structure of black holes is another significant feature. Resolving various contradictions in black hole physics as described by general relativity, string theory provides explanations for black holes' entropy and temperature that comply with the principles of thermodynamics. Black holes are seen as states of extremely excited strings rather than as points. Additionally, suggested by string theory are the presence of branes, multidimensional objects on which strings can terminate. From 0, a point, to 9, filling space, branes offer fresh perspectives on the interactions between particles and forces, maybe explaining why gravity is weaker than the other fundamental forces. Because string theory may offer a quantum explanation of the early cosmos, it is appealing in the cosmic perspective. It suggests that the cosmos may have started from the collision of higher dimensional minds and provides mechanisms for cosmic inflation and substitutes for the Big Bang singularity. String theory has several problems, even with its complexity and beauty. The absence of overt experimental proof is one of the largest. Experimental verification is rather challenging, as the energy scales at which string effects would become apparent are well beyond the capabilities of present particle accelerators. Furthermore, there are a plethora of solutions to string theory, each of which corresponds to a distinct approach to compactifying the additional dimensions. This patchwork of fixes is a feature as much as a flaw. Though it makes it hard to make firm predictions, it gives the theory a lot of flexibility in suiting our reality. String theory's detractors further note that it hasn't yet offered a definite, testable prediction that would enable empirical confirmation or refutation. As a physical theory, rather than merely a mathematical framework, This has generated discussions among the physics community over the scientific validity of string theory. The possibility of string theory to unite all the basic forces under a single theoretical framework keeps it being studied and developed in spite of these obstacles. Furthermore, it has enhanced theoretical physics by offering novel instruments and ideas with uses in several other scientific domains. In order to understand the basic properties of particles and forces, as well as to use its mathematical methods to address challenging issues in quantum field theory, nuclear physics, and early universe cosmology, researchers are still delving into string theory. String theory could change as it goes along to better fit empirical facts, or it might provide a springboard for a more basic theory. It is still one of the most fascinating and rich fields of contemporary theoretical physics, though, in any case. Investigating string theory, then, is a voyage at the frontier of our knowledge of the cosmos that promises to transform not just our comprehension of the basic particles and forces, but also our larger knowledge of the cosmos. The search of theories like string theory, the multiverse, and other sophisticated theoretical frameworks has drawn criticism and offers a number of major obstacles. These problems mostly concern the intricacy, testability, and consequences of the theory for science philosophy. Currently, string theory is criticized mostly for lacking testable predictions. Experiments that can firmly confirm or disprove string theory have proven challenging since it operates at energy scales much beyond what present particle accelerators can reach. This raises the question of whether string theory can be regarded as a conventional scientific theory if it is not verifiable empirically. Comparably, the testability problem confronts the multiverse hypothesis. The multiverse, by definition, implies the existence of other worlds that are not causally related to ours, and thus unobservable. This begs the issues of the multiverse's scientific validity, and if it belongs more in the domain of philosophical conjecture than empirical research. The intricacy of these theories and their strong dependence on sophisticated mathematics, which can be incomprehensible even to physicists, are two other criticisms. This intricacy has the potential to make the ideas more difficult to understand and less approachable, therefore excluding them from more extensive scientific investigation. The multiverse hypothesis begs important philosophical issues regarding the nature of reality and our capacity to comprehend it. It questions the Copernican premise by putting forth the possibility that, out of all the potential universes, ours is unique or precisely calibrated. Allocation of funds and resources is also another point of dispute. The scientific community has some who contend that more empirically based disciplines that offer quicker returns in terms of knowledge and technology would be a better use of the significant resources allocated to these high theory fields. Additionally questioned is the idea of beauty as a guiding in theoretical physics. Researchers may ignore less mathematically beautiful, but more in line with empirical facts, alternative workable explanations of the cosmos in their quest of beautiful mathematical equations and visually appealing ideas. The multiverse's detractors further contend that it violates the parsimony, or Occam's razor principle, which holds that the simplest explanation, typically involving the fewest assumptions, is the best one. Some consider it an excessive assumption that the multiverse hypothesis adds an almost limitless number of worlds to explain happenings in our own one. The need of supersymmetry in string theory presents a problem. Although supersymmetry gives string theory a mathematical coherence, there are questions regarding this fundamental feature of the theory, as experimental searches for supersymmetric particles have so far produced no results. The educational hurdle in these areas is also considerable. It is challenging to include these sophisticated ideas into regular curricula and include a larger audience in their discussion and growth, since teaching them calls for a grounding in high-level mathematics and physics curriculum, and to involve a larger audience in their creation and discussion. Furthermore, relevant to large-scale trials that could be needed to verify any of these notions are ethical and environmental issues. There must be thought given to the ethical and environmental effects of building and running large particle accelerators. There has long been criticism of the cyclical character of theoretical physics, which implies a potential stagnation or lack of discoveries that completely change the paradigm because theories frequently return to identical issues and answers. Furthermore, sociological is the critique. Sometimes the close-knit groups of theoretical physicists working on these sophisticated ideas create echo chambers where critical evaluation is reduced, and agreement on untested theories may be achieved too soon. The scientific community has lastly called for a variety of concepts and methods. Some contend that the preponderance of popular ideas like string theory and the multiverse may cause alternative theoretical frameworks to be ignored, therefore obstructing other less well-known but perhaps productive research directions. The James Webb Space Telescope, or JWST, is slated to be the top observatory of the upcoming 10 years and marks a major development in astronomical technology, intended to be the leading observatory of the ensuing 10 years. Operating out of an orbit around 1.5 million kilometers from Earth, JWST will investigate every stage of cosmic history from the earliest universe's most distant detectable galaxies to our solar system and all points in between. Its capabilities are geared at seeing planetary formation, the development of galaxies, element creation by stars, and high redshift star formation. One outstanding illustration of worldwide astronomical cooperation is the Event Horizon Telescope. It is a global network of radio telescopes joined together to produce an interferometer the size of a planet with until unheard-of sensitivity and resolution. The first ever photo of a black hole in the galaxy M87 proved the EHT's ability to record the most detail yet obtained of the immediate surroundings of supermassive black holes. Operating atop Cerro Paranal in the Atacama Desert in northern Chile, the Very Large Telescope, or VLT, is one of the most sophisticated optical devices in the world and is run by the European Southern Observatory. With its 8 2-meter main mirrors, each of the 4 separate telescopes that make up the VLT may operate separately or in concert to create a massive interferometer. Astronomers may now view features up to 25 times finer than they could with the individual telescopes. A 1999 NASA launch, the Chandra X-ray Observatory, is a spacecraft that collects X-rays from high-energy cosmic areas, including materials around black holes, clusters of galaxies, and the remains of exploding stars. Chandra has shed light on the interactions of dark matter and the characteristics of matter in extreme environments, therefore assisting scientists in comprehending the structure and development of the universe. The priciest ground-based telescope now in use is the Atacama Large Millimeter Submillimeter Array, situated in the arid Atacama Desert of Chile. ALMA's capabilities enable it to see, with previously unheard-of sensitivity and precision, light from some of the coldest objects in the cosmos, including the early universe's galaxies, planetary systems, and molecular gas clouds. Under construction in Chile, the Large Synoptic Survey Telescope, LSST, which will soon be called the Vera C. Rubin Observatory, is intended to survey the whole visible sky every few nights. A vast and deep astronomical dataset, produced by its broad field of view and quick scanning capacity, will aid in answering some of the most important puzzles about the composition and history of the universe, such as the enigmatic dark matter and dark energy. The 2 10-meter diameter telescopes at the Keck Observatory, perched atop Mauna Kea in Hawaii, are among the biggest optical and infrared telescopes now in use. They have been essential to numerous important discoveries, including the compositions of the atmospheres of far-off planets and the actions of supermassive black holes. In the annals of astronomy, the Sloan Digital Sky Survey has been among the most ambitious and important. Working out of the Apache Point Observatory in New Mexico, SDSS has produced the most intricate three-dimensional maps of the cosmos ever produced, including spectra for over 3 million astronomical objects and deep multicolor pictures of 1/3 of the sky. With future locations in South Africa and Australia, the planned square-kilometer array is expected to be the biggest radio telescope in the world. The SKA will investigate cosmic radio waves with previously unheard-of sensitivity and resolution, by integrating signals from hundreds of tiny antennas dispersed across thousands of kilometers. It will look at early universe galaxies, dark energy, and general relativity in harsh environments. With their special skills and technical advancements, every one of these equipment is essential to our continuous cosmic investigation. They guarantee ongoing advancement in astronomy and other fields by not only expanding our senses into farther reaches of space, but also improving our grasp of the basic principles governing the cosmos. Observing the early universe's star and galaxy formation, the James Webb Space Telescope, or JWST, tackles cosmological problems. Its infrared capabilities enable it to see farther back in time than ever before, giving light on the epoch just after the Big Bang when the first galaxies were forming. This facilitates the understanding by astronomers of the early universe's evolution and the formation of its initial structures. This clarifies to astronomers the evolution of the early cosmos and the formation of its initial structures. Our grasp of black hole physics is enhanced by the Event Horizon Telescope. Through imaging of supermassive black hole event horizons, the EHT investigates extreme circumstances for general relativity predictions. This is essential to comprehending the function of black holes in the creation and evolution of galaxies, and by exposing departures from Einstein's theory, may indicate novel physics. Determining the rate of cosmic expansion has been made possible in large part by the Hubble Space Telescope. Hubble has improved estimates of the Hubble constant, a crucial cosmological statistic that characterizes the speed at which the universe is expanding and illuminates the dynamics of the cosmos by monitoring far-off supernovae. Seeing the distribution and motion of galaxies, the Very Large Telescope improves our knowledge of dark matter and dark energy. The sophisticated optics of the VLT enable precise measurements of the distribution and motion of galaxies, therefore enabling detailed studies of the large scale of dark matter and dark energy. Tests of cosmic evolution models and the large-scale consequences of dark energy depend on precise measurements of the large-scale structure of the universe made possible by the VLT's sophisticated optics. The hottest parts of the cosmos, including galaxy clusters and supernova remnants, are studied using the Chandra X-ray Observatory. Chandra maps the hot gas distribution in galaxy clusters to show that dark matter, which does not produce light but rather exposes itself via its gravitational effects on visible matter, exists. The frigid dust and gas that stars and planetary systems are formed of is seen by the Atacama Large Millimeter Submillimeter Array. The chemical makeup and dynamics of these early phases of star and planet formation are well studied by ALMA because of its high resolution and sensitivity at millimeter and submillimeter wavelengths, which also offers hints about the circumstances under which such processes might take place in other regions of the universe. Soon to become operational, the Large Synoptic Survey Telescope, or LSST, will be essential in answering cosmological queries about dark energy and the source of cosmic acceleration. Through continuous scanning of vast regions of the sky, LSST will monitor changes over time and contribute to the unparalleled mapping of the universe's expansion history. Powerful telescopes at the Keck Observatory enable astronomers to study the furthest objects in the cosmos and shed light on how galaxies at the end of the observable universe develop. Cosmologists may now test ideas on the general structure of the cosmos and the billion-year development of cosmic structures. Our grasp of the vast-scale structure of the cosmos has been completely transformed by the Sloan Digital Sky Survey, or SDSS. Detailed three-dimensional maps of millions of galaxies produced by SDSS have given vital information for verifying theories of galaxy formation and dark matter dispersion. The Square Kilometer Array will trace the distribution of hydrogen across the history of the cosmos, therefore addressing important cosmological concerns. Through tracking the development of hydrogen clouds into galaxies and clusters, SKA will enable scientists to better comprehend how dark matter and gravity combine to create the large-scale architecture of the universe. From the characteristics of the early universe to the behavior of dark matter and dark energy, these devices together address a wide variety of cosmological issues. Through a multidimensional picture of the universe at various wavelengths and at different periods, these instruments provide a greater comprehension of its most basic secrets. These observatories also collect data that validates theoretical physics predictions, therefore establishing a crucial feedback loop between theory and observation that is necessary to progress cosmological models. Furthermore, these tools support the hunt for exoplanets and the study of their atmospheres, which advances our knowledge of the creation of planetary systems and the circumstances that may result in livable conditions elsewhere in the cosmos, therefore indirectly advancing cosmology. These instruments enhance our measuring capabilities and hence improve the basic constants of physics, which are essential for accurate cosmological models. More precise estimates of these constants enable improved predictions of events such as the distribution of matter in the universe and the cosmic microwave background radiation. Finally, the many functions of these sophisticated astronomical devices allow for a thorough method of resolving the cosmic riddles. Every instrument contributes something special to the cosmic jigsaw, enabling the construction of a logical picture of the universe's functioning at all sizes. Cosmologists now depend heavily on developments in data processing and simulation to handle and analyze the enormous volumes of data gathered from astronomical observations, and to simulate intricate cosmic events with previously unheard-of precision. Among the major advances has been the creation of sophisticated algorithms to handle the enormous information produced by telescopes such as the Sloan Digital Sky Survey and the forthcoming Large Synoptic Survey Telescope. These programs improve data processing speed and accuracy by automating the categorization of galaxies and the detection of astrophysical events using methods from machine learning and artificial intelligence. An additional significant development is the application of parallel computing architectures. Larger data volumes and more complicated simulations are feasible for researchers to tackle using distributed processing over several CPUs and GPUs than with conventional computing techniques. For simulations involving the dynamics of billions of particles, including those used to represent the large-scale structure of the cosmos, this is very critical. Through the provision of scalable, flexible computer resources, cloud computing has also revolutionized data processing in cosmology. Large amounts of data may be stored in the cloud, and on-demand access to enormous processing capacity speeds up data analysis and model testing, and promotes cooperation between worldwide teams, improves in numerical techniques, including n-body simulations, which compute the gravitational interactions between particles representing dark matter, stars, or galaxies, have had a major impact on models of cosmic structures. Additional physical processes like gas dynamics, star formation, and supernova feedback have been included into these simulations to make them more realistic. Using simulations to create artificial worlds, cosmologists may compare simulated and observational data to evaluate hypotheses of cosmic evolution. This method clarifies the function of dark matter and dark energy in forming the cosmos and helps to improve theories of how galaxies form and develop. Significant progress has also been made in data visualization techniques. Presently, intricate data sets are explored using virtual reality settings and interactive 3D models. These resources facilitate public and scientific understanding of the three-dimensional structure of the cosmos. Increasingly, cosmic data is being used with machine learning methods like neural networks and decision trees. These techniques provide new opportunities for discovery and large-scale survey data by identifying patterns and correlations in data that are too subtle for conventional analytic methods. Bayesian statistical techniques integrated into data analysis enable more reliable cosmological parameter formulation and improved handling of uncertainty. With the use of these techniques, one may include past information and draw probabilistic conclusions about the universe. Now, practically instantly after they happen, automated survey telescopes with real-time data processing capability may detect transient astronomical phenomena like supernova and gamma-ray bursts. Understanding these transient occurrences depends on prompt follow-up observations, which are made possible by this quick processing. Other theories of gravity are also being investigated, and their observable fingerprints are predicted using simulations. Astronomers may limit or reject these hypotheses by comparing these predictions with real observations, therefore improving our knowledge of the basic processes governing the cosmos. A future path for analyzing cosmic data is presented by quantum computing, which can do computations that are not possible with conventional computers. This may transform both the processing of enormous information and the modeling of quantum events in the early cosmos. The utilization of telescope time and data collecting efficiency are maximized by the development of autonomous observatory systems powered by software that can modify observing methods in real time depending on the weather and the data being acquired. Better methods for noise reduction and error correction have raised the standard of data collected using observational devices. It will require these developments to separate real cosmic signals from the noise that comes with observations made at great distances. Finally, the adoption of cooperative platforms and open-source software has democratized access to cosmological simulations and data processing tools, therefore promoting a more diverse worldwide researcher community. As a result, cosmological questions are now solved more cooperatively by combining several viewpoints and areas of knowledge. These developments in modeling and data processing taken together are advancing our knowledge of the cosmos, allowing cosmologists to address more difficult problems than previously, and opening the door for new discoveries. Because artificial intelligence and machine learning allow scientists to manage enormous volumes of data and intricate simulations with previously unheard of efficiency and accuracy, they are revolutionizing cosmology. Where data volume and complexity surpass the capacity of conventional analytical techniques, these technologies are very helpful. Using machine learning algorithms, for example, telescopic photos are analyzed to automatically categorize galaxies according to their sizes, shapes, and other characteristics. Astronomers may concentrate on more complex study and interpretation while cataloging astronomical objects is accelerated by this technology. Slight patterns in the cosmic microwave background radiation are being found using deep learning, a form of machine learning. Through their ability to shed light on the circumstances of the early cosmos, these patterns enable cosmologists to more successfully test theories on cosmic inflation and the Big Bang than before. A further instrument in the machine learning toolbox, neural networks are used to forecast the distribution of dark matter in galaxies. Through training on simulations, these networks may acquire the fundamental physics and then apply this information to actual data, therefore improving our grasp of the function of dark matter in the construction of cosmic structures. Optimizing telescope functioning also requires artificial intelligence. Significantly increasing observational efficiency are AI systems' ability to schedule observations, modify settings in real time in response to environmental variables, and even foresee system problems before they happen. Gravitational wave detector signals are processed by machine learning techniques on LIGO and Virgo, for example. By rapidly sifting through noise to find the tiny signals of cosmic occurrences, these techniques greatly shorten the period between discovery and notification to the astronomical community. Artificial intelligence, AI, methods are crucial in radio astronomy for removing noise from the enormous volumes of data gathered by instruments such as the Square Kilometre Array. Data utilized for cosmology study is pure because machine learning algorithms can differentiate between interference from earthly sources and signals from celestial sources. Theoretical components of cosmology are also served by machine learning, including parameter estimate. More accurately constrained models of the expansion of the universe and the characteristics of dark energy may be obtained by AI algorithms than by conventional grid-based techniques exploring the enormous parameter spaces of cosmological models. Numerous scales of the universe are being emulated by AI-driven simulation frameworks. These emulators enable fast testing of theoretical models against observational data by running cosmological simulations in a fraction of the time it takes with conventional techniques. Because machine learning makes it possible to analyze time series data from changeable astronomical sources, it is also helping to investigate cosmic evolution. Artificial intelligence (AI) programs can identify and describe transitory events like as variable stars, gamma-ray bursts, and supernovae, which advances our knowledge of the dynamics of the universe and star lives. Cross-validation of data from several observational platforms made possible by AI technology increases the validity of the findings obtained from cosmic data. AI facilitates a more coherent knowledge of observational cosmology by comparing and synthesizing data from optical, radio, X-ray, and other telescope types. Artificial intelligence (AI) driven predictive analytics is being applied to speculate on the presence of celestial objects and phenomena before they are ever seen. This preventative method can direct observational techniques, giving methods and goals based on prediction models priority. Managing the data lifecycle in cosmology, from collection and storage to processing and analysis, requires AI. AI speeds up and saves money the process of turning unprocessed data into useful scientific information. In cosmology, artificial intelligence, AI, and machine learning are also spurring innovation in data visualization methods, enabling scientists to easily study intricate, multidimensional information. This makes patterns and abnormalities easier to spot than they could be otherwise. All things considered, machine learning and artificial intelligence are playing a fast-growing role in cosmology by providing strong instruments for theoretical investigation, data analysis, and observational strategy. These technologies, which promise to open up new scientific discoveries and expand our knowledge of the cosmos, are not only auxiliary tools, but are starting to take center stage in cosmological study. The European Space Agency's Euclid mission is slated to launch soon with the goal of charting the dark universe's shape. Euclid wants to know how dark matter and dark energy shaped and propelled the universe's expansion by examining the forms and redshifts of millions of galaxies. Once launched, the James Webb Space Telescope will investigate a number of cosmic events, one of them being the discovery of the first galaxies to form in the early universe. In order to maybe find indicators of habitability, JWST will also investigate the atmospheres of neighboring exoplanets. Previously known as WFIRST, NASA's Nancy Grace Roman Space Telescope is intended to address important issues in the fields of infrared astrophysics, exoplanets, and dark energy. It will conduct a census of exoplanets to aid in understanding the demography of planetary systems and progress research of the structure and expansion of the cosmos with a wide-field survey instrument. Previously known as the Legacy Survey of Space and Time, or LSST, the Vera C. Rubin Observatory will carry out a 10-year project to provide an incredibly comprehensive public catalog of more than 20 billion galaxies. The purpose of this study is to clarify enigmatic characteristics of dark matter and dark energy, as well as basic concerns about the formation and development of the Milky Way. When finished, the Square Kilometre Array, SKA, which is being built at locations in South Africa and Australia, will be the biggest radio telescope in the world. Its enormous network of dishes and antennas will investigate the cosmos in depth never previously possible in radio astronomy, with the goal of shedding light on cosmic magnetism, gravity, and the hunt for extraterrestrial life. The goal of another ESA project, Plato, is to find and investigate extrasolar planetary systems, concentrating on finding Earth-like planets in the habitable zone of their stars. The telescopes included in Plato will make it possible to measure star brightnesses precisely, therefore allowing for the identification of minute dips brought on by planets in orbit. The Chinese Space Station Telescope seeks to provide high-resolution photographs across a large field of view, therefore augmenting existing space-based telescopes. Surveying the structure and distribution of dark matter, investigating the creation and development of galaxies, and spotting brief astronomical phenomena are among its mission goals. Explored by NASA's Dragonfly rotorcraft is Titan, the biggest moon of Saturn. Understanding the atmospheric and surface characteristics of Titan, and maybe illuminating the circumstances that can support life, Dragonfly will investigate primordial chemistry and alien habitability in the rich organic environment of Titan. And surface features, which could give information on the circumstances that could support life. The least investigated planet in our inner solar system, Mercury, is the subject of the Bepi-Colombo project, a cooperative endeavor between ESA and the Japan Aerospace Exploration Agency. Among the mission's goals are to investigate Mercury's geology, magnetic field, and incredibly thin atmosphere. To learn more about the behavior and makeup of our star's outer atmosphere, the Aditya L-1 mission of the Indian Space Research Organization will investigate the Sun's corona. Data essential to comprehending solar variability and its effects on space weather, which may damage satellite communications and Earth's power grids, will be provided by the project. Collaboratively headed by NASA and ESA, the Mars Sample Return Mission seeks to gather samples from Mars and bring them back to Earth for in-depth investigation. Opening a new era in Martian research, this mission will offer hitherto unheard-of insights into the geology and possible biosignatures on Mars. The NASA Planetary Defense Project, DART, seeks to evaluate our capacity to reroute an asteroid via kinetic impact. Developing plans to shield Earth from any future asteroid strikes depends critically on the goal of this expedition. Set to investigate Jupiter's big ice moons, Ganymede, Callisto, and Europa, which are thought to have subterranean oceans, is the Jupiter Ice Moons Explorer, by E. Among JUICE's objectives are a deeper knowledge of the intricate Jovian system and an evaluation of these moons' suitability for life. The hot and energetic cosmos will be studied by the Advanced Telescope for High-Energy Astrophysics, Athena, which ESA plans to deploy in the early 2030s. It will look at big structures and the mechanisms guiding the development of galaxies, with an emphasis on black holes and how they mold space. Finally, the Artemis program of NASA seeks to send people back to the Moon and maintain a long-term presence there. In addition to acting as a venue for technological demonstrations and scientific study, this project will act as a springboard for next crewed trips to Mars and maybe beyond. Each of these missions represents a significant investment in our quest to understand the universe and our place within it. Deeper understanding of the early universe is predicted to come from telescope technological developments like the James Webb Space Telescope. We aim to clarify the early expansion period and maybe solve the Hubble tension anomalies by studying the first galaxies and stars, thereby improving our understanding of the circumstances soon after the Big Bang. Already, the Event Horizon Telescope has made a major contribution by taking the first picture of a black hole. Testing of the limitations of general relativity in the strong gravity realm is anticipated as this study advances. Any departures from Einstein's theory predictions might offer hints for novel physics that can account for cosmic acceleration without the necessity for dark energy. Missions like Euclid and the Vera C. Rubin Observatory are made expressly to investigate dark energy and the expansion of the universe by means of thorough surveys of billions of galaxies. These observatories will improve our knowledge of how dark energy has impacted cosmic history by documenting the large-scale structure of the cosmos spanning enormous epochs, maybe leading to a solution of why the universe's expansion is speeding. With its square-kilometer array, the early universe's structure will be shown in a way never before possible. SCA may shed fresh light on the function of this enigmatic component in cosmic development by tracking neutral hydrogen and its progression across time. Because AI and machine learning can now handle enormous data volumes from these missions more efficiently, cosmology is being revolutionized. These instruments can reveal not immediately obvious patterns and connections, possibly pointing out anomalies that contradict accepted theories and models. High-precision testing of many scenarios is anticipated to be made possible by the synergy between observational data and simulation technology developments. This could result in improvements to theoretical models of the cosmos, especially those that describe how dark matter, dark energy, and regular stuff interact. Encouraged by observatories like LIGO and Virgo, gravitational wave astronomy is providing a new perspective on hitherto unobservable phenomena. Our knowledge of cosmic history may be changed if gravitational waves from black hole mergers and maybe from the early cosmos are found. Although mostly concentrating on planetary science, the study of exoplanets and their atmospheres made possible by missions like as JWST and Ariel also advances our knowledge of the genesis and development of planetary systems, therefore contributing to cosmology. This increases the range of situations under which we understand physics, therefore influencing cosmological ideas indirectly. These technical developments should be beneficial to the study of cosmic inflation, a fast expansion phase thought to have happened a fraction of a second after the Big Bang. Expected from next missions, more accurate measurements of the cosmic microwave background might offer unquestionable proof of inflationary theories. Our knowledge of the temperature variations in the early cosmos will be improved by attempts to map the cosmic microwave background over more sky regions and with higher precision. Testing Big Bang model predictions and comprehending the quantum fluctuations that could have sparked large-scale structure depend on this. Details of astrophysical events including supernovae, neutron star mergers, and black hole accretion processes are being investigated in greater depth. Given that dark matter and energy affect the structure and history of the universe, knowing these extreme occurrences can offer oblique hints about their properties. Data from cosmic observatories and particle accelerators are being used to combine observational cosmology with particle physics, therefore promoting a more comprehensive understanding of the rules of the universe. Because it enables the confirmation of hypotheses across many physical sizes and settings, this multidisciplinary approach is essential for addressing the cosmological problem because it makes theories viable across a range of physical scales and settings. Using quasars and gamma-ray bursts as standard candles is one of the new, indirect observation techniques that is improving our capacity to calculate cosmic distances and expansion rates throughout the universe. This may answer the Hubble tension directly by offering fresh information on the rate of expansion at various periods in cosmic history. Overall, the crisis in cosmology is about to be profoundly impacted by the confluence of new technologies, missions, and theoretical discoveries. These advances promise to answer long-standing issues and maybe reveal new physics that might completely change our perspective of the cosmos by offering a deeper and more thorough knowledge of the world. Solving the cosmological crises could provide significant new perspectives on the nature and beginnings of the cosmos, therefore revolutionizing our perception of reality. We may understand the cosmos to a new degree if we addressed anomalies like the Hubble tension and the secrets of dark matter and dark energy. Resolution of these difficulties would probably need a revolution in physics comparable to the one sparked by Einstein's theory of relativity. Such a change would not only make sense of the disparities in the observations made now, but it may also bring the forces of nature together under a single theoretical framework, therefore bringing about the long-awaited theory of everything. By resolving the nature of dark matter, we may be able to reinterpret matter itself and discover new, nonconformist forms of matter. This may have far-reaching effects on everything from the basic laws of the cosmos to useful applications in energy, materials science, and technology. Gaining knowledge of dark energy and its part in the universe's accelerating expansion may provide fresh light on the destiny of the universe. It may indicate if the cosmos will terminate in a catastrophic crash, keep expanding endlessly, or come to some other unexpected finale. Understanding cosmic geography and age estimates of the earliest stars may be affected by changes in our measurements of the universe's expansion rate, resulting from a clarification of the Hubble tension. More philosophically, our view of our role in the cosmos may shift if the cosmic crises are resolved. Knowing the actual character of the universe may change our existential and philosophical frameworks, which would affect everything from the quest of meaning to the advancement of science. As new ideas and materials are created based on our better knowledge of the cosmos, the possible resolution of these crises may result in technological breakthroughs. This may propel new sectors and uses in anything from communications and space travel to quantum computing and energy generation. As new ideas and concepts become essential to our knowledge of physics, a resolution might transform science curriculum educationally, just as relativity and quantum mechanics have become bedrock of contemporary science education. A resolution of this sort may potentially affect the hunt for extraterrestrial life. We may better forecast where and how life would develop in the cosmos if we knew the cosmic factors that control planetary formation and galaxy dispersion. If these crises were resolved, techniques for seeing and quantifying cosmic events would probably become more precise and trustworthy. More fields of study that are now out of our grasp may become accessible with improved tools and methods resulting from fresh, theoretical discoveries. Better knowledge of cosmic events may help environmental scientists better comprehend Earth's position in the cosmos, and may even be used to develop models that forecast meteorological and geological events impacted by cosmic occurrences. Globally, the cooperative character of answering these cosmic issues may be used as a paradigm for international scientific collaboration, showing how common intellectual interests may bring disparate individuals together across national and cultural barriers. Resolving these cosmic crises would, finally, highlight how dynamic and always changing scientific study is. It would serve as a reminder that knowledge is a never-ending quest, motivated by human curiosity and inventiveness, and that science is a continuous process of discovery in which solutions frequently lead to new questions. By resolving the present cosmic crises, physics and astronomy may undergo revolutionary transformations that would change paradigms and expand research areas. Deeply entwined, developments in our knowledge of the universe always impact fundamental ideas in physics and broaden the horizons of astronomical investigation. Finding the nature of dark matter might completely change particle physics by introducing new particles that don't fit into the accepted paradigm. A reassessment of the basic components of matter would be required by this finding, which may result in the creation of a more thorough model of particle interactions, perhaps resulting in the creation of a more thorough particle interaction model. In a similar vein, major developments in field theory may result from a better knowledge of dark energy and its consequences for the expansion of the universe. A key problem in theoretical physics, the vacuum energy of space and its part in the cosmological constant, may be better understood by theories that effectively include dark energy. Improvements in the measuring methods employed in physics and astronomy may result from the resolution of the Hubble tension, improving the accuracy of distance measurements and the calculation of basic constants. Testing hypotheses in observational as well as experimental contexts requires this accuracy. A significant theoretical problem in physics would be solved, and technological advances in fields like quantum computing, gravimetric sensing, and space-time-based navigation systems might result from the possible integration of general relativity and quantum mechanics into a single framework. In astronomy, these cosmic riddles would be much enhanced by the solutions to our theories of cosmic development. More precise forecasts on the evolution of stars, the behavior of galaxies, and the life cycle of cosmic objects ranging from superclusters to black holes may result. With better knowledge of high-energy events like gamma-ray bursts, neutron star collisions, and black hole mergers, astronomy may benefit greatly from higher resolutions. These occurrences provide an insight into the harshest circumstances under which quantum physics and gravity interact. Exoplanet study may gain, as well as better cosmological models, help us to better grasp how planetary systems evolve. This may affect our quest for life beyond Earth by pointing out the most likely locations for it to exist and guiding the planning of space exploration missions. Improved sensors and telescopes, among other technological developments fueled by cosmological study, might find application in other branches of science and technology. Applications of technology created for space telescopes, for instance, might improve in other fields of research and engineering. Space telescope-related technology, for instance, may improve terrestrial imaging systems used in anything from environmental monitoring to medical diagnosis. In theoretical physics, new cosmological discoveries may motivate novel solutions to age-old issues, including the nature of time, the beginnings of the universe, and the unification of forces. A series of fresh queries and speculations follow each resolution, hence sustaining the cycle of discovery. Changes in basic ideas would influence the substance and emphasis of scientific curriculum at all levels. Therefore, educational effects are also probably in store. This may lead to a new generation of scientists having a re-evaluated notion of the nature and operation of space. As new theories called for new kinds of simulations, computational physics would also change. Innovations in computers required to investigate these novel hypotheses may find their way into other disciplines like economics and climate research that depend on intricate simulations. Growing from a deeper knowledge of cosmology would be interdisciplinary disciplines like astrochemistry and astrobiology, studies of the genesis of life and the kinds of chemical processes that are feasible in different cosmic contexts might be informed by knowledge about the distribution of materials and circumstances in the early cosmos. Regarding observational technology, the astronomy field may create next-generation equipment intended to track events anticipated by novel theories, or to enhance the range and resolution of present observations, hence accelerating the cycle of discovery. And last, these possible modifications to physics and astronomy would probably increase public interest in and involvement with science. Discussions and arguments that follow as basic facets of our knowledge of the cosmos change would go beyond academic circles and improve scientific communication and education. Through these conversations, governmental choices may be influenced, public support for science can rise, and a society more scientifically informed. Deep issues regarding existence, the nature of reality, and our role in the universe are touched by the philosophical influence of cosmological findings that go well beyond the confines of science. Every significant discovery about the universe changes our philosophical and existential frameworks in addition to our scientific perspective. A Copernican-like shift brought about by discoveries of the universe's size and abundance of galaxies has strengthened the notion that Earth and its people are not essential to the universe's functioning. For anthropocentric faiths and philosophy, this has significant ramifications. Concerns over the ultimate destiny of the cosmos are raised by the idea of an expanding universe that may be speeding because of dark energy. Whether it will keep expanding indefinitely, come to an abrupt freeze, tear, or finally start to shrink. These situations beg philosophical debate on the nature of an impermanent cosmos. The potential presence of other worlds inside a multiverse begs the issue of whether the physics rules of our own reality are unique. Should many physical rules exist, philosophers may wonder about the basis of necessity and contingency in nature. The bulk of the mass energy in the cosmos is made up of dark matter and dark energy, which are invisible but for their gravitational effects, and therefore complicate our conception of what it is for anything to exist. This could change our ideas of evidentiary existence if entities are only known by their impacts on other entities. The philosophical discussion about the rarity and worth of life is extended by the quest for alien life and the study of exoplanets in cosmology. Finding extraterrestrial life may have a significant impact on our conceptions of the purpose and meaning of life here. Discussions of determinism and randomness in philosophy cross with quantum cosmology, which aims to characterize the cosmos at its earliest beginnings. Predictability and the character of scientific explanation are called into doubt by the part probability plays in the basic structure of reality. Philosophers disagree on the roles of observation and measurement in determining laws of nature, and the anthropic principle, which is frequently used in cosmological settings to explain why our world seems to be exquisitely tailored for life. This principle questions theories of an objective cosmos by implying that our comprehension is intrinsically skewed, since we are observers. Our ethical concerns are impacted by cosmic findings as well. Our knowledge of the cosmos and our obligations within it informs ethical issues raised by discussions about space exploration, planetary preservation, and the potential colonization of other worlds. Understanding that space and time are interconnected and dynamic, qualities characterized by general relativity, contrasts sharply with Newtonian views of absolute space and time, changing how philosophers consider the framework of reality is one of the benefits of the cosmological advances. Studies of cosmology also bring up the issue of finitude against infinitude. Whether the cosmos is finite or infinite affects many religious and philosophical discussions on the nature of infinity, the likelihood of an actual infinite, and the boundaries of human comprehension. Cosmological findings affect the way that society as a whole views technology, the future, and development in a larger cultural setting. Growing knowledge of the cosmos frequently represents human potential and accomplishment, influencing cultural myths about the future of mankind. Technical and cosmological developments feed philosophical debates on simulation theories. Representing age-old philosophical concerns in contemporary terms, the hypothesis that our world may be a simulation raises fascinating questions about reality, awareness, and the potential of higher-order entities. Modernizing ancient philosophical questions. The continuous effort to comprehend the cosmos finally captures the philosophical core of human curiosity and the need for information. Whatever the conclusions, the quest itself highlights a basic feature of philosophy and human nature: the unrelenting need to learn about and comprehend our surroundings. In cosmology, ethical challenges include everything from resource and money distribution to the wider consequences of astronomical findings. Research in the subject develops and takes direction in part because of these problems. A major ethical issue is the large governmental or private funding of cosmology. Cosmological research raises concerns about the prioritization of scientific research, particularly when contrasted to more urgent global problems like health, poverty, and environmental sustainability, because it frequently requires costly equipment and long timeliness. Large-scale astronomical facility construction and operation have an environmental impact that must be taken into account in the quest of cosmic knowledge. These initiatives frequently need for a large amount of energy and land utilization, and the scientific advantages must be balanced against the environmental cost. It is also morally required to guarantee that the public and the scientific community get just and open sharing of the cosmological data and findings. Through allowing scientists from all over the world to contribute to and profit from new discoveries, the open access to scientific data concept encourages transparency and increases the impact of research. Ethical issues also include the cultural and religious value of locations that are frequently selected for astronomical observatories. For instance, native Hawaiian organizations that regard the land holy have opposed the building of telescopes atop Mauna Kea in Hawaii. An important ethical issue in these situations is upholding indigenous rights and cultural legacy. Deeply moral concerns about how mankind should react are raised by the possible discovery of communications from alien intelligence. It is imperative that a cautious reaction that takes into account the worldwide consequences of such a finding be developed. This calls for international collaboration and communication to create procedures that honor different points of view and possible worldwide consequences. Considerations of inclusiveness and equity are also part of ethical financing procedures in cosmology. Fostering a more inclusive scientific community requires making sure that a wide range of scientists, especially those from underrepresented groups and poor nations, have access to research opportunities, financing, and resources. There is a need to prevent space militarization when one pursues cosmological study. Sustaining a clear ethical line is crucial to stop the spread of weapons in space, since technology created for cosmological study may find their way into military applications. The ethical terrain of presenting their discoveries to the general public must also be traversed by researchers. Avoiding sensationalism, especially in media representations that may mislead the public about the consequences of cosmological findings, is part of this. A responsible and accurate communication is essential. The cosmological findings' long-term character. It is essential to communicate accurately and responsibly. Many cosmological efforts, including those seeking to address basic issues about the universe, need for ongoing financing that may last for decades. Ethical issues with these kind of long-term expenditures include weighing the opportunity cost of not funding other scientific fields against the possibility of making groundbreaking discoveries. It is also morally required to impart cosmological knowledge and motivation to the general people. By proving the importance of cosmological study in enhancing our knowledge of the cosmos and our role within it, public participation helps to justify the substantial expenditures on this field. When working with unidentified phenomena, including energy or dark matter, ethical science practice calls for remaining humble and receptive to fresh concepts. Accepting our ignorance directs responsible theory and experimentation. In cosmology, ethical issues should also deal with the possibility of international hostilities over common resources and scientific discoveries. Mending cooperative international frameworks for research and discovery might lessen these tensions. Furthermore, deserving of ethical attention are the effects of cosmological study on existential or philosophical views. The possibility that scientific findings will refute or alter our understanding of the cosmos and existence should be handled sensitively and with regard for different religious views. Finally, like in all science, cosmological study needs to be carried out honestly, free from prejudices and conflicts of interest that might jeopardize the validity of the results and public confidence in science. Maintaining these moral guidelines is necessary for cosmology to keep developing and receiving support from society. Today, we bring together a prominent group of philosophers, theoretical physicists, and cosmologists to talk about the current cosmological crisis. The tension in the Hubble constant measurements to the enigmatic properties of dark matter and dark energy are only two of the many issues the research faces. Leading cosmologists who have worked their whole lives examining the universe's large-scale structure make up our panel. They contribute understanding of the most recent observational evidence and theoretical models addressing the universe's expansion and its consequences for the conventional cosmological model. Theorists who focus on the mathematical foundations supporting cosmology will join them. They include viewpoints on other gravity theories, changes to the conventional particle physics paradigm, and possible unification of general relativity and quantum mechanics. Our scientific philosophers will also assist us in negotiating the philosophical ramifications of these cosmic concerns. Their examination will include how cosmological findings have changed our conception of reality, existence, and the scientific process. The Hubble tension, a disparity in the rate of cosmic expansion as measured from the early universe and the local universe, will be discussed first in the panel. The probable consequences of this conflict for our knowledge of physics and cosmology will be discussed. The mysterious elements of our cosmos, dark matter and dark energy, will thereafter be explored by our specialists. The proof in favor of these ideas, the difficulties in identifying them, and the theoretical substitutes that may account for the facts ascribed to them will be covered. Next up on the agenda will be the function of new tools and technology in cosmology. The panelists will talk about how fresh data from developments like the Event Horizon Telescope and the James Webb Space Telescope may assist to solve current cosmic mysteries. The philosophical problems raised by contemporary cosmology will take up a good deal of the conversation. This covers discussions on the need of simplicity and aesthetics in theory selection, as well as the standards for accepting scientific theories, like falsifiability and predictability. The panelists' exploration of the possibility of novel physics at the nexus of gravity and quantum mechanics. They will talk on how new research and theoretical developments could change how we think about these basic forces. Our philosophers will address the consequences of maybe finding a multiverse. They'll talk about how such a finding would impact conventional ideas of scientific truth and our conception of the cosmos as a coherent one thing. The panel will also go into the ethical issues surrounding cosmological research, talking about the duty of the scientific community in carrying out and disseminating its findings. This will include resource distribution, as well as the effects of big astronomical observatories on the ecosystem. Our experts will interact with the scientific community and the interested public directly when the conversation opens up to questions from the audience. This section will offer a chance to clear up popular misunderstandings and public inquiries on the nature of the cosmos. The panel will consider the direction of cosmology as a field in closure. They will talk about forthcoming research and missions that will probably completely change how we think about matter, time, and space. Impending research and missions that will probably completely change how we think about matter, time, and space. The objective of this panel discussion is to promote a wider conversation on the function of cosmology in our common search for knowledge, in addition to clarifying the present cosmological crises. This conversation attempts to close the knowledge gap between the general population and complicated scientific problems. Finally, highlighting the significance of keeping an open and critical attitude to cosmic exploration, the speakers will share their views on the philosophical and scientific mentality required as we approach the limits of cosmic knowledge. Expanding cosmology in the 21st century and beyond will need this viewpoint. Throughout our conversation, we have looked at a number of significant cosmological crises, each of which offers special difficulties and chances to further our knowledge of the cosmos. The Hubble tension, a difference between the pace of cosmic expansion as determined by measurements of the early cosmos and predictions based on the local universe, is the first of these crises. The consistency of the conventional cosmological model is called into question by this unsolved problem, which raises the possibility of novel physics. We explored the mysterious properties of dark matter, an inert material that has a strong gravitational effect on galaxies and galaxy clusters but does not emit, absorb, or reflect light. Dark matter has been controversial because, although being essential to the cosmological model, it has not been directly detected. One more pillar of the conventional cosmological model, dark energy, was examined for its contribution to the universe's expansion acceleration. Although its basic characteristics are currently little known, the enigmatic force challenges accepted physics ideas by opposing the gravitational attraction that should halt its growth. As we consider the problems and theories covered today, a number of possible fixes and future paths for cosmology development become apparent. These methods seek to clear out the basic doubts and contradictions that the science is now dealing with, therefore opening the door to a more comprehensive comprehension of the universe. Refinement of our universe expansion rate data is one possible way to alleviate the Hubble strain. More consistent data, and maybe a resolution of the disparities between measurements at various cosmic scales, might come from future missions and technological advancements like more accurate distance ladders and improved calibration of standard candles. Upcoming particle physics experiments, including those carried out at the Large Hadron Collider and other subterranean detectors, may eventually directly identify dark matter particles in the search for understanding it. On the other hand, developments in astronomical measurements could provide fresh and more definitive evidence of the existence of dark matter by its gravitational effects on visible stuff. Thorough studies of the universe's large-scale structure and galaxy distribution may help to solve the enigma of dark energy. Millions of galaxies are to be mapped by missions like the Euclid spacecraft and the Vera C. Rubin Observatory, which will provide light on how dark energy has affected the universe's expansion across time. Galaxy clustering string theory is still a major field of study, with theorists trying to derive testable predictions and possible signatures of extra dimensions or supersymmetric particles. Theorists are also investigating modifications to general relativity. The more general assertions of string theory may be supported or refuted by data found in future particle accelerators and cosmic observations. The distribution of physical constants in our cosmos or statistical study of cosmic microwave background radiation can be used to investigate the multiverse hypothesis further. Indirect signs or theoretical compatibility with other physics domains might support this audacious theory, even if direct evidence could still be hard to come by. Foundational and philosophical issues will always direct the understanding of cosmic evidence. Philosophical implications of new theories must be taken into account in order to make sure that they not only suit the evidence, but also align with more general epistemological ideas. Future cosmological paths will also be shaped by ethical issues. As the subject continues to need substantial resources, the scientific community must strike a balance between these needs and the larger needs of society to guarantee that cosmology advances human knowledge while upholding our moral responsibilities to the current and next generations. Undoubtedly, cosmic issues will be addressed in large part by technological breakthroughs. New sensors, telescopes, and computer techniques will improve our capacity to gather and examine data from the furthest regions of the cosmos. By combining machine learning and artificial intelligence with data analysis, cosmologists will be able to quickly sort through enormous volumes of data and find trends and anomalies that might lead to new discoveries about the universe. Furthermore, crucial to the ongoing funding of cosmological research will be educational programs that produce a new generation of scientists and an educated public. Deeper respect for the study of cosmology and its contribution to the answers to basic concerns about our existence will result from these initiatives. The size of cosmological issues frequently calls for resources and knowledge dispersed around the world. Hence, international cooperation will be essential. Through collaboration in data, ideas, and financing, the global scientific community may more successfully address these important issues. We shall have a better knowledge of the cosmos if philosophical research on the consequences of cosmological findings continues. The philosophical, existential, and ethical ramifications of ideas like the multiverse, dark matter, and the possible finiteness or infiniteness of the cosmos are among them. In conclusion, a multidisciplinary strategy combining cutting-edge technology, theoretical creativity, philosophical in-depthness, and public participation is what cosmology needs to succeed. Through investigation of these many routes, cosmology can get closer to fixing the present problems and revealing the more profound realities of our vast cosmos. Finally, the quest of cosmological knowledge will always arouse amazement and astonishment at the size and complexity of the cosmos, reminding us of the everlasting mystery and beauty of the universe we try to comprehend, whatever answers and paths the future contains. Beyond the simple study of stars and galaxies, the deep scientific field of cosmology addresses the basic beginnings, structure, and destiny of the universe itself. Its significance comes from its scientific achievements, as well as from its capacity to both uplift and challenge our conception of reality. Thinking back on cosmology history helps one to fully understand how our understanding of the cosmos has changed. From the first geocentric theories of the cosmos to the current knowledge of a huge, expanding universe, cosmology has continuously changed our perspective on our location in the cosmos. A link between several physics fields is provided by the study of cosmology. Through the connection of the rules of general relativity, which control the dynamics of galaxies and the universe, with quantum mechanics, which regulates the tiniest particles, it provides a complete description of physical reality. Cosmology deals directly with existential and philosophical problems by tackling basic concerns like the creation of the universe and the nature of its parts. It asks us to think about the beginning of time, the ultimate destiny of the cosmos, and the principles guiding its development. The search by cosmology for dark matter and dark energy touches on the boundaries of human understanding and technology. These enigmatic elements, comprising the bulk of the cosmos, serve as a reminder of the size of the unknown and the possibility of future discoveries that may completely change our knowledge. Cosmology is important also because it promotes worldwide cooperation. Because national boundaries do not exist for the mysteries of the cosmos, this area by nature demands international collaboration. Advancement of our combined scientific knowledge depends on this cooperative attitude. Innovative technology also heavily depends on cosmology. Advanced telescopes and observational methods, among other tools and techniques developed for cosmic study, frequently find use in other scientific domains and even in commonplace technology. An original viewpoint on Earth and people is encouraged by the discipline. Understanding the brittleness and uniqueness of our planet via cosmic studies might help us to appreciate our world more and inspire us to take steps to preserve it. The impact of cosmology also reaches education, where for many pupils it is a springboard to science. More young brains are drawn into careers in science, technology, engineering, and mathematics by the wonder and curiosity that the study of the universe inspires. Broader still, cosmology increases knowledge of the size and intricacy of the cosmos. It pushes the boundaries of our creativity and intellect, and deepens our understanding of the complexity and beauty of the universe. Cosmology is a mirror reflecting how our worldviews evolve in response to fresh discoveries. Every cosmic discovery has the power to fundamentally change the way we view reality, nature, and our own beliefs. Cosmology not only satisfies human curiosity, but also a want to know our beginnings and our role in the world by keeping exploring the cosmos. A basic feature of human nature is this need for knowledge, and cosmology unites people as well. It serves to remind us of our common beginning and end in the great cosmos, therefore fostering a feeling of oneness and purpose that cuts over personal differences. Practically speaking, the study of cosmology improves our skills in critical thinking, modeling, and problem solving. The difficulties of cosmological study help to build abilities that are priceless in many other subjects. Finally, considerations of the significance of cosmology return us to the fundamentals of scientific study, the harmony between knowledge and curiosity. We keep accelerating the cycle of discovery that is both thrilling and humble as we learn more and more. As we come to an end our exploration of the deep secrets of cosmology, I would like to urge every one of you to learn more about this fascinating subject. There are many different approaches to learn more about the mysteries of cosmology, regardless of your level of expertise, seasoned researcher, inquisitive student, or just someone who is enthralled with the universe. Use of educational resources is one of the easiest methods to interact with cosmology. Profit from popular science books, movies, and online courses that provide interesting, understandable explanations of difficult cosmological ideas. A more practical method can be found by taking part in citizen science initiatives. Through data analysis, galaxy classification, or even new astronomical phenomenon discovery, these projects enable aficionados of all ages and backgrounds to participate to genuine scientific study. Join local astronomy groups, go to local stargazing activities and public lectures, and don't be shy. These get-togethers give chances to meet other aficionados, pick the brains of seasoned astronomers, and use telescopes to view celestial objects. Social networking sites provide lively cosmology enthusiast groups where you may post your ideas, pose queries, and keep up to current on the most recent findings. Talking with these internet groups can start interesting conversations and lead to new research directions. If you're a student thinking about going into science, you should not undervalue studying physics, astronomy, or associated subjects. The path to cosmology starts with a strong background in computing science, physics, and mathematics. For teachers, including cosmology into the curriculum may pique students' interest in the cosmos and motivate them to become scientists. Including practical exercises, multimedia materials, and special guests could help pupils grasp and value cosmological ideas better. By exposing their children to age-appropriate literature, videos, and interactive learning opportunities, parents may help foster their interest in cosmology. Early encouragement of inquiry and discovery can set the stage for a lifetime love of science. Recall that cosmology is an open field to fans of all stripes and degrees of experience. There is a place for you in cosmology whether you are a professional scientist, an amateur astronomer, or just someone who enjoys staring up at the night sky. Ask inquiries, test presumptions, and welcome ambiguity as you set out on your exploratory trip. In the dynamic and always changing science of cosmology, every query you pose advances our understanding of the cosmos. Make the most of the abundance of cosmological materials accessible both online and in your neighborhood. When at all feasible, go attend conferences, seminars, and workshops to stay up to date on the most recent findings and research. Give some thought to endorsing groups and schools that advance cosmological education and scientific research. Your gifts may motivate the next generation of cosmologists, support outreach programs, and finance groundbreaking research. Contributions may encourage the next generation of cosmologists, support outreach programs, and finance groundbreaking research. Above else, approach cosmology with amazement and wonder. Numerous marvels awaiting discovery abound in the enormous and enigmatic cosmos. Engaging in cosmology means joining a centuries-old research and discovery history that has revolutionized our knowledge of the universe. Remember that you are an essential component of humanity's continuous effort to discover the mysteries of the cosmos, whether you are reading the most recent cosmological research articles or staring up at the night sky from your garden. Accept the voyage and let cosmological marvels motivate you to go for the stars.